Okay, in this lecture, we're going to be transitioning away from character movement and projectiles, and now we're going to start considering higher level decision making of our agents. So we've seen before our agents can move around our environments through steering behaviors. We can support these steering behaviors through specialized form of decision making called path planning. So we've learned about A star and also especially how to represent our game world through space discretization. Um, but there's other things we might want to do, like make strategic decisions for warfare type scenarios, so maybe flanking or how to attack an agent, maybe decide between using the shotgun and the machine gun or throwing a grenade. There could be the need to unlock a door, some kind of basic problem solving sort of scenario. Could involve pushing blocks around to get somewhere, maybe like solving a puzzle, navigating um, that involves more than just path planning, but also, say, changing the state of the world, like the unlocking the door. Um, and we have seen some interesting capabilities through the movement alone, say through blending steering behaviors. And that can result in some pretty unique and complicated looking um, movement of the characters, but there's a limit to what you can accomplish with that. And even adding on the special case of path planning, there's only so much that you can enable your agent to do without further providing some sort of decision making process. So we're going to be looking at decision making as this design effort to create pre-planned behaviors. So the programmer or the designer of the agent is going to be determining a recipe for the agent behavior. And this means that the designer is going to be implementing the plan that the agent follows and only follows the plan. So all contingencies must be anticipated as part of the recipe. And if the designer doesn't consider something, then the agent is not going to be able to adapt. And that might be that the human player, perhaps an opponent, figures out that the agent does not have a contingency for the strategy used against it. That's not always a bad thing, though. If you think about the purpose of your typical agent, it's meant to be there to provide a challenge to the player, maybe do something neat or interesting in terms of the activities or the challenge provided to the player. It doesn't necessarily need to adapt or the agent doesn't have to recognize that they don't have a plan for something and then try to come up with something new. And that being a rather complicated, uh, complicated in terms of implementing that sort of learning. It's much more straightforward to have these sort of pre-planned behaviors. And so the sort of decisions that are involved in executing a plan is really comes down to conditional logic. So there is some evaluation of game state information. It might involve a bit of pre-processing, taking the game state information and converting the raw data into something that can be acted upon in terms of this conditional logic. It can also include deterministic or non-deterministic conditions. So you might want to not have the agent be completely predictable, and so you introduce random number generation as part of this conditional logic. So there's different types of decision making in artificial intelligence. So there's reactive decision making, which is the sort of the sort of AI that we just talked about. So a reactive agent is going to respond directly to environmental state, leveraging pre-planned conditional actions. So there's some criteria for performing an action based on the world state, and that's all laid out in a way that it's fixed, um, and the agent just runs through the plan and then figures out of the conditions that are there. Which how do you get of all the possible actions? How do you pick one of them, let's say, or maybe a few of them and apply them all at once? So most real-time game agents are going to be reactive. Anything you see like commercial game development, you're going to have a reactive agent. Now you can also have deliberative agents, and this is a case where you are modeling the environment, you've discretized the state of the world in some way, and then inferences are made to determine the plan that can achieve the goal state. Now, path planning is a specialized case of deliberative decision making. There are also examples used in games such as A-star path planning. Let me back up. A-star planning, not specific to path planning. This was popularized in the game Fear, and so we will take a closer look at that in the future. But for now, we're going to focus on some reactive approaches. But before that, I'll also mention that the third type of decision making is reflective, and this is where you actually have the learning. So you might actually have an agent that figures out it's being taken advantage of, and then be able to adapt. And that's one of the most challenging to implement. So reactive is where you just have the pre-baked plan. Deliberative is similar in many ways, but it's able to figure out how more flexibly move parts of the plan around, basically. So it can understand through analyzing the world that there's different pieces of a plan that can be stitched together in a way that can arrive at a goal. So it's can be a more flexible approach to just a strict reactive sort of planning. So we're going to first start off by looking at reactive decision making, and some examples that we will be going over include decision trees, rule-based systems, finite state machines, behavior trees, and we'll also probably take a look at some other less popular but still interesting to discuss approaches to reactive decision making. Hello. In this lecture, we are going to cover decision trees. So this is a form of reactive decision making, and it's one of the simpler forms. So here is a example of a decision tree in the form of a flow chart. And so you start off with an initial root decision to make. And so this is just a little funny example from online, but it is for deciding how to deal with a problem. Like, so does something move? And then if the answer is yes, should it? And if it's not supposed to move, you perform the action of applying the duct tape. Otherwise, there's no problem. And then there's a similar path on the left side. So this is basically a decision tree. And so this is a way that we can make decisions about any sort of reactive logic that, say, an agent needs to make. in terms of gameplay in a game. And so I have a game example here shown in this flow chart form. So it looks very much the same as what we just saw in the WD-40 and duct tape flow chart. So in this case, we're trying to make decisions for an agent related to the presence of an enemy. So is the enemy visible? No. Is it audible? Yes. And then along that path, you end up at the action, which is at the leaf of this structure, and that would be to creep. So like to try to be careful not to be found by the enemy. But there's other possibilities like the enemy is visible and if it's close enough or not. And so you can see how you can sort of represent a bunch of different strategies just cascading down through each of these different decision points. And this being basically a tree structure, but typically presented in this inverted flowchart form. So really all a decision tree is just an if statement inside, nested inside of another if statement and so on. And so you kind of just work your way down, and then the end result of the decisions is that some action is decided upon for the agent to perform. So this is really good for simple decision making that you need to have your agent make, and is great for especially simpler agents as you try to add more and more possibilities. Then things can become difficult to manage. So here is a visualization from the Millington book, just showing the end result of a parse. So you can think of it as just working your way from the top to the bottom and zigzagging down through the decisions according to these decisions that are made. And you'll notice that at each of the decision points that there is some evaluation of game state information. So like if the enemy is visible or the distance. And in some cases, the information will just be already available with no processing, but in other cases, there might be some processing necessary, like computing a distance to an enemy. So there would be some costs with that. And we'll revisit that in a bit, but keep that in mind. In terms of applications for decision trees, most commonly you see it in character control. I think is probably more common with earlier games, and also animation control. If you are familiar with Unity, you've probably seen the use of a state machine rather than a decision tree, but other game engines and especially like internally developed game engines for, say, a particular company has their own in-house engine. Like this is pretty common to find animation control with a decision tree. You also find decision trees used fairly often in strategic or tactical AI sorts of games. And additionally, rule-based systems, which we'll also cover as well. But you do see it applied for those tactical sorts of AIs as well. And really, you can use a decision tree for any situation where reactive decision making is needed. Pretty much any sort of reactive decision making strategy or model that you're using, you could convert from one to the other. And some are just easier to work with in terms of like a design pattern. So some benefits of decision trees: they're very simple to implement. Easy to understand and to read, especially if you visualize them, like in the flowchart form we've been looking at. So you've got that top down and left to right sort of a way of looking at them. They're modular to some degree. You have the ability to stick parts of decision trees together. So you might take a little bit of one and put it somewhere else. And one thing that's probably most interesting about the decision trees is there's this potential for training and learning. We're not going to cover that in this lecture other than just to mention that it is something to consider. So the structure, of course, we have that inverted tree structure, and the nodes are where our decisions are made until we get to a leaf, in which case that we have a special case type of node, which is an action. So anything that's not a leaf is going to involve one of these conditional sort of evaluations of a parameter like is enemy visible. So that parameter, we provide the outcome of the visibility test, and that would be like true or false. And then we can just directly compare that to either the left branch for no or the right branch for yes. Generally, you're going to have 2 branches per node. So it's a binary sort of structure. But you could sometimes have more, and we will look at that briefly in a few slides here. As for the sort of logic that you represent in these at each of these nodes, you could easily make a very complicated node in terms of the logic within one node. So you could say if A and B in parentheses or something else, and just have a really long Boolean sentence to evaluate. But that's not typically what is done with a decision tree. Usually you keep each of the decisions very simple, where it's just a single evaluation, like say you test a Boolean value as true or false. You don't combine it with some other Boolean variable in a compound Boolean sentence. You might, with say evaluating a floating point value, you might have a test of if your test value is greater than a threshold. And occasionally you'll see what's basically an and for a range check. So if T is greater than a minimum threshold and less than a maximum threshold, but that's usually the extent of any sort of compound Boolean. And this works out well. You might think of it as being kind of limiting, but it has just the nature of the tree, that there's this implicit structure to it that allows for Boolean and or. And so I've got a little example here on the slide. So if you want to construct the logic for Boolean and so variable A and B, where A and B are Booleans, then you can represent that in the D-tree structure. So the two figures I have here, A and B, then return action 1, otherwise return action 2. And then it's a very similar example, A or B, then return action 1, otherwise return action 2. So you can see the structure here. I have the root node is A, and then it's got, so testing whether A is true. To the left is, in the first example, to the left, no or false. That will return 2. So that makes sense, because A and B, if A is false, then we can short circuit straight to returning action 2. But if A is true, then we continue the evaluation. So we follow the right branch leading to node B. And then if B is also true, then we continue following down and to the right. and we'll get to action 1. So that is the equivalent of A and B. But if either A is false or B is false, you can see that both lead to separate leaves with the action of 2. However, in the case of OR, we just change the structure slightly. So in this case, we're gonna continue this model of short circuiting. So if A is true in an A or B scenario, then we can short circuit straight to returning action 1 if A is true. There's no reason to evaluate B. But if A is false, that's the only case where we would need to evaluate B. And then, so you can see how you can represent ands and ors even with this simple structure that's imposed to not have compound Boolean sentences. So the reason why you do this is because it makes it easier to restructure the tree. So if your decision tree you actually have like first class structures, say like an object oriented design where you have different nodes that you can just change the references around, then having a simple structure allows for easy manipulation and moving things around. And it's even more so the case if you're going to have the automated sort of restructuring, especially related to learning. So in terms of implementation, like in the Millington book, an object-oriented pseudocode example is provided. We're not going to go into all those details, but you do need some sort of structure to represent the nodes and define the connectivity of nodes with other nodes so that you know the order in which you're going to be processing the decisions, and then which of the decisions finally lead to a terminal state or a leaf, and so that you know what action to perform. So you have to be able to, whatever your implementation is, needs to be able to transition from links to decision nodes to links to actions. And so once you reach an action, you know it's terminal, and then you just can return that. Now each node is going to have some sort of assigned type, like what is it testing, and it will usually be related to some kind of like primitive data type. So you might have a node for testing floats, say maybe greater than or less than, or maybe a bounds check. So you have a low value and a high value. You can test for a Boolean state, and you might have more complicated implementations that are, say, application specific. So if you're need to calculate, say, a vector distance, that sort of thing, you could perhaps extend upon these base node types to make more complicated node types that address the logic that's in your particular game. And then also each node is going to be, somehow it's going to be able to indicate what test information is assigned to it. So you might have just, say, through an object-oriented implementation, you have a reference out to game state that you programmed into the node. But there could be other approaches too. You might have like a lambda function that's that you provide to the D tree, and then so it's wrapping some sort of information source. So there's lots of different ways that you might approach it. The design of a D tree, it'll probably partially depend on like the programming language you use, the nature of the data, and how you access the game state information to pass to it. But once you have the D tree structure in place, and have indicated the types of tests, what the tests are, and what the actions are that you arrive upon, Then you need a way to evaluate this, and that'll be a recursive approach, not necessarily through like your programming language recursion. You could iterate through and track in that form, but conceptually recursive, and then just tracking through each of the decisions until you get down to the terminal action state or the leaf, and then so that's returned as the action, and it could just be an action by name, or you could actually be directly calling some sort of like an executable method that initiates the action. So really, there's a lot of flexibility here. There's not anything like set in stone for how to do it. It's more just the methodology of representing your decision making process. So just the fact that we're forming this tree structure, you can see that there's maybe, I guess you could think of it as a nice feature of the decision tree, in that you don't have to analyze all of the decisions that are possibly involved in selecting any given action. You just you evaluate the root node, and then you either go to the left or the right. You don't have to evaluate both sides. And so that means you're only ever evaluating a subset of the tree. And if the tree is well balanced, then that's going to minimize the depth of the tree, and therefore the number of decisions that you'll have to make is also minimized. Now we could also consider the number of branches, and so far we've continued to look at a binary tree, but we might have n-ary trees where we have n branches, and there could potentially be some benefit in that sort of an implementation. But often, if you think about the nature of any sort of game logic decisions you would make that would involve selecting across multiple choices, the simplest thing is you would just have if, else if, else if, else if, and so on. And computationally, there's not going to be any benefit to that sort of evaluation within a D tree to do that all in one node versus just chaining together multiple nodes. And maybe just the tiniest bit of difference, but I mean, very, very negligible. They're really the only way to make it considerably faster is if you can come up with some kind of mapping function that generates from your test data an index into a lookup table. So that way you avoid the chain of if statements, and then can just jump straight to an indexed position in the table that would tell you which of the multiple in branches to take. But that would probably take a lot of work. Many sort of decision problems that you would be considering in your game that would involve something more complicated than a binary decision, coming up with that mapping function could be non-trivial. It could take a lot of work, or just not even be a sort of a natural approach to solving the problem. So this is all sort of leading to you're probably better off just sticking with the binary tree. And again, it does have the benefits of simplifying the shuffling stuff around. If you want to like snap off a part of a tree and move it to another place, just kind of manually moving things around, that's more likely to be straightforward with the simpler tree structure of a binary tree. In terms of knowledge representation, I mentioned before about accessing game state information. So we have these standard sort of node implementations to handle like our Boolean values, our floating point values, and so on. And so we'd often have nodes of those types maybe extended in an object-oriented sense, or some other means of connecting a type of node with game state information. And so we don't have any we don't necessarily have a well-defined abstraction that's separating the implementation of the D tree from the implementation of the game. And so this is one of the downsides of D trees, because this is not well there's not a well-defined like software engineering pattern or principle here to try to decouple the two, so that you end up with them kind of this tight coupling of the D tree with game state. Now, where this is problematic is a lot of times when you're writing a D tree, you'll have like a common path through the tree, so like a common parsing. So when you're evaluating at each node, like one of the branches versus the other is probably going to be a lot more common, and it's going to get progressively more rare, or potential for more rarity in evaluation. So like if you're just running your game in like a demonstration mode, you might possibly never see certain branches trigger. They might be so rare that you don't see it unless you kind of like force the scenario. And so if your game is evolving, and that's common of games, so like you're say a team developing a game, things are going to change about the game. So you may have already written the AI for the D tree, and then something in the game changes for some necessary reason, and you had the D tree connecting to that game state information. Well, that could change, and it can result in subtle bugs, and that's in the D trees. So you have these bugs in the D tree making bad decisions, and it can be compounded by whether this is in more rare nodes of the tree. So yeah, that makes things kind of problematic there. Now, in some cases, when you are connecting the knowledge of the game state with the D tree, it's not already going to be in the right form. You're going to have to do some sort of processing. So you might know, say in the case of the distance, vector distance information, you know the positions of objects, but in the game state, there was no reason to calculate and store distances. So there's a computation associated with that. And of course, it could be a much more expensive calculation than just a distance, like a Euclidean distance. So in those cases, if it's only information that the D tree needs and nothing else in the game needed it doesn't exist yet. And so in terms of the D tree, you don't want to calculate everything you might need in the all decision nodes in advance. Instead, you just wait until you're parsing and arrive on a node that needs certain information. So that this is called lazy loading. You wait until you actually need the information to calculate it. And so that's a common approach with a D tree, and it works well. So if you parse to the left of the tree and you don't need that to calculate that distance of the player and the enemy, then it never happens. But if later you do need to calculate it, that's only going to be because you landed on a node where that information is needed for the decision. So there's a performance benefit there. All right, so there might be a temptation when you look at the fact that a D tree is a tree, and you know that you're going to minimize the expected number of nodes visited. If the tree is balanced, you're going to put a limit on how deep the any given parsing is going to go. So that's going to be big O log of n. Instead of if we had like the worst case would be just a completely unbalanced tree where it's just all like a linked list, and so you would have big O of n. So you might be tempted to want to like really work to force a balancing of the tree, but in reality, you're going to get better average performance if you take into account that some actions are going to be more commonly selected, and so the path to those common actions is actually better to have a shorter number of decisions to get to those common actions than rare actions. So it's non-trivial to balance a D tree because balancing isn't as straightforward as just the standard sort of balancing. It's really more like a weighted balancing is what you're desiring, and to do this by hand is kind of a black art. You've got to have some intuition on how to design the decisions and how to shuffle things around. So just taking the position that, well, you should always balance the tree as best you can isn't the best solution. You need to really also consider what are the most common actions to be performed as well. Now, one interesting possibility is that you can streamline things, maybe minimize the number of nodes by merging branches. And this can work with minimal impact on the implementation of a D tree, provided that the end result is a directed acyclic graph. So otherwise, what you end up with is a loop, and you could, I guess, potentially write an algorithm for your D tree that would detect that a loop occurred and then do something. But it's better to just keep the parsing logic, the recursive call of evaluating your D tree. Keep that simple, and then just if you're going to use any sort of branch merging, just make sure that it maintains the directed acyclic nature to it. And so there's a couple figures here from the Millington book to show you what this might look like in a decision tree form. So the upper example is a valid directed acyclic graph with a branch merge, and then the lower figure is an example where there's a loop and where that would be problematic for the D tree. All right, so another thing that would be desirable with a decision tree would be to extend it so that it's not so predictable. And that's one thing that is really a challenge for all reactive decision-making strategies, is the fact that agent behavior can become very predictable, and human players especially are going to notice that. They're going to take advantage of it. They're going to become bored in gameplay that involves predictable agents. And a good strategy to try to minimize that perception is to introduce some sort of randomness to the decision making. So in the case of a D tree, this is a little tricky because we don't maintain any sort of state naturally. So like with a state machine, which we'll talk about later, the agent would be in a state for some period of time before going to the next state. But with a decision tree, the state, there is no state. You just, every time the agent updates and is leveraging a decision tree for decision making, it reevaluates the decision tree and arrives on an action. And so if in, say, the current frame, it arrives on, say, patrol, as shown in this figure, the next frame it might arrive on defend, and it'll just immediately make that change. Now, this is tricky if you want to integrate the the random decision making, because let's say in the case where you see the decision node for flip a coin, if you're reevaluating this every time, and when you arrive on flip a coin, you have like a 50% chance of heads and a 50% chance of tails, then you could just be flipping and flopping back and forth between patrol and standstill over and over as fast as the frame rate of the game, or as fast as the updates of the AI goes. And so that's going to be probably not what you desire in terms of designing behaviors in your agents. So instead, what you need to consider is introducing some stickiness. So you want to, in any case you pick a random choice, that needs to be maintained until the state of the game world changes that would affect other decisions. So like if for instance, if you had parsed in the lower direction towards flip a coin and selected tails to stand still, you would want the character to continue to stand still every time under attack keeps parsing no. So if the last frame you parsed under attack no and arrived on flip a coin, then you're just going to remember, oh, well, the last time we flipped the coin was tails, so you just keep going that route. But as soon as flip a coin is not arrived upon in consecutive frames, then you know that the world state had changed before it comes back. So it's a pretty trivial implementation change. You just add to the nodes tracking to know what frame it was, and so if it knows that its consecutive frames keeps arriving on the same node, you preserve the choice through the stickiness. But if you know that it's a new visit in the near term to a node, then you reevaluate your choice. And you might couple this with a timeout. So just in case, you might say that, well, the flip a coin stuck on tails, it's only going to stay stuck on tails for, say, 20 seconds. And that allows agents to break out of getting stuck permanently. So it takes maybe a little bit of thought to get this random decision tree implemented, but the end result in terms of what needs to be implemented is really pretty straightforward. It's just a little tiny bit of extra logic to introduce the stickiness. All right, so just to wrap up our initial look at decision trees. So we've seen that they're easy to implement, easy to understand, and to read with a top-down, left-to-right flowchart. They have a bit of modularity to them because you're able to stick parts of D trees together. They perform well. There's a little overhead involved in the decision tree, but downsides is they can quickly become unwieldy as you get these deeply nested trees, and there's limited structure for access and game state. So the end result is you can end up with this tight coupling. We talked about how that is prone to error as the game evolves, as the implementation of the game evolves, and just the nature of the decision trees with the rare branches that can be difficult to find. Hello. In this lecture, we're going to take a very brief look at rule-based systems. So just an introduction to the basic concept and kind of set the stage for comparison with, say, decision trees and finite state machines, behavior trees. We will revisit rule-based systems in the future and look at some more advanced implementations. But for now, we're just going to focus on the basics. So rule-based systems was a very popular strategy for early research in AI. So especially the era of symbolic AI and expert systems. Rule-based systems were core to that effort. So that was the height of research in the 70s and into the 80s. A lot of the original implementations were in Lisp, which was or is a language dedicated to manipulating list data structures. It's not necessarily appropriate for video games, though there have been games in the past that have either been built with Lisp or had a AI subsystem that worked with Lisp. In terms of what a rule-based system is, at its core, it's not a whole lot more than just a series of condition action statements. So like, if condition, then perform action. So it's similar to decision trees in that it's a really simple concept, but we can build upon that to pretty complicated systems. So the simplest way you can probably set up a rule-based system is production rules, where you just have a fixed priority arbiter. So we haven't defined what that is, but it basically it's the notion of dealing with the possibility that you have lots of rules that could be executed, and so that would be called like the rule is activated. So if you have lots of rules that are activated, how would you pick one? Well, we're just going to skip over that whole scenario by setting up our rule-based system in such a way that we don't even have that come up. So in this simple strategy where we have this fixed priority arbiter, we are just going to have a series of if statements, basically. And we are going to analyze each one in order and then determine if it activates, meaning if the conditional statement evaluates to true, then we'll have an action that's matched with it. So that's like the if, after the then statement. So we have the if condition, then action. That action, we're just going to immediately return that to execute. So we're not going to further consider any rules. So we have this implicit structure for execution. So we'll take a look at that in a second. So as you can imagine, this is very simple architecture. Even if we add a little bit of complexity, rule-based systems, at least in terms of representing the condition and action statements, that itself is pretty simple. Now, sometimes the interpretation, like in more advanced rule-based systems, that can get complicated. It can, however, be difficult to organize. If you have all of these statements in isolation, there's no structure, there's no grouping or organization typically. So if you just looked at all of the rules that might be part of a rule-based system, it's not necessarily going to be easy to interpret or to organize or to figure out, like, if you are given an existing rule-based system, how do you extend it so that it effectively adds new behavior to an agent or improves upon its decision making? That is a challenge. So here is an example of production rules with just the simple implementation with fixed priority. The priority is defined strictly by the order in which the statements are presented. So the first statement is executed, and then you move further from there. Now, typically, the way these work, when you have this fixed priority, you'll need to place more specific scenarios first and more general scenarios later. So for instance, you might have logic for an agent dealing with encountering an enemy. So you could say, if the big enemy is in sight, run away. So that's a specific interpretation of the enemy that is available through like the state of the game. We can make a query against the game state, and so maybe we have a method that we call that can calculate whether enemies are in sight and also the size of the enemy, like some sort of decision making process there. So that's a specific sort of analysis of the state of the world, and of course, if that matches, immediately we can return the action run away, and so that would be then executed by the game, maybe steering behavior perhaps. And now the second statement. So if that first statement does not evaluate true, it's not going to execute the action. So now we're on the second statement. If enemy in sight, fire. So in this case, it's more general. So imagine if we swapped those statements. The first one now being if enemy in sight, fire. That would mean that if there ever was a big enemy in sight, that logic could never be run. So that's why you have to kind of think in terms of more specific to more general. So let's see. Now, normally, we could, well, in fact, we actually can have multiple rules that that could evaluate to true. So normally, this is a big problem in a rule-based system, and that being you typically like a more general purpose, more capable rule-based system implementation, you would evaluate all of your rules and figure out which ones are activated, and then from there you'd need an arbiter that would select as appropriate. But again, we have simplified the problem by just saying we have a fixed priority. The priority is defined by the order in which we list the if statements, and that is kind of an implicit arbitration. That so we don't need any special logic to evaluate it. So this, if you've ever set up like firewall rules for networking, so the firewall settings to decide which packets or connections to allow on different ports, you have the same sort of logic where you have to put the more specific scenarios first in the list and then progressively more general as you go. So this can work really well for simple agent AI decision making, and it's nice in that it's stateless. So of course, like a finite state machine where it's got state in the name, so we don't have any overhead of maintaining any state. There's no impact on memory. The evaluation is also nice because, and this is kind of sort of rare for most rule-based system implementations, in that, worst case, we would be evaluating the very last rule. Like each rule in a sequence would evaluate false until the last one evaluates to true, and then we'd run that. So in worst case, it's going to be big O n, where n is your number of rules. But on average, you might go partway through the list, and so you don't have any overhead of the arbiter having to select among perhaps multiple rules that match. And again, this is something that gets quite a lot more complicated and a lot more overhead computationally when in a future lecture we will look at more advanced sort of rule-based systems. I did want to mention one other scenario. So we're going to get rid of the fixed priority. So this is a simple example that only just a tiny bit more work is involved, but it creates a much more capable rule-based system. So we still have an arbiter, but it's very straightforward to implement with using data structures that everyone in the class should be able to work with. So the basic idea is that we will still have our list of rules, so with a condition and action, but we aren't going to immediately return the first rule that matches. We're not going to immediately return. Instead, what we're going to do is we're going to populate a list, and this could be it doesn't have to be like dynamic memory allocation list. It could be an array. We know the number. We know how many rules we have, so we could just have an array that is as long as it needs to be for the possibility that all the rules matched. So that would be a reasonable, efficient solution in mini games. So I've got just a little bit of pseudocode here. So imagine we have a list of some sort, perhaps an array of activated rules. So we start off initialized at empty list, and then we go through our rules, like if condition, then we will add to this list of activated rules an action with an associated priority. And this priority will be dynamic according to the condition. So this might be like game world state. It could actually be related to the condition or other information as well. So for instance, an example would be if there's an enemy near, then you could have add an action to the list of candidate rules that you're going to possibly execute. You don't know yet if you're going to, but you could have, let's say, a rule for attack the enemy. So if the enemy's near, we're going to add attack the enemy, and the priority is going to be based on health. So we'll say if it's a low health, then it's going to get a low priority, because it doesn't make sense for our agent to go attacking if they're badly hurt. We could have another rule that is, if the enemy is near, then the action would be to run away. And then we could have the opposite priority. So if the health is low, then we would have a very high priority. And so there could be a whole bunch of different rules that are activated and or fired. Not fired yet. They're activated, and then when we get to the end of all our rules, we will just select the highest priority. So that's the extent of our arbiter. Is that it's just going to say, all right, there's a whole bunch of rules that were activated. I'm going to find the one with the highest priority, and that one's going to be executed. And so this is really pretty straightforward. It's simple to implement. Only a little bit more work than the fixed priority, I would say, and hardly any more overhead. And so this is something that very quick and easy to implement, and would be great for simple agents. So either the two strategies, either the fixed priority or this simple dynamic priority approach, both very straightforward to implement. So again, we will be revisiting rule-based systems. So we will look at adding more capability, especially requiring a more complicated arbiter. We'll look at other features like how to more efficiently evaluate rules. You'll notice one thing that came up as soon as we went to the dynamic priority, we had to allow for every single rule to have an opportunity to activate and to assign a priority. So that's I'd say the weakness in general for rule-based system solutions is most of the time you end up having to evaluate all the rules or a lot of rules, and so a lot of the strategy with a rule-based system is making that the fact that you have to evaluate all these rules, making that process more efficient. So yeah, that's something that we will touch on again in the future. But for now, you have a basic idea of what a rule-based system can be, and you can compare and contrast with, say, decision trees and finite state machines and behavior trees. Hello. In this lecture, we are going to look at finite state machines. So finite state machines are a very popular strategy for implementing reactive decision making AI agents, especially in games. So first off, we'll look at just some of the basics of the structure of a finite state machine. So we have components in the form of states, and these are often visualized in these flowcharts that show the states and then how you get from one state to another. And so that the way that we get from one to the other is through a transition. And so we can define these formally as sets for the states, and then a transition function that defines how you go from one state to the next. Now, the transition function acts on an input vocabulary, and in relation to like an actual problem, the input vocabulary, it would be like the information about the state of the world or the problem space. So in this case, this would be like the game world state that we're talking about. And so one of the states within our set of states is going to be the start state. And then they'll generally have a final state in like a classic or conventional sort of finite state machine. But in a video game, you often will have a finite state machine that never ends. So it's just the agent, as long as it persists, will just continue to move through states. It might have like some idle state that it will stay in. So structurally, a finite state machine is not very complicated. There's a few other rules, such as you can only be in one state at any moment in time. Though you might, as we'll see, we might break that rule on occasion, especially with hierarchical state machines that we'll look at in a bit. And so you can make transitions from one state to another, or you can cause some sort of action to be taken according to the states you're in. And there's a few different ways, or a couple different ways, that we can formalize the action taking, which we'll look at in a bit. So each, in like our game application, each state in our state machine is going to be associated with a behavior of the agent that will be performed. And so the agent's going to respond to the change of the world state. That's like our inputs to the transition function. So there will be some sort of conditional logic that gets evaluated. We will grab information from the world state, apply some sort of comparison. There might be some pre-processing necessary in the form of some kind of metric. So we might like calculate a distance or a visibility test, depending on the nature of the behavior that we're modeling and the decisions that need to be made to support that. So an example, very simple example shown here. You think of it as these different mental states that we're modeling, as if this was a human, and we just have this kind of abstract notion of different behaviors that the agent is taking. So we might have, say, the mental state for gathering treasure or fleeing and fighting, and then these different world events or world state that arises through the course of the simulation. So that might involve suddenly a monster is in sight. So the agent was gathering treasure, but now the monster's in sight. It leaves the gather treasure state, enters flee, and will perform the flee behavior until there's an opportunity to transition out. So maybe the monster is no longer in sight because the agent ran away. So we could now have the agent go back to gathering treasure, or perhaps the agent gets cornered as they're fleeing. The monster chases and corners, forcing the agent to have to fight. And so we could recognize this, and so you'll notice that the agent is only able to perform activities that are represented in the finite state machine. So if there's not a behavior there already, it can't perform it. And furthermore, it can't perform a particular behavior unless it transitions there. So you have to, in terms of authoring a finite state machine, you have to be aware of all the different scenarios in which the transition can occur or should occur. So here's another example. This would be like one of the townsfolk in, say, Warcraft 2, chopping wood and taking it to a depot to drop off. So very simple sort of state machine, but this would be a great scenario in which to implement a state machine. Just simple activity, and we can organize the different behaviors that are involved in this chopping wood, collecting the wood, and taking it back using a state machine. We can tie our different states to many of the behaviors that we've seen before, and especially related to character movement. It's also quite common to associate different states, the behaviors performed with a state, with animation systems, so that each state is coupled with animation. Now that is something that gets a little tricky, and we will revisit that as well. Transitions that would possibly occur, of course, events in the game, which are usually an event is just a change in world state from the previous frame to the current, and we have some sort of logic that recognizes that change, and so it is marked as an event and acted upon. So completing an action, and these could be things that maybe is internally tracked with the implementation, say, of this little townsfolk person chopping wood. We just know that there's a certain amount of time that they have to perform the action, and that's just built into the game. And so they perform this chopping long enough, and when they're done, they have the resource, they take it back. So I mentioned before exactly how we go about the actions being executed varies with implementation. So there's two primary ways of doing so. There is melee and more. And so with the melee strategy, you have, with both strategies, you have your states and you have your transitions, but with melee, your transitions have an associated output. So there is an input, recognizing an event has occurred, and then an action is performed as part of the transition. So transitioning from one state to the next performs the action. And you would often see melee implementations where you have a loop back, like a loop back to the same state. So each frame, you reassess the current state of the world, and you might have an input event that keeps occurring over and over. So you just stay in the same state, looping back, and then that act of following the transition back to itself triggers the behavior or whatever the action is. But with more, which I think is more typical, and that is where the action, like whatever response the agent is taking, it's just whatever the current state is, decides that. So there's no input requirement to executing a behavior. It's just if you're in that state, the agent will continue to perform that state. So if you think in the context of a game event loop, every time the agent stays in a state, they keep performing that same behavior. So it might be repeating it over and over, or just continuing the behavior. So if it's, say, walking on a patrol, it would just, the agent would just keep doing the steering behavior for the patrol uninterrupted. So it's a little bit different approach. You see, Mealy, I'd say is well, I think it originated in like electronics design, where you have a state machine, say for the buttons on a microwave or something like that. But there are some situations that we'll see in a bit where Mealy might make sense for some designs. And if you did have like actions you want to perform primarily in response to different events occurring, it could actually make sense to use that strategy. But again, I think more is the more approach is much more common. One thing that comes up as you're building a finite state machine is that they're very simple at first, and it seems like, oh, this is a great way to organize my strategies for my agent design. But things can snowball very quickly, and we'll see more examples of this. But I wanted to go ahead and mention a strategy that can be used to help reduce the explosive growth of your finite state machine. And that is to support global transitions. And so this is an example. This is actually from Unity's animation system, which uses a state machine. So this is not an AI example, but I think it gives a good idea of how this might work. So here, I've got a visualization of the state machine designer for the animation system. It's called Mechanim. And you'll see a number of states. So there's this idle state, which is the initial state, and that you can tell it's the initial state because there is a transition from entry into idle turn, and so that tells us that idle turn is the initial state. And there's different ways that this could be denoted, other than the transition line from entry. So not every finite state machine is going to have exactly the same sort of layout. But the one that is interesting is this any state. So you can see that there is an any state that goes into falling. So what that means when you see the any state is that it's a wild card. If you didn't have the any state, we would need to have a line going from blend tree forward to falling, and also from blend tree backward to falling, and also from idle turn to falling. So that would add several additional transitions that would have to be drawn on the screen. That would also be getting in the way of other things, maybe overlapping or basically making a big spaghetti mess. And in this case, for the scenario here is that so the falling animation, as you might imagine, it involves a character that begins to fall. So it plays a special animation for falling. But you can have an agent that starts to fall from any of these different scenarios, whether they're walking forward, walking backward, standing in place, and maybe the floor falls out from underneath them. All of those are valid scenarios where you could begin falling. And so if you have a finite state machine that allows you to just do this wild card, it really simplifies things. And in case you're wondering, it is possible that you're already falling, and then the any state would match with falling. So in fact, Unity has if you select the transition, you can choose whether to allow a transition from the same state. Otherwise, you override it, and in this case, it's overridden. So the any state is not applied. So if you're already falling, and then the next frame you detect you're falling, it'll ignore the wild card in that situation. So let's consider a little scenario, and you might want to consider the scenario and just pause the video before moving on. Just maybe think about how you might build a finite state machine, and I would suggest that you draw it out as like a flow chart with states that you represent with like a circle or a box or something, and then draw the transition lines according to the different conditions that would lead to the transitions. So imagine this scenario where we have a security guard that's patrolling a school after hours, and maybe the player controls a student that is breaking into the school and causing mischief of some sort. So we want the agent to chase after the player, and if the security guard catches up to the player, then they will have to sit there and wait for a lecture to finish. So he's going to point his finger in the kid's face and talk for a while and slow the kid down from doing whatever, and then eventually the player can slip away. So that'll of course he'll chase if he sees the student. The security guard will chase if he sees, and then if he catches, he'll do the lecture. Otherwise, when not seeing the student, we'll just switch between idle and patrol. So not a very complicated behavior. So clearly we've got 4 states: idle, patrol, seek, and lecture. And so you got to figure out what are the transitions and what is the information that you're acting upon. So if you are going to try to figure this out on by yourself, it'd be a good time to pause and finish thinking it through. But otherwise, I will switch to the next slide now. So here we have just a simple implementation for the security guard. So we have our state idle, and so I haven't shown the initial state here, but we'll assume that we'll start in either seek or idle. It doesn't really matter here. But then we've got patrol and lecture, but you can see all the different transitions that we have. So one from idle to patrol is based on a 5-second wait, and patrol is also a 5-second wait, perhaps, or we could have maybe a different amount of time to do the patrol. I guess it depends on how fit the security guard is. Then the patrol, we've got sees player, transition out of patrol that is sees player, and that will go to seek. And then from seek, if we get close enough, then it'll initiate the lecture. Otherwise, we'll keep seeking as long as we see the player, but as soon as the player is no longer seen, that is triggers the transition back to idle. So yeah, we want to make sure that any state that we transition into, that we can transition back out, and it doesn't matter if this will go on forever. We don't need a terminal state. We just need an initial state, and ideally not get stuck in a state. So pretty straightforward to implement. Now, it's one thing to work with like a visual representation for thinking things through, and of course there are editors that you will find with various tools for implementing a finite state machine. But another common way to implement one is with a state transition table. And so the state transition table just lists all of the different possible transitions. So it's like a representation of our transition function as a lookup table. And so it's based on what's the current state. And then for any transition you have a different line. So you might see multiple lines with the current state, such as patrol here. And it basically, the table just tells you what the condition is, and then what the current state is that has to be matched with, and then where is it going to transition to in terms. So it's just tells you how you're performing the transition. And so this is an efficient way to represent the different states and transitions that might be occurring. So finite state machines have various problems with them. One is that they're very predictable. Sometimes that can be a good thing. And we've discussed before how agents don't necessarily always have to be very capable. Sometimes the predictability is desirable, but if it's not desirable, we can introduce some sort of probabilistic nature, where maybe the transitions that are occurring are not strictly deterministic. We're going to roll the dice. We've seen that sort of approach used before with like decision trees. Now, in the case of a finite state machine, if you fail to transition, rolling the dice to decide whether to transition in addition to whatever other the criteria are for the decision. So if we fail to, like, say, roll a number higher than a threshold, then you stay in the state. So, and one thing you got to watch out for in this scenario is that as often as you update your finite state machine could vary, and that, so like your frame rate of your simulation varies, and so I believe we talked about this a little bit before with the frame rate varies and the impact it can have on like character movement. So you always want to have things related to the amount of time elapsed from the previous frame. So this is definitely a situation where this comes up. If you've got your frame rates varying when you're updating your finite state machine, then you would definitely want to make this probability be time-based. So the likelihood of the transition occurring is going to be proportional to the amount of time elapsed, rather than just always some fixed value. And the problem you could run into is, let's say you have a game that, so you write one implementation of the game, but you have one game player playing on a very powerful computer and they're getting, say, 60 frames a second. And then you have someone else runs it and they can barely get 20 frames a second. The opportunity for the agent to make a probabilistic decision is going to, there's going to be more opportunities at the higher frame rate if you don't compensate for the elapsed time. So the player with the lower frame rate, each tick that gets updated, the probability should basically be higher that the transition occurs compared to the 60. And that if the frame rate rises and falls, then it needs to, the threshold needs to follow as well. So something to keep in mind. Well, I'll probably bring that up again in the future, just because it is such an important issue. Another thing is that finite state machines tend to be very simplistic, and it's difficult to model really elaborate sorts of behaviors, we will consider the use of a hierarchical finite state machine as also finite state machine stacks. Both of those can allow you to model much more complicated behavior and avoid some of the challenges that are created when you try to build a very complicated state machine. So next up, we've got some more difficulties here. So the complexity I just mentioned about the state machines getting too much, like too many states and too many transitions. And so you can address that with like a hierarchical or a stack sort of approach. But if you don't do that, what can happen is basically you have a combinatorial explosion. So as you try to deal with more and more contingencies, like exceptions to normal behavior for your agent, then the way that you address that, like with just a normal state machine, is, well, you have to add more transitions and more states. So if you have some contingency, you got to leave the current behavior, go do something else, and then maybe come back again, maybe try to continue on the whatever behavior was before. But what if it was like a partially completed task? That means more states and transitions to try to track that. And so that gets really difficult to deal with. So yeah, it's basically you have this problem of a combinatorial explosion. So there's a point, like a tipping point, I would say. It's like a finite state machine starts off great. They're very capable for simple things, but then you can get a bit of a feature creep, like, oh, it'd be nice if the agent can do just a little bit more. And then you start to add that, and you realize, oh, I got to add a lot more logic to deal with this. And if you miss one little thing, you can have the agent get stuck in kind of a degenerate behavior, maybe flip-flopping back and forth between two states. So that can be difficult to deal with. Also, one thing you can have trouble with finite state machines is they don't really work well if let's say you have a sequence of steps to perform. Your agent needs to do, say, step 1, step 2, step 3, and so on. You can have difficulties there. And again, this is especially a problem if performing this plan can be interruptible, like dealing with a contingency and then needing to remember where you are and come back to it. That is a really difficult thing to do with a finite state machine. So advantages of the state machines, of course, that they're very popular. It's probably my go-to solution anytime I'm implementing like an AI agent for like a video game or a virtual environment, something like that. The first thing I will probably implement will be a finite state machine. Just I'm familiar with them. They're easy to implement. There's a number of different ways I will implement them. I've built myself, pretty, I guess, complete implementations with like a number of different features, but I don't necessarily always use that. I will often just whip up a procedural implementation. We'll look at some pseudocode for one in a second. So there's not very much development overhead. And, if I can just start writing one from scratch without needing to go import a library, then they are that easy to deal with. They often can be easy to visualize and debug. Of course, we can see the flowchart sort of implementation. Debugging, it depends on how complicated your state machine is as to what you're going to be dealing with. But there are ways, of course, to also visualize the debugging of the state machines. Um, so, if you don't have like an overly complicated, meaning like number of states and transitions, if you're not to that point yet, they're usually pretty easy to deal with. And you can even have sometimes state machines that with the visual programming and pre-made states that you can just drop in that are already implemented. You'll occasionally find visual programming that are designed so non-programmers can think in like a finite state machine sort of design, and be able to come up with effective agent behaviors that way. There's very low cost in terms of computation for your finite state machines. Since you're only in one state, you only have to consider the transitions for that state. And as long as any sort of metrics that are being calculated for each of those transitions isn't high, then it's going to be a low cost. It's barely going to add whatever is required to maintain the given behavior of the current state and evaluating those transitions. Also, they're very intuitive as well, just understanding, okay, I'm in a state that equates to some behavior that's being performed over time that may be transitioned out of for various reasons. All right, so some code here. This is a procedural implementation. And so really all you need in order to get up and running with a simple finite state machine is just like an enumerated type. And you don't have to have like an enum, for instance. It can even just be an integer, and maybe you have some constants. You just list out a number of constants at the top of your source code, and it would just be named whatever the different behaviors are for your agent. So patrol, go to ammo depot, and so on. And of course, you need to have a variable that'll store this enum or integer value. And then part of your update loop, so it's going to be called every tick of your update cycle for your simulation. You're just going to maybe go through like a switch statement, for instance. So you're going to say, run a switch on the current state value for your state variable, and then you will list cases for each of the different possible states. You'll have logic associated with maintaining the behavior or transitioning. So you check all your transitions, and if none of those execute, then you just perform whatever behavior, so like a steering behavior perhaps, and that's it. You just wait till the next update and continue. Now, if you do have a transition, what you're doing is you're just assigning a new value to the to your state variable, and you just go ahead and break, and you wait until the next update, and then now you're on a new state variable value, which means a new state, and you'll execute a different block of the switch statement, a different case. So conceptually, it's really the concept of a finite state machine is very simple, and it doesn't take a lot to implement. Now, this sort of procedural implementation, this is great for just when you're prototyping something, or just have something very simple, very small, self-contained program. Great for that, like making little examples, just that you're trying to figure something out. Otherwise, you probably want to go to something with a lot more structure for a more complicated problem. And so a common strategy would be to use some kind of object-oriented design where you can encapsulate your different behaviors and the transitions in like a class. So you'd have maybe you define a class for a certain state, and you'll have a common behavior of each state that you'll need. So you'll be able to enter the state, And then once the state's entered, you'll have future frame updates of your simulation where you'll call execute. And so that will be meant to run in a very brief amount of time, making decisions about transitions or performing the behavior, and then you'll exit potentially. The exit can be optional, but so like say execute decides to transition, for instance, then whatever, like the finite state machine manager that would be calling and selecting between the different states, it would call exit right before it transitions to the next state. So you'll often have those three, and you see some variations. Like sometimes the execute is really, it's just performing the behavior or the action, and any transitions, they're evaluated separately. So you might see, say, a third public method that is common in the object-oriented sense. So you might have enter, execute, evaluate transitions, and exit. So there's some variations in the implementation, but having this sort of object-oriented structure can be helpful. And especially it helps to organize a few other things that I've found useful in finite state machines. So one of those is parameterized transitions. So quite often you'll see implementations that don't bother with any sort of parameterization, but it is typical that you have states in your finite state machine that need information on which to act. And normally you just say, well, all the information you need is in the state of the game world, and you can just go there to get it. But you, as finite state machines get more complicated, you might have scenarios where there's some information needed in order for whatever state you're transitioning into to work effectively. So it might need to say a target if you're transitioning into a state to attack a target. So it would be nice if that target is provided. And so one way that you can deal with this problem, and then not. So let me back up a bit. So one thing you can have happen where you run into trouble is you implement something and you come back to it later. So you have a state, and at the time you wrote it, you knew exactly what it needed. Say it needed a target, it needed a few different things tweaked or configured. And later, when you're going back to the code, you add some new states and you realize you need to build a transition into that particular state. And you forgot all the things that needed. So you do the transition there. And then you run your code, and there's like a bug that you encounter, maybe a null reference, or the agent just gets stuck not doing anything because, well, you didn't assign a target, so it has nothing to do. So if you explicitly enforce, as through the design of your finite state machine framework, that this state, a given state, it requires a parameter to be passed, then you can't call it later not knowing what the contract is for executing it. By having the parameter, and you can only be entered with the parameter, then when you go to use it, or someone else works with your code and extends it, they're like, oh, I cannot call attack enemy until I provide a enemy target. And so that is something that can be a really nice feature for a finite state machine, is to have these parameters. Now, of course, this can get tricky with a finite state machine because with it, like an object-oriented design, you've got variable number of parameters that would be possible. Like one state machine might not need any parameters. One state in a state machine might not need any parameters. Another might need one parameter. Another might need 2 or 3, and so on. So this tends to kind of like really push at least in terms of language features, it pushes the need for either generics or templates, depending on which language we're talking about. So you need these more advanced object-oriented features in order to be able to flexibly define how many parameters that there are going to be. So if you ever see, like I've got in the prison dodgeball example, you can create states that take variable number of parameters, or you can have none or one or two and so on. And so you have to be familiar with the generics feature of C# in order to understand how to define or declare classes that have parameterized transitions. Now, another thing that can come up that sort of another software engineering sort of challenge with finite state machines, that is related to when the transitions occur. Now, I like to have transitions that occur from the execute or the update part of the finite state machine. I don't like to decouple the transitions from the update logic, because sometimes I think to be the most flexible, you keep the two together, because sometimes as you're making the decisions about performing the behavior, you discover the situation that leads to the transition. Now, when that happens, you could return that the transition is going to occur. Like you could perform the update, say assign a new state, but then you're kind of in this in an odd situation where exactly what happens when you assign the new state. If you call and enter a new state, but you don't return from the current code that's executing and run code after that. So you have to be really clear. Like if you're calling enter state, does that mean that it's executing the entering of the new state, like the enter of the other state? Or is it just denoting that this will occur in the future? So in order to be as precise as possible and as clear to the programmer as possible, I like to have a deferred state change in the form of a return value. You could do this in other ways. You could just call, say, a method that sets the deferred transition at any time and maybe could be overridden at any time as well. But it doesn't get executed until the return happens. But I actually do that as a return. So it's a returned value. But as long as you're clear about it, that the entering of the next state will not happen until after returning from the current update of the current state, I think you're good. So you could have some flexibility in how this is implemented. But it does create a little bit of a challenge if you do have deferred state changes, whether it's by return value or just by rule, like you call some method that sets a parameter. In either case, if you like the previous slide, we were talking about transitions that are parameterized, meaning that the state you're entering requires some information. So that adds some complexity as well. So if you have a deferred state change, then not only is it being deferred, but also you have to provide the data for the parameter. So whatever the parameter is has to be passed as part of this deferral request. And so like in my implementation with the prison dodgeball, you are basically saying what state you want to go to, and then if it requires parameters, they have to also be passed, and that relies on the internally on the generics features of C#. So another thing that is sort of like a software engineering issue with finite state machines. I call it the inaction problem. And so if you have a finite state machine, say a state that makes a decision, but it doesn't actually perform any action itself, and then transitions to a state that is going to perform the action. Well, you've got this problem if you think about in terms of the update loop. So you have the update loop, it runs, whatever the current state is, it calls the update or the execute, whatever the name is for it. It calls the what's meant to occur for just a single tick for that state. It does its thing, and then say it stays in the same state. Well, then we'll wait for the loop to go around again, and it'll call execute again. And it just continues that process. So it's one state gets executed every tick. Now, if you have a transition, you would execute the state. It identifies a transition, and then that transition will be entered and executed the next frame, perhaps. And so that would mean that anytime there's a transition, nothing happens until the next frame. So this is especially a problem if you have a state that doesn't perform any action. If it's just acting like a function call, so you enter a state, it makes a decision, and then it immediately decides to enter a new state. So you've wasted a frame there, and that maybe that's not a big deal. That's just a fraction of a second, but that also means there's a period of time the agent is just not doing anything. And as your state machines get more complicated, you can run into long chains of that occurring. So you have to watch out for it. One thing that I like to implement, which is a little bit dangerous because you might create an infinite loop, but I think it is useful often enough to use it very sparingly. And that is when you identify a transition, there's an optional parameter to mark that transition as immediate. And that means that in the same frame, it will call enter. Well, it'll call exit for the current state. It'll call enter for the next state, and it'll call execute for the next state as well. And so that means that if you did have like a state that ended up having no action performed, it will at least the next state will quickly be called and be allowed to perform an action. Now, the danger here is, well, what if the next state does the same thing and it decides, well, I couldn't do anything. I'm going to call a transition also with an immediate execute. Now, the problem there is that we each update cycle in our game simulation, it needs to finish very quickly. We only have just a fraction of a second to do everything that needs to be done. And so if we keep executing code that never returns, of course, we're never going to get to the next frame where the game's just stuck, locked up. So you have to be very careful about allowing immediate transitions. You could impose some sort of safeguard, maybe like counting how many immediate transitions occurred and then just forcing one of them eventually to stop, just as a little safeguard. You might do some other sort of analysis to detect if a loop is possible, depending, like a static analysis type approach. But I don't have any problems with the infinite loops. I do, if I'm going to use this, it tends to be very sparingly. And also, I avoid ever writing a finite state machine state that just all it does is make a decision. It's far better to realize you've got that scenario, and instead of writing a state to make a decision for you that has no purpose other than like being a dispatch to other states, it's far better to just write a method that does this, and then other states can reuse that code through a method call to if they need like some sort of common logic to be performed. A method is called that returns what I need, and rather than sending off to a separate state to make the decision. So that is probably the most useful of this whole issue, is just to be aware that a state machine is meant to model um, actions that are performed by your agent. It's not just decisions that are being made. So make sure that each state has an associated action. Usually, when I run into this problem, it is related to like some exceptional case where I went into the state. There ended up being nothing I could do because something in the world changed, in the game world changed. Nothing that I could do in that state. And just for the sake of efficiency or performance, I want to immediately transition and execute a new state. Next up, debugging finite state machines. So there's some different strategies that we can use. So of course we can perform offline debugging, which is typical of lots of computer science and programming sort of tasks, logging verbosity levels and so on. So I'm sure you're all already familiar. We can also perform online or interactive debugging. And this is something that I think is especially important with finite state machines for video games. So having graphical representation of your AI state. And in fact, you can see this like in the prison dodgeball. I have text that's written above each of the agents to tell what the current state is. You might even add additional supplementary information according to each state, like print out some extra stuff. So I think that is really helpful because you can detect issues like getting flip-flopping back and forth between two states and never doing anything. You can see, well, exactly what the two states are. You can also maybe have some kind of interactive controls, either through pre-programmed key presses or a control panel, so that you can tweak the behavior or maybe force transitions to occur can be helpful. Creating little like test world type scenarios where you're can force the agent into situations or perhaps a like in Unity, you can also create play mode tests where you can instantiate a game world, maybe a little specialized dedicated game world where you isolate the scenario in a way that the agent, you can focus on debugging one part of the agent behavior. There's some other testing strategies that aren't really specific just to finite state machines, but I figured I'd mention them here. And so in AI, it is common to use what's called ablation testing. And this ablation just means like removing. So you remove a part temporarily. You don't want to like lose your code, but you disable some part of your agent and you can study it with that removed. So of course the removal process, you need to, the end result needs to be compilable code. But you see what parts of your finite state machine are critical. So you remove a few states and the accompanying transitions, and then you can see what the agent does in response to different conditions. And that can be useful for testing. It can be useful for making, say if you have like an enemy scenario where you have agents pitted against one another, it can be useful for the testing purposes that the opponent that your agent is facing is one where stuff has been removed or disabled. You can also do A/B testing. I find this useful. Like if I'm trying to make an agent that's better and better at something, I will often test against a previous version of the same code. So like say in the prison dodgeball, if I'm making a better opponent, then I want to certainly see improvement against my previous implementation. So if I was say implementing some new feature in my agent, I would pit that agent with the new feature against the old agent that didn't yet have that feature. And I would expect to see, after a number of runs, maybe a higher win percentage of the the new versus the old. So doing this sort of testing is useful, but how you got to watch out though, because you can sometimes it's sort of dig a hole for yourself where you've gone off on a tangent where you're specialized only in strategies against yourself and that aren't really applicable in a general case or the most likely scenario that you might run into. So it's good to have other implementations as well, just to kind of like a sanity check. Next up, I want to look at a scenario with a state machine for an agent that has behavior to perform related to, say, foraging and eating food, but there is this potential to be interrupted by a predator. And so you can see here that all these states that the agent could be in related to finding and eating food, they can all be interrupted by the predator. And so this is like a situation that we looked at previously with the wild card transition, where maybe we could simplify this with the wild card. But clearly, the introduction of the predator creates all this extra complexity with all these transitions and, of course, a new state. And so, in addition to like the wild card concept, which really there's only so far you can go with that and gain benefits from it. But an alternative, more powerful approach is to introduce hierarchical structure. And so we could consider how would the previous state machine look if we were addressing the design of the state machine with this hierarchy. So we could have, say, a high-level strategy for finding food with a very simple state machine. And then we could think about entering and exiting that high-level strategy based on different transition requirements. So, for instance, the predator, now we don't have to think about the predator transition from every one of the smaller or the lower level states. Instead, we only have to think about in terms of transitioning to or from this high level strategy. And so you can see that there's this big potential gain here. And you can start to get some idea of more capable implementation. There's more that we could do with a hierarchy as compared to just the one-off strategy with the wild card. So the wild card is like we only have one level of depth that can be applied, but we might be able to divide and subdivide as appropriate to arbitrary depth, mixing and matching lots of high-level behaviors into more complicated behaviors. And that's clearly something that the wildcard solution alone could not solve. So we can generalize this scenario that we just saw with the prey, that we can refer to as the alarm state problem. And so the alarm state problem, basically, it is any sort of event that can occur in your game world that can interrupt at any point whatever activity that the agent is performing. So another scenario we can consider is, say we have a cleaning robot like on a space station in our game. And it could have a very simple state machine related to picking up trash and disposing of it. So you can imagine this would be a very straightforward thing to implement. But the complexity can easily snowball as soon as we start to introduce alarm states. So one that we might encounter with the cleaning robot is that it could run low on power. And if it runs low on power, well, that could happen at any time, meaning any of the states that it could be in. So we have all these transitions where we would maybe desire some kind of wild card um, way of isolating that alarm state. Um, and so in the hierarchical approach, we could just have a cleanup, high level cleanup strategy that is a little self contained state machine. And then we could just say, well, there's a transition to and from the cleanup state related to getting power. And so that's a pretty simple concept. We could even now introduce other alarm states. So maybe there's something related to get power. Maybe there's another if space pirates come on board the space station, then maybe the robot needs to go hide. We'd have other alarm states for other things, and be fairly straightforward. Now that could all be potentially addressed by the wild card as previously discussed. But we start to also have complexity introduced if we think about, well, what if certain low-level states within a high-level strategy have transitions, and those transitions go out of the scope of the current behavior. So, for instance, search within the search state within the cleanup strategy for the robot, there could be a transition if there's no trash found, that, well, this would be a good time to go opportunistically have the robot charge, even if it's not on the lowest power threshold that normally would trigger this. Go top off the battery instead. So that would be a more efficient behavior, but it adds a bit of complexity here to our state machine. Now, this can further be compounded by what if we wanted to build an even higher level behavior that encapsulates other high level behaviors. So we have like this nesting in our hierarchy. So hierarchical finite state machine is equivalent to regular finite state machines, but we're adding this recursive multi-level evaluation. So it makes things a lot easier to think about encapsulation and abstract software design sort of strategy. So each of our high-level, like hierarchical states, they're still going to have the same features that we've seen before of states, like in an object-oriented design where we have our enter, update, and exit. And this will exist at for every state at every level, whether it's a high level state or like at the very lowest level. They'll all have this sort of pattern. But how do we deal with that scenario we saw before, with a transition from a lower state to another? And so it gets really tricky to implement the engine, the actual evaluation of the finite state machine that would be built in this way. So changes in the world state are our input vocabulary that'll be used for transitions at any level in the hierarchy. So we still have the same events that are going to be triggering transitions. And so if you have, say, a low level state and it does not handle a potential transition event, then it will likely be handled, say, at a higher level. So you just you can address that with the evaluation at the higher level, and so that's basically allowing the designer of the finite state machine to avoid duplicating transitions. So it's got this wild card sort of feature to it to do exactly that. You don't have to deal with all those transitions at the lower level. You just let the higher level catch it and deal with it. So we'll again still have this issue of the dealing with the transition from the lower level states out of the bounds of the what it's encapsulated in. So what you end up with is a recursive algorithm that is really pretty tricky to follow. I'm not going to try to fully explain it here, and you're not expected to memorize it. But I do encourage you to check it out in Millington's Game AI book. He has a very detailed description along with pseudocode, very detailed pseudocode that explains it. And I think it's just one of those things that, in terms of the design, it probably took a lot of tweaking and really thinking carefully about how this would work in order to get it to evaluate just right. But some of the key features of the algorithm. So the highest level transitions are always honored, and they'll bypass the lower level update. So you won't even update the lower level states if the higher level transition occurs. And then the hierarchical states, they remember what child state they are in. So this is one really nice feature that you get out of this particular hierarchical implementation. And that is when you go back to a high level state, it remembers where it was before. So it's got this memory to it. And so that can be a really great feature when you do have, like, say, sequences that are like multiple steps in a plan that are being executed. Say if you go back to the guy chopping wood, if he's interrupted, then say by an ogre, then assuming he survives the encounter, maybe rescued by some knights, he can go back to work and remember where he was before and continue the activity. Next up, all the actions, whether they're associated with entry into a state or update or exit, all of them are deferred. And so all of these different, whatever the end result execution is, it's noted but not actually done yet. So it's just noted that this needs to happen. So those are all collated in the order of the recursive evaluation, and only executed once once the entire hierarchy has been evaluated. And so this has to be deferred because the act of parsing, like, you don't know yet whether you're going to have a transition at a higher level state as you're parsing. So you have to defer the execution so that you can figure this all out. And then furthermore, transitions that change levels in the hierarchy are deferred when transitioning up, and then recursively chained when going down. And so this is one of the really tricky things that probably isn't going to make any sense until you actually walk through the examples in the Millington book. And so this is probably one of the more complicated concepts that is in the Millington book that it goes into in detail. And so I would say that if you were, say, building a production game where you're using finite state machines, that the hierarchical approach would probably be worth the effort. But for smaller design tasks, like maybe where you're just making a game as a hobbyist, or a little just small self-contained problem, probably you don't need the hierarchical approach. But if you expected a game to develop a lot of complexity, it would probably be worth the effort. One other thing I wanted to mention about the hierarchical finite state machines is that, but going back to the Mealy and Moore designs, you can get something that is somewhat hierarchical from Mealy, just one level deep, in that when you have those loopback transitions in the same state, those can describe a number of different different behaviors. So it's almost like by having all these different loopbacks, you can kind of create a state machine within a state machine in that fashion. Um, so that might be a reason why one would want to consider it over Moore. But with the Moore strategy, I personally find that the global transition state is pretty powerful. And in fact, rather than just using the global transition state exclusively for transitions, like say in my prison dodgeball state machine. So that state is actually not only is it a wildcard transition manager, but it's also a simultaneous state. So you can think of it as a bit like a hierarchy, like an encapsulating hierarchical state, because there's nothing to stop you from making other calls to with side effects. You can do things within the global state that have side effects. Now you have to be very cautious about doing so, because these are going to be layered on top of the other, whatever the current state is. It coexists and is on top of effectively in parallel the execution. So yeah, you do have to be careful there, but I found it useful to perform actions within the global state. And so again, for simple things like say the complexity of the dodgeball opponent, you don't really need the hierarchical approach for that. There's quite a bit you can accomplish without just the global state is sufficient, I think. Now, another common strategy for adding a little bit more capability to the finite state machine is to use a stack. And so with the stack, the idea is that states are pushed and popped. And so you don't have transitions the same way. I mean, it's effectively the same, but the transitions involve stack operations. So pushing a new state onto the stack can be like a transition, or a there's like an atomic operation that you'll often see where it's a pop and immediate push. So you can say, all right, remove the me. If you, from the perspective, if you are a state, you can say remove me and replace me with this new state. And so that is the shown on the animated figure here on the left, the pop itself and push new. Or you can just pop itself and return to the previous state. So that's a bit like deferring to, in a hierarchical sense, when one state finishes, it goes back to the calling state, and so that allows for this hierarchical sort of management. And if say you have a high level state that has more low level states to maintain, then it will push new. So it's got these kind of interesting features that can allow fairly complicated behavior similar to the hierarchical state machine. And then the implementation is arguably easier. But you could also say that while the implementation might be easier, you kind of open up more opportunities to shoot yourself in the foot. There are ways that things can go badly pretty quickly with a state machine stack. So we've got basically like a memory leak potential. So imagine you just keep you mess up somehow, and you end up in a vicious cycle of keep pushing onto the stack. Like somewhere your logic was wrong. So of course you're going to run out of memory if you do that. So Things you can do that'll help with the problem. The pop and push new is certainly something that can help because it minimizes the height that the stack could ever grow. And you may need some other sorts of restrictions that are imposed on the use of the stack. So you might have a rule that perhaps enforced by like an assertion or just throw an exception or an error of some sort would be you can't have two of the same state on the stack at the same time, or maybe you impose a restriction that's based on two states from the same hierarchy family. So it would really kind of depend on your particular needs, how you might go about implementing this, and whether it's just a soft warning or some other sort of enforcement. You could also potentially have a requirement that a pop and push new is always required for when states change among sibling states. So if like one sibling state goes to another, so like in the hierarchical sense, if one state within the same hierarchy is transitioning to a sibling state. So yeah, there's a few different things that we might do to try to make it less likely that you introduce horrible bugs with your state machine. All right, so next up, I want to show. So it's actually an Xbox 360 commercial. It was a well-received commercial, just because it's kind of funny and entertaining. But there's a little thing that happens right at the end I want you to look out for with the cab driver. So I'll let it play here.
Where's that tiger? Where's that tiger? There's that tiger. Where's that tiger?
Okay, so in the commercial, it was very much like you would see like in a video game, but of course you had all the human actors just acting out as if it was like what would happen in a game. But then the part with the cab driver, you'll notice that he was in the middle of a phone call, so he's performing a behavior that couldn't be interrupted. He couldn't transition to the appropriate response of pretending like he had been shot. And so that is not unlike the very sort of problems that you can run into with any sort of decision-making framework. So not just the problem with finite state machines. This is really more of a fundamental problem in games, is that you might be modeling complex behavior, perhaps through an animation system. And then you've got, separate from that, you've got decision-making going on, and there's decisions being made that perhaps can't be made or can't be acted upon because there are dependencies with other systems or subsystems of the game. And one of the most common situations is animation and the time constraints imposed by animation. Like an animation, it takes time to play and complete and so on. And so that restricts when and how say like a finite state machine can react. And so we've got this tight coupling issue with say animation system, but it's not just the animation system. There can be other constraints as well that are dictated by other parts of the game. And so as say in the hierarchical finite state machine, so if you say have an interruption of a behavior, which might be a low level behavior that's being executed, but you have a high level interruption, there could be cleanup associated with that interruption. So you can't just say, oh, well, it's a high level decision. I'm going to transition now. Well, the low level stuff that's happening right now, it could be tightly coupled with the animation system or other parts of the game. So a lot of complexity can be behind the scenes related to what might seem trivialized in at least how we've presented things so far. So you might have strategies of whatever behavior was being performed, say like an animation, we might need to, part of the cleanup would be to transition to a neutral state. And so that might be, say, standing in place, the character would stand in place. But that could be awkward, like if you have a character that's seated and say something happens and they need to stand up in order for the whatever to happen, rather, and part of it's like, is it implemented or not? Maybe it's just an issue of lack of resources. As a game developer, you can't build say animations or graphics for every possible scenario. Now, some of these sorts of things, like related animation, you can deal with maybe through blending or interpolating animations, or perhaps using physics-based simulation. So maybe you turn off animation for a bit. So if it's like violence related, this is often actually a good strategy. Say a character's in the middle of doing something, a complicated animation. You don't have to wait till the end of the animation before they can finally be killed. You can just immediately pause the animation, turn off the animation system actually, and then switch to a ragdoll simulation. So where it's physically simulated. But that's kind of a special case. A lot of games do involve death and so on, but if you have a game that's maybe something a little bit more atypical of violent sort of gameplay, then you're not just going to be able to quickly transition to ragdoll all the time. You're probably going to have to wait or have something a little bit more sophisticated to deal with, like, well, when the new decisions are made by your finite state machine, how you deal with it. So, like, what if you have an agent that is interacting with an artifact, for instance? So something comes up and they're currently holding a live grenade. If you're going to transition out of the current state, which was maybe to throw the grenade, to something new, like run away, well, they need to still get rid of that grenade before they start running away. So those are the sorts of problems that you can run into. Again, this doesn't apply just to finite state machines. It can come up with other reactive decision-making scenarios as well. So the takeaway here is that you're probably going to need some additional support for transitions with like a time delay, like multi-frame sort of thing, where your decision-making framework, like your state machine, will have identified that it wants to do a transition, but there's like a synchronization that occurs with other resources in the game. So maybe it's deferred, or it blocks the transition. The transition's not allowed to occur right now. In fact, we'll see that in behavior trees. That's formalized with behavior trees in the form of a semaphore. So if a particular behavior tree transition is not possible, it's blocked. So you might need similar things implemented for whether it's decision trees or finite state machines or rule-based systems. you maybe need similar kind of synchronization. Um, like maybe an attack animation needs to finish before you have your transition, so you have some sort of delay imposed, or maybe like an agent, if the agent's going to enter a town and enter a conversation with a friendly NPC, the sword needs to be sheathed. So, in fact, you see this pretty commonly, like Legend of Zelda. Link always puts the sword away before he talks or interacts with an NPC. So, so that's definitely something that you in a real game, this sort of thing has to be considered. I mentioned before that we might want to try to compensate for the highly predictable nature of state machine behavior in agents. And so we could add probabilistic transitions. So this is just extra criteria as part of a transition. So there is some sort of condition for our transition, like enemy being in sight. But on top of that, we would also have a random number check. So previously we focused on the frame rate issue, but there's some other things we can consider with this probabilistic approach, and that's we can do some interesting things. We can have different personalities for our agents. And in fact, this is really a powerful feature for finite state machines, but it can also be applied to other reactive decision making. And that is, so the threshold, whatever say we're generating a random number between 0 and 1, we might have a threshold of some amount for, say, a very aggressive agent. So you have to roll above 50 or 0.5 to decide to attack, perhaps. But a very passive agent, you might have to roll above a 0.95. So you only have that 5% chance of attack with the passive agent. And so we have a whole vector of features, like a feature vector, and the vector is full of thresholds associated with those features. So different behaviors like attack, evade, whatever the different activities are. And so the nice thing here is we have one state machine implementation, and the single state machine implementation can be applied to multiple agents. So, based on capabilities, based on personalities. So you're only debugging this one state machine. It's the only thing that's changing are the thresholds for the likelihood of different things to occur. Of course, we could use 0 or 100% thresholds as well. So this would be like maybe, say, if you have an agent that can, one that can jump and one that cannot jump, you could just treat it as like an on or an off. Of course, you would skip over doing the random number generation if you're doing that. But yeah, so having this configurability that includes probabilistic as well as features of or capabilities of the agents can be very powerful. In fact, these can even be dynamic within the same agent. An agent that has been damaged, say low health, you could have a very aggressive agent that becomes very passive when they're badly hurt. So again, there's a lot less debugging to do. You still have all the same states and state transitions. You're just changing the likelihood of entering and exiting the states. So it'd look like, in a very simple case, it'd look something like this. So we have an opportunity that, say an agent that's currently firing at the enemy. If the enemy gets too close, we might have some probability of running out of range and trying to get far enough again to start firing. So maybe it's an archer. So the archer would try to quickly get far enough away to shoot arrows again. Or it might decide the agent would have a 50% chance of deciding to just run away completely, like abandon the battle. And yeah, so it's very straightforward to implement. It's just you're adding a little bit of extra specialized conditional logic that includes a built-in random number generation. And again, you will want to compensate for the frequency of the updates if that is variable in your game, which it very likely would be. Now in Unity, you might have it in a fixed update cycle, which is meant to be a guaranteed update cycle. But quite often, in implementing a game, you would need to be able to deal with variations there. And just to wrap things up, there's other aspects that you could use the framework of a probabilistic state machine for. So, say for perception, you can have probability of having seen or noticed something, like maybe there's a character hiding in the shadows, like the human player hiding in the shadows. If there's movement there, there's like a Dungeons and Dragons dice roll. Like, what's the chance that it was perceived? So it can be applied to all sorts of things, and this can add a lot of capability to the finite state machine. All right, so that wraps up our look at finite state machines. They're, of course, very capable, very popular, but they are limited in that it's a reactive decision making. So there's no learning taking place. But it works pretty well. There's this danger of combinatorial explosion, in which case, if you're getting into situations where you have a particularly high amount of complexity that is being formed necessarily for whatever your agent needs to do, you might want to switch to a hierarchical approach, or maybe just consider a much more capable strategy altogether. Hello, in this lecture we are going to explore behavior trees. So behavior trees are a form of reactive decision making. They're fairly similar to finite state machines, but you kind of have to flip around the way you think, and the way that they're structured is different enough that the way in which you design them, I would say it feels very different, the approach that you take in building one, but what you gain in the learning curve of a behavior tree is a big increase in flexibility. So we might think in terms of reusability of a behavior tree, or especially parts of a behavior tree. And so there's potentially big gains as compared to finite state machines. And so behavior trees have become very popular to use in games, especially in the last few years. They've begun to, I would say, replace finite state machines in terms of popularity. So we'll start off by looking at the structure of a behavior tree. So again, it does have aspects that are similar to state machines in that you often have a visualization that looks very similar. You have states or what look like states in the flowchart, so that you have these blocks, and some of them, like the leaves, appear to be what you might find in a state machine representing a particular behavior. So the leaves in the tree are the behaviors, and that's also similar to decision trees as well. So a behavior tree ends up being much more declarative because of the way that the behaviors are linked together. So no longer do we have these context-specific transitions like in a finite state machine. Now we have these very structured nodes that perform logical sort of expressions of behavior. They have this Boolean-like characteristic, and so all the transitions end up being decoupled from the behaviors, whereas in a finite state machine, they're kind of unified together. And that has an impact on the reusability. So we'll revisit that. So we have this more declarative structure. The fact that we are forming a tree means that it's a more understandable or readable data structure as compared to a finite state machine, especially because we can have loops and all sorts of arbitrary connections up to, however the finite state machine gets designed. It doesn't necessarily lend itself well to reading off of a screen or a piece of paper. But with a behavior tree, we're imposing this structure, which means that it'll be really easy to read top down and left to right. So the key components are we have composite nodes, decorator nodes, and leaf nodes. And then each of these nodes can be in a state of success, failure, or running. And then also, I guess, uninitialized if a node has not been visited, which we'll see in a bit. So again, behavior trees, it's a simple reactive planning. There's really nothing different that we can do with a behavior tree as compared to any other sort of reactive planning paradigm. But it's just the way in which we organize information can make things more flexible, especially like in terms of reuse. So the behavior tree that you design for an agent, that specifies everything the agent can do, every contingency plan, any way in which the agent can respond is in the tree. So if unforeseen circumstances arise, if the agent doesn't have the plan built into the tree, it cannot react. That's true for all the reactive decision-making strategies. So again, the transitions are externalized from states, and that is in the form of the compositor and decorator nodes that we're able to realize this externalization of the transitions. So because we've decoupled the two, that is what enables the reuse, because we've got these behaviors that are realized or created, implemented in your code, that since they're not tied directly to transitions, makes it very easy to reuse them. If you think about a finite state machine, you would have to you go in and like anytime you find a state you want to reuse, you'd have to go in and edit, like strip out the transitions that you don't want, and then would need to re-implement those. So that's something that's easily avoided with behavior trees. So a lot of the magic of the transitions comes from the compositor nodes. And so these operate a bit like Boolean operations for the most part. So we have and or operations, and they're called, for and it's called a sequence composite node, and an or is a selector composite node. And then there's random variations of these. So you could have a random sequence or a random selector. That's useful for when later on we might consider making a non-deterministic agent from a behavior tree. We can just introduce a shuffling of whatever the conditions are in the ands or ors. Now these are not, say, two Boolean comparisons. These can be evaluated in like a list form. Is typical for a behavior tree. So if you have the sequence, it's A and B and C and D and so on. As many conditions as you add. So you don't have to add more than one sequence node. It just has some arbitrary number of children. So this is a node in the an intermediate position in the tree. and it can have an arbitrary number of children. So it's not like a binary tree, the way that we might have for say a decision tree. It's an in-array tree. Same with selectors. Now, the real power of the behavior tree relies on short-circuiting Boolean logic. So that means if we are evaluating a sequence, so A and B and C, if A fails, like returns false, there's no sense in evaluating B, C, and D as well. We can just immediately say that that sequence itself failed because one of its children failed. So it avoids evaluating further down. And as we'll see, that means avoids executing behaviors that are pointless to execute. And selector works similarly. It's an OR. So as soon as one node evaluates to true, there's no point in further evaluating. And so you can imagine if you are coming up with a recipe for an agent for behaviors, there's some cases when you have sequences of things to accomplish. Like you first have to put the ingredients in the blender before you turn the blender on, or the key in the door and unlock it before you open the door. And so there's all sorts of sequences, and of course these can be hierarchical as well. And in the case of the selector, this is good for when maybe an agent is aware of a number of different candidate strategies that might work. You might order them in terms of some kind of priority, like don't do the high energy attempt before you try the low energy attempt. So for instance, if you're trying to get into a house, you would try the door first before you climb to the roof and go in the chimney. So you can sort of introduce priority just in terms of the ordering, and you know that it'll short circuit the first of the behaviors that is effective will return true, and there's no point in trying further any other alternative strategies. So each of these nodes returns success or failure, and that'll be based on the return value of the children. So you have a lot of return values that get bubbled up the tree whenever the tree is evaluated, which happens like every update cycle for whatever your AI update cycle is. And so generally with a compositor node, the values that are being bubbled up, they originated from a behavior or leaf node in the tree. Now we also have decorators, and these end up being very powerful, as you will find if you try to design your own behavior tree or implement your own behavior tree. So a decorator, unlike the composite nodes, will always have one child, and this works by changing or filtering the return value of the child. And so this can be used for control logic, maybe repeating attempts of a behavior such that it could, maybe a child would fail several times before it finally works. So such as, say, shooting at an enemy. You might want to continue a behavior of shooting at the enemy, and it might fail, but you don't want that single shot to cause the whole strategy to be abandoned. So you'd have like a repeat node, and sometimes you can have a repeat until a count or a time. There's many variations that you'll find in different specific behavior tree APIs. You will also see some that change the return value. So you might perform a strategy and you don't care whether it succeeds or fails. It's maybe something that's just, Nice if your agent does it, and if it is successful, that's great. But if it's not successful, that means don't interrupt say a sequence. You don't want the sequence to be interrupted because of a failure on a non-critical behavior element. And so in that case, you can have a succeeder. And so this filters any values that are being bubbled up through it to force it to always return true. And that avoids the implication of a false being bubbled up, or a failure being bubbled up, because it would say, in a case of a sequence, it would short circuit the sequence and it would fail, and you don't want that to happen. So these tend to be very useful for especially when you have some sort of recipe, like a plan that has multiple steps. And occasionally you'll have steps that could fail, but it doesn't necessarily mean that the whole plan is spoiled. So you just can say, like, return true. So yeah, very useful to use decorators as well in conjunction with the compositors. And of course, there's the leaves, and these are the actual behaviors. So the terminal nodes in your behavior tree are associated with behaviors. They will often, like as part of a behavior tree API, you will often have common game logic that's already implemented for you. So say if you have path planning or maybe steering behavior type movement, those you'll often find already in the pre-implemented behaviors, but certainly you can always implement your own. So there's often you'll find object-oriented approach, an interface perhaps that you can implement, and there's some key methods that need to be implemented, an initialization, and then a process or an update sort of callback. And what this does is it performs a very brief calculation that is meant for a game loop update. Often, as you might expect in a game, behaviors aren't immediately resolved in a single call, and that's because you have behaviors that can take many update cycles to complete. Say a steering behavior may be following a path that was returned from a path search. So that could take some number of seconds before the agent finally gets to the destination. So in that case, when you parse through a tree and land on a behavior, most likely what you're going to have after you initialize and start the call is that it'll make some little incremental calculation, say like steering, and then the physics simulation or the character movement simulation will run just briefly for that little moment. And of course, it's not going to be done yet, so the tree can't make further progress yet. So what happens is the update will return processing. So it's like one of three values. It'd be like success, failure, or processing. And so if it says processing, that means next time, the next update loop, the next time the AI updates, we want to have that same node revisited because it's not done yet. So as the parsing of the tree occurs, each node will remember what child was being evaluated, and so it'll just very quickly land back on whatever the behavior was before that wasn't done processing. And it will get another opportunity to update, and it'll continue on. It'll probably go for many frames, and then finally, let's say if it was following a path, if it gets there, it will return success. Otherwise, it would return fail. And so then that gets bubbled up to the parent, and that parent might be a decorator or a compositor, and then that would impact the logic, possibly with a compositor triggering short-circuiting to break out and return a true or false, or maybe all of the children have been exhausted. So say in a sequence. It's the last node to be evaluated in the sequence, so you have all true. So therefore, that compositor would then bubble up true. So yeah, each node has one action per tick, and generally they're all going to just be making their recursive call down to you get to the currently active child, and so that's the only one that actually is going to do anything. And then it bubbles up the most of the time it's going to bubble up processing. It's only when a certain behavior completes that you're going to change the current path through the tree. And so I think this would be a good time to look at an example, because it's probably kind of hard to think of this in an abstract sense. So this is like the canonical example for a behavior tree, a burglar trying to break into a house. This particular scenario fits really well, because the burglar has to have, say, a number of different strategies in order to get into any given house. Some might have the front door unlocked. Some the door might be locked. It might be reinforced or not. There could be an open window. There could be a chimney, and all these different possibilities. So in that case, we need to have different strategies, basically different contingencies for the ways in which the house might be secured. And so our agent could represent a number of plans and contingencies with a behavior tree. And so this particular example has two key subtrees. On the left, we have one that deals with a sequence of behaviors to get through a door. And on the right, we have a sequence of behaviors dealing with getting through a window. And so you'll notice that if we assume this is read top down, left to right, we have the door strategy on the left. And I think that makes sense that in terms of the amount of effort that the burglar would have to put forth towards getting into the house. And this is, door is easier to deal with than climbing through a window and so on. So let's consider what exactly would happen. So the burglar, say, arrives at the house. Now they're trying to get in. We have a selector. So a selector is like an OR operation. So conceptually, we can think about this as if the strategy in the first child, which is to the left, and that's dealing with the door, if that overall ends up being successful, then there's no point in breaking into the window with using the strategy to the right. However, if the door strategy fails, then we'll continue to try other things. So we can have the next subtree that deals with the window, and hopefully that would be successful. And we could, kind of skipping ahead, we could even extend this pretty easily if we wanted to add breaking in through the chimney. So we might have a whole plan that deals with, well, if you have a ladder or maybe like a gutter that the agent can climb up. If they can get to the roof, then can they get through the chimney? And so we'd have some pattern of behavior represented in a third subtree, and we could add more if we could come up with other ideas. But we'll start with the left subtree here. So when we go to the strategy for using the door, you'll see that there is a sequence that's involved. So one is walking to the door. The next is doing one of a number of things to get the door open. And then we'll revisit that. And then the third step in the sequence is to walk through the door. Fourth step is to close the door. If all four of those children branches can resolve to success, then that means that it was successful. The agent successfully was able to get through the door. No longer do we need to worry about going in through the window. So there's a short circuit at the root level selector, and the agent is in and can move on to the next thing, which would be bubbling up. So we could actually think of this entire tree shown here as really being a subtree of a even bigger tree. We're just focusing on this. And so that's a kind of a nice feature of behavior trees, is you can kind of zoom in and focus on some aspect of it. All right, so walk to door, that is a behavior. It would take some amount of time, so it would be returning, processing for a while. It would eventually bubble up a success. The sequence, that is the parent, would know at that point that it can move on to the next child. It was not short circuit canceled. So go on to the next child. And we're now in the selector. First try open door, which would be working in the case the door was accidentally left unlocked by the homeowner. That is like the easiest strategy to try. Probably likely to fail, but worth a shot. Low cost in terms of effort for the agent. Next up is the second child for the selector is a sequence, and this is involving unlocking the door and opening the door thereafter. So if the agent is able to unlock the door, perhaps has a key that they found previously, maybe they have a lock pick, something like that. If they're able to unlock the door, that would return true, and then we continue the sequence and then open the door. But we'll say that's likely to fail. So the unlocked door fails. We don't attempt to open the door in that case. So that bubble up to sequence. The sequence short circuit cancels. So it knows, that node now knows it's returning failure, bubbles up to the selector. Selector still has a chance that it could work. So it's had two failures so far. So the final strategy to use is the highest energy of the three, being the smashing the door. So break down the door. That could succeed or fail. In this case, we'll say that it's not a heavily reinforced door, so there's a success. Go to the selector. It is able to return success as well, bubbles up to the sequence. Well, the sequence is not done yet. It's had two successes so far. Third will be walk through door. Of course, this is very likely to succeed because the door is no longer closed. We've broken through the frame, so the door swings open with the broken door frame, and the agent can now walk through. And then there's closed door. Now there's one interesting thing here that is not reflected in this particular behavior tree, and it's the closed door. Now, if you think about in terms of the purpose of the behavior that the agent is performing, they're just trying to get into the house. Closing the door might be nice so that it doesn't bring attention to the home. Say maybe police on patrol, they look to a house and they see a door wide open. That would probably raise concern. Now, if the door has been smashed, though, maybe it won't shut anymore. So the closed door strategy is something that I would say is advantageous to the agent to perform, but it's not critical to the task of going into the home. They might change their strategy. Maybe they spend a lot less time in the home because there's this, evidence and the loud noise they made and so on. Maybe they only spend a couple minutes to very quickly go in, steal whatever they're going to do. But maybe that would have taken a lot longer time had they not. But in any case, I could argue that closing door is not critical to the strategy. And so what's not shown here, and what would probably be nice to add, is a decorator in the form of a succeeder. And that would be put in line between the currently the parent of closed door behavior, which is the sequence. So in between the sequence and the closed door, we could add a decorator node called a succeeder. And so what that would mean is whether the closed door succeeds or fails doesn't matter. If it's anything other than processing, it will be converted to success. But if it is processing, the succeeder does need to return processing. So you don't want to return success for all possible return types. It's only the terminal return types that you would change it to success. So processing bubbles through normally through a succeeder decorator, but if you get a failure, it gets flipped to success, and a success is passed through as success. So I would argue here that that is needed in order for this to be a more flexible strategy. And so you can do a similar sort of thing. Maybe we could say that for the right side, we could say that the smash door fails because the door is reinforced. And so if that had happened, we would instead have had the selector would have exhausted all possibilities. The parent of smash door selector would have exhausted all possibilities, would then go bubble up to the sequence. The sequence now can short circuit fail because it knows that it was unable to have success returned for all 4 children. That bubbles up to the root level selector. And now we can immediately jump to the strategy dealing with entering the window. And so you can look at that. I think it's also worthwhile, in addition to this example, just consider other types of scenarios that you might have in gameplay. One thing that's not really shown here, because this is kind of like a little isolated strategy for just a small part of what an agent would do. But you easily get into a situation where you're going to need control logic, like looping, for instance. So you would have decorators that would just keep repeating something over and over. And there's also a few other things that you quickly will run into that you might need that we're going to cover here in a bit. So yeah, we'll revisit some of the issues that come up when you're dealing with behavior trees, such as like being able to store something or like parameterize, like what are some parameters that you might need to identify in one node and then send on to another node. So we'll look at that in a bit here. But yeah, so I think this example especially gives a good introduction to the way that you think about structuring behaviors in a behavior tree. So I mentioned before that the strict ordering is very predictable with a behavior tree. Same sort of fundamental problem that other reactive planning or decision-making strategies have. And so we can introduce a random, or the ability to randomize the behaviors by manipulating how the selector and sequence compositing nodes work. And really this just works on shuffling the order. And then we'll want to have of course, some persistence there. So when the nodes first visited, initialized, we would do the shuffle and preserve that across multiple parsing of the tree until we come back to the node again. So it's kind of a similar thing to what was discussed with decision trees. So when you're randomizing a decision tree, you want to kind of remember the whatever random decision was made. You got to preserve that until you leave that parsing direction, like leave that node and then come back again, and then that would trigger reinitializing. So it's the same sort of thing with the behavior tree. So pretty straightforward logic. It's just instead of remembering a binary branch like in the decision tree, we are remembering our shuffling and resetting it when we leave and come back. All right, another issue that comes up, and this is sort of related to the issue of, so we've got this abstract decision making that's taking place, and it's decoupled from game logic. And if we don't have that coupling, and this was covered in the in the finite state machine lecture when we looked at like the Xbox 360 commercial where there was the cab driver that was interrupted. So you had this like disconnect between the expected behavior based on the decisions being made and the state of the game. And so this is dealt with in behavior trees in the form of semaphore nodes. And so the semaphores is like a way to keep track of resource use and lock access to the resource while something is being used and then return it. A common scenario would be like a path finding. You might have some dedicated threads for performing, say, like an A-star search for agents. If you have a lot of agents, they will actually make requests for this limited resource. So like one of the small number of threads for path finding calculation would be assigned upon request to an agent. And so the way that you build this into a behavior tree is with this semaphore. And so the semaphore node allows external resources external to the behavior tree. You can lock access to it. So that could be like a pathfinding system. It could also be animation system. So if you have a behavior that is tied to an animation completing, and maybe dealing with some of the issues that were previously discussed, like related to the spin-off discussion from the Xbox 360 example. So yeah, this is the behavior tree way of dealing with that. Now, another thing mentioned before, you might need to have one node that makes a decision, and the results of that decision need to be passed along to other nodes. And in order to maintain the flexibility of a behavior tree, we don't want to end up with any tight coupling, because that's going to limit the reuse of a behavior tree, and it defeats the key purpose of the behavior tree. So one strategy is that we can use a blackboard. And so a blackboard is just a flexible shared memory structure that can be used to read and write values. And so it's kind of like from a symbolic AI sort of strategy that you can define symbols that represent maybe information about what was observed from the world, and then that is used to synchronize across different behaviors in a fairly decoupled way. So one behavior doesn't have to know about another. All it needs to know about is the type of information that it cares about that may or may not show up in the blackboard. And so a common way that you might think about implementing this is with a key value pair in a dictionary. So in this example from the Millington book, we have a sequence, and so we have enemy visible. If that returns true, then we know to continue the sequence. Next up, we have a behavior that the only thing this behavior is doing is writing to the blackboard. And so it writes an enemy to the blackboard. And then the next branch, we go to a selector. And here we have some strategy involved in like strategic positioning relative to the enemy. Then, assuming that is successful, we will then move on to actually this is structured such that it'll always succeed. So whether or not it's able to get a more strategic advantage, it will continue. And you can see why this happens, because the selector, the final child in the selector, is always succeed. So that's like a variation of the decorator, but in this case, you might have a behavior that is effectively doing the same thing. we could easily switch this around such that there is a decorator inline instead. But yeah, so that is like an optional strategy that would just be nice to occur. But yeah, back to the blackboard, the final behavior is engage enemy. And so this relies on reading from the blackboard. And so if we had it like a dictionary, we could have a key of enemy. And if it doesn't find an enemy, then I would imagine that this behavior would fail if the blackboard didn't show it. So this can be effective. The blackboard facilitates this decoupled sort of approach. There's some things to watch out for. You might have stale data. If you're not careful in the naming of things, you might fill up the blackboard, especially if you had things like rather than just a single value like an ID for an enemy. If you had, say, like a list of enemies, you could perhaps have things kind of snowball. So you probably need some way to clean up the dictionary. Maybe additionally, you would need timestamps and things that get stale automatically expire. So there's a lot of little like peripheral issues that you do need to consider with a blackboard. But the key here is this decoupling and the fact that it supports something that's like having parameters passed to your behaviors and not we're avoiding cluttering up the structure of the behavior tree by approaching the sharing of information in this way. All right, so just to wrap up, so behavior trees, they've become very popular. I think you could argue they've begun to replace finite state machines. I believe Unreal has a first class implementation, like their own. It's not like a third party plugin, but it's actually part of the Unreal Engine for their AI control. It's been used in many commercial games like Halo 2, and it's got many of the features you find of like a hierarchical finite state machine, but also other planning sort of concepts. It works well with sequences of behaviors without a lot of extra tracking information like that you might need to do with some other decision-making strategies. They're really easy to design, especially if you have a solid library of predefined behaviors to the point that non-programmers can build these. They have this nice ability to understand and read them, just because the fact that it's a tree and there's no loops. They can easily be altered and reused parts of. You can even do this at runtime. I didn't cover this in the lecture, but you might be interested in Millington. They talk about some strategies for you basically using like a memory pointer type approach, so you can have agents that are sharing like different bits and pieces of trees, so you don't have redundant representation in memory for the game. They're just really easy to use. And yeah, they also tend to fail pretty gracefully. You're just like the agents will maybe be taken advantage of by the player, but they'll still tend to select something to do. You may occasionally run into cases where you get in a bit of a loop where the agent is everything they try fails, so it looks kind of like they're just wiggling back and forth between two possibilities, but never making any progress. But that's really the same sort of problem you can run into with a finite state machine. So I think given these benefits, and they're really no worse than any other reactive decision making, but do have many advantages that has led to their growth in popularity. Um, and so, yeah, if you're building a game, you might consider to use a behavior tree for implementing a reactive decision making strategy. Hello. In this lecture, we're going to explore the topic of fuzzy logic. So let's start off by considering the scenario of making a grilled cheese sandwich. So we have basically a recipe here of how to make our grilled cheese. So we've got 2 slices of bread, a description of slicing the bread medium thick, turning on the heat to a high setting, and then grilling the bread until golden brown, and so on. So now think about this recipe in terms of you following the instructions, and then in terms of how to automate this with computer technology to decide like how thick to slice the bread or how hot to heat up the griddle. So that suddenly becomes a lot more challenging when you think about, well, how would you make a computer recognize these sort of very subjective objectives for the different steps of making the grilled cheese sandwich. So this comes up a lot, especially when humans are involved. So we have this non-numeric linguistic expression, so a lot of subjectivity, vagueness. There are flexible interpretations, like these words may mean different things to different people. But I think probably most people could follow that recipe, and while each might get a slightly different grilled cheese sandwich, they'd all probably end up with something that's edible. So it's really a challenge from the perspective of conventional logic and applying logic and decision making to a computer. So this is where fuzzy logic comes in. We are going to embrace this sort of linguistic characteristic of describing decisions or processes, and we will be able to work with these kind of linguistic ways of defining the states of different objects, and be able to maybe interpolate between different strategies if there are, if you're kind of in the middle in a gray area between different possibilities. That's something else that fuzzy logic can deal with. And to do so, we're going to be working with, rather than absolute, like black and white, true or false, instead we'll have this sort of gradient between maybe 2 extremes in the case of like Boolean logic. So if we think about decision making that we've seen so far, like decision trees, rule-based systems, finite state machines, those all work with these very distinct transitions, like from selecting one rule or another, or transitioning from one state in a finite state machine to another. And if the behaviors that the agent exhibits according to those states are distinct, then we're going to have this very abrupt transition. So as soon as the transition completes in the finite state machine, we'll immediately have this entirely new behavior. And so that switch can be very unnatural, and it might be a bit extreme given the change in world state. We might prefer to have something more gradual in terms of um, switching from one state to the next, for instance. So, fuzzy logic is something that is has been popular over the years, but is largely dismissed by the academic community in AI, and that being largely because fuzzy logic is not motivated by um, probabilities or um, like a observed statistical pattern of the, say, in the case of a game, it would be like, what's the likelihood of certain things to happen? And a lot of fuzzy logic does have a bit of a feel of being like probability based, but um, it's actually not a probability. It's more of just a way to define different behaviors or strategies, which we'll see as we get into. So, fuzzy logic's been something that's really pretty popular in the game industry for decision making, but you will often see it sort of frowned upon in terms of academia. So with fuzzy logic, we have modeling of imprecise concepts and modeling of imprecise dependencies between these concepts. So it can be thought of as a superset of classical logic. But the end result is that we will have this fuzzy characteristic, as we will see. So we'll be introducing this concept of degree of membership, and this is a membership at, say, some particular variable to have a certain state. So, like, temperature could be cold or warm or hot, and rather than saying that this is all yes or all no, so like it's either hot or it's not, we could say, well, it's a little bit hot, for instance. So this degree of membership is a way of saying how much is that the case or true. So it's not going to be like a binary yes or no. And so we will also be defining fuzzy sets and fuzzy rules. And again, this is not going to be probability. So we could consider a thermostat example following along with this use of temperature. And so we're going to start with what we're going to call crisp values. And so we have some measurement. In this case, it is a temperature in degrees Fahrenheit. This could also be other sorts of measurements, maybe measurements in like a video game. It could be, say, a distance or an angle. So there's all sorts of different ways we can define what our crisp values are. And it doesn't need to be, I mean, it doesn't have to be a float. It could be a Boolean or categories like an enumeration. It could be integer values. So there's lots of possibilities for what we will use for our crisp values. But you can see here we have what we will later be calling membership functions on the figure here. We've got a graph of temperature, and then overlaid with the temperature scale, you see a kind of these trapezoidal sort of shapes for cold, warm, and hot. So those are our membership functions. And so we can think of this process of taking a crisp value and converting it to a membership in a fuzzy state. So depending on where the temperature is on the graph there, we can look above, for instance, and say, okay, well, it could either be a little bit warm or a little bit cold, perhaps, in the area where the two overlap. And we might have rules that work off of the conversion of the crisp values into those fuzzy input states. So here's a set of different rules we might have for thermostat control. So if the temperature is very cold, then fan speed is stopped. If temperature is cold, then fan speed is low, and so on. So we have these different fan speeds that result from different temperatures. Now, these rules, if you just read them as they are, they do have this subjective, very vague sort of presentation. I'm sure you can look at them and understand, and you could probably, like, if we put a person in charge of the fan speed just by feeling the temperature and saying, well, it's cold or warm or hot, that subjective sort of response, you would get appropriate behavior for the fan with the manual control. To make this work with a computer, that's a lot more challenging, because now we have to define what cold and warm and hot are within some ranges, and there's the rules as written don't suggest what to do if we have values that fall in between. Well, I can't decide if it's cold or warm. So what do we do in that sort of intermediate stage? You as a computer scientist probably can think of ways. Well, you could implement that in code, but then you're getting to the point where you're kind of moving away from these rules, and then say doing like some linear interpolation between different values, and so the end result is going to be code that is much more complicated than the easy to read rules that are presented here. So let's consider some different use cases at a high level when you might want to use fuzzy logic. So it can be a more direct way to represent expertise, because if you think about the typical expert in any field, they're probably not going to be computer scientists and not think in terms of procedural logic. Instead, they're going to define their processes in a linguistic form. It'll be much more declarative. And if you were to, say, consult with an expert to help you design an expert system, then there's going to be a challenge, because you're going to have to translate their understanding and way of describing their domain, translate that into code. But with fuzzy logic, we have this potential to sort of maintain the expertise in a form that the expert would still understand it. So even if you were writing, say, the rules we were looking at before, if you're writing those in code, you might be able to still maintain some readability. We could even go further and say build a scripting language, a declarative scripting language that works in the fuzzy logic framework. And maybe we could even have non-computer scientists build their own fuzzy logic solutions. So we have this ability to capture expertise. And if we consider other possibilities for how to, say, replicate expertise, well, one might be to use, say, a neural net and train it. And say we could observe the expert making lots and lots of decisions, and then we, with enough observation and enough training, we could perhaps replicate the expert. But this is really changing the requirements for the problem, for building the solution. Now we have to budget to collect all this data from the expert. It's not necessarily going to be possible. You might only be able to say talk with an expert for a brief amount of time, collect some information that would be basically the linguistic form of their own set of rules for solving a problem. So while something like a neural net may be more grounded in understanding probabilities, statistical likelihood of different scenarios occurring, fuzzy logic, it has this ability to very quickly design behaviors in a system that can transition smoothly from one strategy to the next. So you might select to use fuzzy logic, say in a video game, because you're not really looking for an optimal solution. That is something that's probably likely. Most agents in a game or other applications of AI in video game technology, you're not looking for optimality. You're instead looking to create entertaining behaviors or other AI-driven solutions. So just because fuzzy logic isn't grounded in theory that will allow to target the sort of optimality, doesn't mean that it can't serve a purpose. And so we can avoid the resources and the time, overall expense of say a solution that requires training or deep analysis of some observed behavior. And instead, we can just go straight into designing and think of it as more of like painting a picture. So you can make different choices, selections of behavior, tweak knobs and dials, and have a very quick turnaround to see, like, as you make these changes, are you arriving on something that's interesting and appropriate for your, say, agent behavior, for instance. And it ends up being very flexible. We can work on multiple variables without imposing any rigid structure on the decision making like we might with other decision making frameworks. Now, we will find out there are some limits to what you can do with fuzzy logic, and that's largely to do with the fact that you can kind of have a combinatorial explosion of all of the different possibilities that can arise in the rules that you define, the fuzzy rules. And so yeah, you can get to the point where it ends up not being very efficient. So fuzzy logic tends to work with smaller, more self-contained problems that don't have a large amount of variables or large number of things to consider. Now, in terms of the history of fuzzy logic, we won't get into a lot of the details, but it was first introduced by Lotfi Zeta from UC Berkeley. So he introduced the original concept of fuzzy logic, and I believe it met resistance in academia pretty much right from the beginning, but it did quickly gain traction in electronic control systems. So anything from high-speed trains to rice cookers, other sort of home appliances like a toaster, that sort of thing. And Japanese engineers were probably the first to really apply it to commercial applications, and it was quite popular approach, especially in 70s to 80s. And then we started to get in the 80s specialized hardware controllers. So you'd have tools to populate these tables of rules, and they could run rather efficiently. And a good bit of research continuing from the 80s into the 90s. So there's certainly a well-established engineering tradition of leveraging this fuzzy logic sort of concept, and you again also find the use of fuzzy logic in video games. So let's look at an example with a little golfing scenario where we have kind of similar vague description of strategies for different golf shots that, say, an agent might take in a golf game. So if the ball is far from the hole and the green is sloping gently downward from left to right, then hit the ball firmly and at an angle slightly to the left of the flag. So you can see here we have a number of different descriptions. Again, we've got these sort of subjective interpretations of different states that we might find certain variables in our game, like the distance the ball is from the hole, the slope of the surface the ball is on, and also there's this vagueness or subjectivity to the output. So how hard the ball is hit with a club, for instance, or the aim left to right relative to the direction of the flag or with the hole. So we might define some ranges for these subjective descriptions. Say for distance, we have close and medium. The ball is between 0 meters and 2 meters from the hole, we'll say, is the range for close. And then medium could be 2 to 5 meters, far as anything greater than 5 meters. But then what do you do when we get up near these transition points? So if the ball is at 4.99 meters away, we're going to have this abrupt transition, perhaps, if we go like a little bit over the 4.99 transition to 5 point something, then suddenly we've got the far whatever the strategy is associated with the far distance, which is probably like hitting the ball harder. So if we maintain that sort of abrupt transition, we might expect maybe the shot to be too short for medium, and then when we cross over that boundary for far, now the shot's too far. So we've got this abrupt kind of transition with maybe a more conventional sort of logic strategy. And we might come up with, say, an approach that where we write code to represent one of these rules with the very the natural language description with these subjective terms. So we could perhaps come up with an equivalent where we write the code to say process the wind speed, because we really want an absolute value for wind to make these comparisons. And then so we've got maybe a range defined for the minimum that the strong wind can be and the maximum, and also similar ranges for the distance. And then we will perform a linear interpolation, inverse interpolation from the input variables, and then a linear interpolation to define our output of our hit force and our angle. Now, as a programmer, you might be able to look at this code and pretty quickly figure out what it is, especially if you commonly use the linear interpolation code. But it's still very, I would argue, much easier to read the natural language sort of description of this particular strategy for driving the ball from the tee. And so that would be even probably that much more true for someone that is not a experienced programmer. So let's look at Boolean logic and how, say, we might define logical elements in like classic symbolic AI. So in symbolic AI, you're often working with predicates that return either true or false. So we can think in terms of the set membership. And these might be parameterized, like is armed. Say we have a combat video game. Is armed, where a parameter could be, say, a particular agent. So you could pass an agent to this function and it would return true or false. And this tells you a membership in a set. So there's the armed agent set, and then there's the injured set. So is injured, and we pass in an agent and know whether it's injured or not. And it's going to be true or false. So this is conventional logic, and it has that very sharp true or false characteristic to it. So very much not the fuzziness that we've been suggesting so far for fuzzy logic. Now with fuzzy sets, we have, instead of it just being all or nothing, true or false, we have this degree of membership. So our predicates, we will still have this ability to represent the predicate type logic, but instead for each set there'll be a degree of membership. And so this is a normalized value, like from 0 to 1, a floating point. So 0 to 1 inclusive. So perhaps our agent has a 0.7% membership in the is injured set. And now that doesn't mean a 70% chance of being injured. It just means a 0.7% normalized scale value membership, or degree of membership. So this this sort of is setting us up for this ability to consider not just like a single predicate, but we might have multiple ones, maybe even predicates that would otherwise be in disagreement. So for instance, you have these kind of weird situations where you have a degree of membership for an agent in the is healthy set simultaneous with is injured. So in conventional logic, you would expect these to be mutually exclusive. So you could only consider like one or the other in terms of making any kind of Boolean decision. But in fuzzy logic, this is perfectly acceptable that you have the non-zero degree of membership for both of these predicates. So when you do have multiple degrees of membership that are non-zero, and they're both applied to the same crisp value, so that whatever the observation of our world or game world. So if these sets are applied to, say, temperature, so if you had, say, cold and hot, and they're both non-zero, well, you would expect that whatever all of the different set memberships that there are, where these non-zero degrees of membership, you'd expect maybe the sum should be 1. And that is an appropriate assumption to make. However, in practice, that isn't something that absolutely has to be imposed, because you can take just a weighted average of all of the non-zero DOMs or degrees of membership for a particular variable and its set memberships. All right, so once we have this notion of degree of membership in the we'll call it a fuzzy set, and there can be so one particular variable like temperature, it can be maybe multiple sets like cold and warm and hot. So we have enough. We can start to think about, well, how exactly does this algorithm work for fuzzy logic? So there's 3 main steps here. We've got fuzzification, fuzzy rules, and defuzzification. So in the fuzzification step, this is where we take our crisp values. These come from, say, game world state, maybe like a distance or temperature, that sort of thing. So we're going to take those crisp values and we're going to apply them to a membership function. And this membership function will then allow us to determine the degree of membership for different fuzzy states for that given value or variable. Then we apply those all of the different activated states, fuzzy states, all of the activated states. We're going to apply those, so they're going to be in the antecedent. So each one is going to have a DOM or perhaps multiple ones, because we might have some binary logic there, like cold and I don't know, like the clothing you're wearing or your agent is wearing. So maybe deciding in terms of say the thermostat example. So you're going to use the degree of membership, which are those values that are somewhere between 0 and 1. So we're going to have some sort of logic in the antecedent. And then the consequent, that is the output. That's like, what's the decision made for in terms of a logic, a decision-making response by, say, the agent. So that is then passed to the defuzzification step. So the consequents are fired into a crisp value. And so this whole process, you're going to have multiple fuzzy rules that get activated because of the multiple activations or multiple fuzzy set memberships that are driven by these crisp values and the overlapping membership functions. So you kind of go in reverse at the end. You have defuzzification, and that's where you go the opposite way. So it's kind of like you are figuring out where membership functions intersect with the degree of membership going out. And so that gives you a crisp value going out the other way. Now, the defuzzification, as we'll see, ends up being a lot more tricky than the fuzzification. So for each of the different rules, for each antecedent, we're going to calculate the degree of membership for the input data. So again, those are going to be crisp values coming in, meaning the real world or the game world values, and then they're going to be converted into this kind of fuzzy state, and then at that point we can process the rules and then get to the point where we need to go back out again. So yeah, we're going to be calculating the rules whatever the conclusion is probably going to be involving multiple rules, and it's going to be based on the values in the previous step. And so those will be combined into a single conclusion that will come from the fuzzy set. So at that point, we have to do this defuzzification again that we'll look at look at in more details here in a second. So for any particular rule, any particular fuzzy rule, we're going to have taken various variables with crisp values. We're going to get degree of membership, and this will probably involve some Boolean-like logic, like an and or an or. And that's we're going to have to perform a special operation on the antecedent to combine the effects of all of the antecedent terms. And that's going to give us a mapping to the output fuzzy set, which will be defuzzified. And so, for instance, with an and type of Boolean operation, we have recall that these are going to be degrees of membership, so it's going to be like 0 to 1. So what would be the equivalent of like a Boolean operation, but now we have these normalized values? So in the case of like an and, what's often used is a minimum. So the minimum of the two values. And you might be wondering why we would use minimum, and we'll see here in a second. But once you do that, that gives us now a membership value that transitions to the output. So like if condition, then the consequent. So like in this example, if I am close to the corner and I am traveling fast, like driving a race car perhaps, then I should brake. So we can take the degree of membership for close to corner and the degree of membership for traveling quickly. So those will be two different values. We'll take the minimum of the two. And so that tells me the degree of membership in the should brake strategy. So that is a pretty straightforward sort of operation to get to the point that we have the degree of membership and the consequent that we will then use for the defuzzification. All right, so the fuzzification, I kind of quickly explained before, this involves a membership function. Now these functions this is really just a part of fuzzy logic design. There's not like a truth or a one way of doing things. Instead, it's just whatever is appropriate, and that often can vary just based on choice. Especially things like, where do the ranges begin and end, and so on. So if you look at these, the figure shown here in the slide, we've got a crisp value for health, and this is just a percentage of health like that your agent has in a game. And we've got two degree of membership functions defined. And so you can see that there's a range. So like in the case of hurt, somewhere I guess around from 0 to 10% of health. So very low health. That is 1, meaning fully a member of the hurt set. If you see a crisp health value from like 0 to 1, but then you see it tapers off. And so from about 10% maybe to 40% of health, we see a drop off of degree of membership. simultaneously, we've got a crossfade going with healthy. So healthy starts at 10 at with 0 degree of membership, but it quickly ramps up to a full 1.0 value that is around 40, and it stays there all the way to 100%. Now we can have other shapes that we might use, and again, we might think that we want at any given point how many ever fuzzy states or fuzzy membership functions overlap on this graph. The vertical line should always sum to 1, and that is something that is potentially desirable with fuzzy logic, but it's not something that is absolutely set in stone, again, because we can always do a weighted like a weighting to compensate for times when it doesn't add up to 1. All right, so these functions is completely something that's part of the design process. We just select things that are appropriate. If we are attempting to sum to 1, certain shapes and combinations will make that easier to work with. Like, for instance, a crossfade, you would want the start and end of your your fade up or fade in and your fade out, like you would want those to match. So if you have an API or tools for building fuzzy logic, you would probably have supports built in to make that easy and efficient to lay out and make adjustments, and have automatically, like, adjusting one of the membership functions would adjust the other to preserve that sum to 1 possibility. So these functions can have different shapes. So we have like the trapezoidal, so to be able to perform the crossfade, or triangular. Shoulders, which are basically when your trapezoids run to the end or to the limits of the range for the crisp values. Here's some other or visualizations of what we just talked about. So you can see the different shapes that might be possibilities. Now we might also have fuzzification of small sets and enumerated types. And so in these cases, we can just treat these as like lookup tables. So for a particular enumerated type, we just look up, and we will, from that lookup, we will get a degree of membership, a single degree of membership value. So here's an example showing, say, maybe we have opponents that in a kung fu game, and these opponents, you can just say observe in the game, they're each wearing a different belt or sash, and they have different colors, and so those colors tell, say, an agent how much fear to have. Maybe, and that fear would perhaps drive evasive or defensive behavior more than aggression. So this is how we could perhaps include this enumeration in fuzzy logic related to that. All right, so we briefly looked at how to deal with the equivalent of Boolean logic in our fuzzy logic, with the AND example, where we saw the use of the minimum of the two values. So if you have like A and B, how do you have the minimum? And so similarly, you have a fuzzy logic operation for OR. So in this case, we'll take the max, and then not of a particular variable would be 1 minus the value, and that would be, so 1 minus the degree of membership. You can also do what's called hedging. So you can say that something is very or fairly, and so we can apply an exponent to the degree of membership value, and that can kind of bend the curve one way or another. So that's something that doesn't even apply in Boolean logic, but it's something that's potential with fuzzy logic. So again, you might be wondering, well, why is it min and why is it max? Well, this next slide here, I think, will help a lot with this. So when you're considering the possibility that you have, say, A and B, you might have two membership functions, and those membership functions will overlap, and or they can overlap, and at the point where they overlap, that's the only place where the and can occur. So it's an intersection, and so it turns out that this intersection area can be defined by the minimum value, as you can see here at how it's depicted, because the minimum value is always going to be, whether it comes from the A side or the B side, it's always going to be less than or equal to, with applying the min operation, the less than or equal to. So it's going to capture the part where the overlap is. So one line of that part of the membership function is probably going to be, one or the other is going to be underneath the other. So A is under B or B is under A. And so the minimum defines that region. Now, in the case of OR, it doesn't matter if both are present, like intersection of the curve. We just need the overall silhouette of the intersection. So even if, say, A is at 0, if B is non-zero at that particular value, then you just go with B, whatever point it is in terms of degree of membership. So yeah, I think this can give you a good intuition on why you're using min and max for and or. Now, all that said, this is arbitrary. The implementation of these, I guess, Boolean equivalents for combining your fuzzy set. And you could, for instance, have other rules. And so, in fact, here are some that are effective and sometimes used in other approaches. So you can use multiplication for and that works well. But then, how do you define or? And so has to rely on a little trick to figure out what the equivalent should be if we're using multiplication for the and. So if you play around with I guess a Boolean definition for and, we can change things around and define in terms of a not. And so for a not, we're going to still use the 1 minus value, which makes sense to invert it to the opposite degree of membership. So that, in conjunction with or, you can see here the derivation of x or y for fuzzy logic. And so the end result is you get the x plus y minus x times y. And so, again, that is an alternate strategy. And I guess potentially you could come up with other approaches as well. And really, it's what is effective for building the fuzzy logic. So there's somewhat of an arbitrary aspect to the design of fuzzy logic, but you're really looking for consistency in terms of the interpretation. All right, so the defuzzification, I said before, this is a little bit trickier. And like dealing with those Boolean sort of operations like and or, I would say things get even more flexible and arbitrary in terms of, well, what does it mean to perform defuzzification? Now, in the case of the input variables, it was very straightforward because we'd have a value on the x scale, and so we could just draw a line vertically to figure out where it intersects with the degree of membership function, and then that y value, that is the degree of membership value for that particular set. But we're going the opposite way with defuzzification. So we're going to have a degree of membership which is along the y-axis. So now we're not guaranteed to only have that one intersection point. So we're going to be drawing a line across on the y-axis horizontally. So find a point on y, the degree of membership that we determined from the antecedent, and we need to figure out where that goes for defuzzifying to get a crisp output value. So here is a demonstration of the sort of challenge that we're working with here. So we've got these different degree of membership lines. We've maybe determined a degree of membership. It needs to be converted to a crisp value, which is on the x-axis. But we have this issue. So if you draw a line, we're going to get intersections possibly at more than one point. We might have only one point, but we also have to consider the fact that if there is, imagine you take a full slice through, you're going to have points on parts of your degree of membership curve for the output variable that are above that value. So we also have to consider any place where the curve is above the degree of membership value in question. We'll have a whole range of valid movement speeds for that degree of membership. And so that's where the complication comes in. You end up with this whole range of values. So what you generally end up doing is you take a slice through your degree of membership function. So if you have a trapezoid and you slice through some part of that trapezoid, you'll still end up with a trapezoid. It'll just be truncated a bit. It's going to be shorter. And you can consider well, how do you select a single crisp value from a whole range of valid values? And so this is again something that's arbitrary, that you can pick different strategies and just see how well they work, and maybe pick the one that's easiest to compute and that still gives good results empirically. So you might take, say, the minimum of the maximum. So let's say let's see if I can get my mouse cursor to show up here for you. All right, I think you can see it now. All right, so we've got, so here is where a degree of membership had lopped off the top of a degree of membership function for an output fuzzy value. So we could take the minimum of the maximum. So the maximum being the highest degree of membership after we've pruned away whatever was above. So the minimum is in the context of the x value. So the minimum crisp value of the maximum observed. Or you could take the average, which would be, you find that the average of the maximum. So you find all the places, the continuous area where the maximum occurred, and then you take the average of that. or bisector, or maximum of the maximum. Now, in this case, we've got I've skipped over a little bit here. We've got only one single degree of membership function that's been trimmed, but what you really end up with are multiple degree of membership functions that are all merged together. So all of the different fuzzy sets that are activated from your set of fuzzy rules, so any of them that have non-zero degree of membership, you actually merge all of those different degree of membership functions together, and wherever they've been cut off. So you do that intersection with the degree of membership. So the whatever degree of membership it is tells you the maximum allowed in the y direction, or that degree of membership direction, and then you merge them all. So you end up with these really weird shapes. And so that's going to be, say, for your different output strategies. So we might have maybe an agent that chooses between creeping, like for sneaking around, or walking, or running. So we might have, say, a degree of membership of a third for creep, a third for walk, and a third for run. We could use those as weights, and then apply those to a characteristic speed, that being the crisp value that we're aiming for as the agent's locomotion speed. So this characteristic speed would maybe be the average speed, or just something that's hard coded or configured, I guess, as part of the overall fuzzy logic system. So you'd have the weight of a third multiplied with whatever that desired creeping speed is, and then a third times the walk speed, and third times the run speed. And so that would give you a value. You may need to normalize the values if you haven't already guaranteed that the degrees of membership for the overlapping set, or the membership functions for the input variables, if those don't sum to 1. So there's different strategies we already looked at, but one that is probably the most robust but most computationally expensive is to use the center of gravity. So again, you're going to trim each of your membership functions for your output. You're going to trim those by determining, well, what was the degree of membership that came from the inputs after you applied that Boolean logic. So what's going to be the resulting output degree of membership? And then for each of those, we're going to trim them. So in this slide here, you can see the trimming or cropping has been applied. So we've got this degree of membership function, and whatever the degree of membership determined there. So we cut it off here, and then we join it with this degree of membership function's also been cropped, and then this one's been cropped. So if we can integrate under the sum of these cropped membership functions, we're going to see where the most area is, and then that will be the defuzzified value. All right. All right, next up, I've got an example of selecting a rocket launcher for attack in a game where an agent chooses maybe between different weapons. So this is from Buckland's Programming Game AI by Example book. And so it actually goes into a lot of detail on fuzzy logic solution that he uses in some of his examples. So let's say that we've got the following rules. So there's a bunch of rules that are related to when to use the rocket launcher. And so this is something that where uh, the rocket launcher's got not a lot of ammo, so it's kind of a precious commodity. And so we want our agent to make good decisions about using the rocket launcher, not waste ammo. So you can see there's rules like if the target is far and ammo loads, then desirable. And desirable in this case means it's desirable to use a rocket launcher for attack. If the target is far and ammo is okay, then undesirable. So that means that if you only have a little bit of rocket ammo currently and the target is far, well, it's not desirable to shoot long distance shots with this precious ammo. But then you can see other scenarios like if the target is close and ammo loads, then undesirable. Now that is because a rocket launcher has an explosion and we don't want the agent hurting themselves. So really there's this sweet spot of in the medium range. So if the target distance is medium and ammo loads, and very desirable, but it's also very desirable if the ammo is okay, and if ammo is low, it's just desirable. So we've got all these different possibilities. We've got for our input crisp value, that's going to be distance to target. And then also ammo status. So that's like the count of rockets that we have in inventory. And so we have different membership functions for target far, target medium, and target close. We have membership functions for the loads of ammo, okay ammo, and low ammo. And so those rules will overlap. And so as we evaluate all of these rules, that means that because of these overlapping membership functions, we're going to have non-zero values for multiple rules. So the way that we the way that we perform the fuzzification is we just go iterate through each rule, and then based on the memberships on the input that we're considering, we'll look at that crisp value on the graph and draw a line vertically from the crisp value, find where it intersects with the membership function, if at all. And then that point of intersection, the y height of that intersection, tells us the degree of membership for that particular fuzzy state. So then we'll be doing that for both the distance to target and the ammo status. And then we'll have the AND operation. So we'll probably be performing the min of the two. So the whatever the degree of membership is for like target far and ammo loads, for instance, we take the minimum of the two. That's going to tell us the degree of membership for the consequent side, so like desirable. And then what we're going to do is we're going to have to find all of the non-zero degree of membership on the consequent or the output side, or the decision side in this case. And then we'll have to pick an appropriate strategy. So that's depicted here. I've got not the complete example. If you happen to have Buckland's book, you can go through it completely. But so right below the rules, I show, I believe this is for the second rule. So this is target far and ammo okay. Oh, and by the way, this scenario, we've got a distance of 200 and ammo status of 8. So we have to go through all of these rules, checking for distance 200, ammo 8. So that means taking these two crisp values and performing the fuzzification. So here we can see for rule 2, so we're target far, so I needed the degree of membership function for far. So I check at 200, and I find that is 0.33. And then for ammo status, we've got 8, so that's right here. And then draw a vertical line with, and this is for ammo okay. So that particular ammo okay membership function, we get the 0.78. So that is our two values that we're comparing. Again, we're performing an AND operation. So for rule 2, the AND, so it's 0.33 and 0.78, or the minimum, which of course will be 0.33. So now we know the degree of membership for undesirable, and that is we can treat this all of these rules as a table. So you can see the activated rules, or fuzzy set of activated rules right here. So we've got these different values. This is going to tell us all of the membership functions for the output are going to be so desirable, undesirable, and very desirable. And so at that point, we need to do the defuzzification. So in terms of doing the defuzzification, again, recall that we know a degree of membership. We know also the output degree of membership function. So we crop the function by drawing a line from the value that's appropriate for each of these functions. So we're going to match these values with the right functions. We're going to crop them. Then we're going to combine them all. And so that's shown here. And then we have to pick a strategy. We got this weird shape. What are we going to use to calculate? So we could do like the center of mass approach, where we integrate under the maximum value here, or use one of the other strategies. In Buckland's example, we have the mean of the maximum, I believe, or average of the maximum. So for each of the three functions, so like rather than taking the center of mass, instead we identify where is the maximum. That's going to be the line form from the truncation, or the cropping. So each of these lines that you see for the three activated functions will take the mean of those. So that'll be in the middle of the flat plateau sort of line. And so that'll give us 3 values. And then we can use that to determine the overall crisp value output for desirability. So that it goes through the full example of performing the fuzzification, the evaluation of the rules, and then the fuzzy rules, and then the defuzzification. So there's a lot of flexibility here, because there's different, we can pick different ways of performing the fuzzy logic, like ands and ors. We also can pick the shape of our degree of membership functions on both the input and the output side. And then we also are selecting what's the strategy we're using for defuzzification, because we're going to have multiple rules activated, and therefore multiple degree of membership functions that have to be used in the defuzzification. So we can use fuzzy logic in decision making. In fact, we've already seen some examples of this. So use a fuzzy logic to select actions or behaviors or states, and each action can be applied to varying degrees rather than selected discretely. And so through application of the fuzzy logic, this is going to allow us to blend actions, especially in like transitional or gray areas where one action or another, it's not clear, like one is appropriate more than another. So we can apply fuzzy logic to maybe a decision framework that's similar to rule-based systems, and we've kind of seen that already. But there's not really a formal name for this, but It's occasionally referred to as fuzzy state machines. However, in Millington's book, he actually describes something that's more specifically finite state machines with fuzzy state membership and transitions, or one or the other or both. So we're not going to call those fuzzy state machines. And by the way, if you are interested in the fuzzy state machines, I'm not going to cover it in this lecture, but if you are interested, you can check it out in Millington's book. But back to using fuzzy logic for decision making in more of a rules context. You also often hear of it as just fuzzy logic, and that automatically implies fuzzy rules in use. So I'm just going to simply refer to it as fuzzy rules. So the key aspects of this approach, decisions are going to be made on some number of crisp inputs, and each input is mapped to fuzzy states. And so we've already gone through several examples with the fuzzy states. So these are going to involve the degree of membership functions. So we're going to take the crisp values and we're going to be able to map them to degree of membership for these fuzzy states. Some of those fuzzy states will end up with degree of membership that is non-zero. Again, we may require that the sum of all those non-zero degree of memberships that's going to need to add up to 1. And in fact, that actually allows for an optimization, which we'll discuss in a second. Our output states are going to be fuzzy states representing agent actions. And again, like we've seen, we can have multiple non-zero degree of membership for the output fuzzy states. And we'll have the structure of if input state 1 and input state 2 and input state 3 and so on through how many ever input states we have for a given set of rules. Then we're going to have this output state. So we might have an example: if chasing and corner entry and going fast, then brake. So that might be a rule describing a race car. And if leading and mid corner and going slow, then accelerate. So each clause in a rule is a state from a different crisp input. And the clauses are combined with the fuzzy and, which is the min operation. So we're going to take the minimum of all of the degrees of memberships that are determined after being processed by the degree of membership function. And in this structure, this fuzzy rule structure, it's going to be common to require all the fuzzy input state combinations to be represented in the overall set of rules. So many systems actually need entries for all of those combinations. And then each fuzzy output state will be the maximum observed from the activated rules. So here is an example. We might have input degrees of membership. So we've got corner entry, corner exit. So this would be like some analysis of the racetrack relative to the race car, and then the state, the speed of the car, going fast, going slow. So we've got those crisp values. They were mapped to degree of membership for these 4 input states. And then we've got rules that we can evaluate. And so here's an example of the rules with the values embedded, for example. So if corner entry, that's currently at 0.1 degree of membership, and then and going fast, that's 0.4, then brake. So that means that the output degree of membership for the brake, the brake fuzzy state, that will be 0.1 because we take the minimum of 0.1 and 0.4. And so similarly for the other examples, we get these various values. So we got all of these rules with non-zero, or the consequent, or all of these is non-zero. All right. So one thing that you can do with this framework for rule analysis, if you guarantee that the degrees of membership always sum to 1, so whatever the overlaps are, you have crossfades. Say those trapezoidal shapes always have a crossfade, such that if you've got like 0.9 degree of membership on one, then you've got 0.1 on the other. So it sums to 1. If you do that, this opens up a possibility that as you sequentially evaluate rules, you can consider what you've seen before, and knowing that there's a sum to 1, you can recognize that it's impossible for a rule to ever, like as you're partway through evaluating, to ever return a value bigger than, say, whatever the previous rule's highest scoring rule returned. So therefore, there's no point in continuing. So you can actually use this as an optimization, so you don't have to fully evaluate every rule in the best case, or maybe average case. In a worst case, you would still have to evaluate all. But end result is you can abandon fully evaluating some rules some of the time. Now, in terms of performance, so you've got big O for the algorithm's use of memory is n plus m, where n is the number of input states and m is the number of output states. But you also need all those rules stored. And if you recall, many implementations require that all possible combinations of the input state, the fuzzy states, be combined in these Boolean-like sentences with the ands. So in that case, you end up with the big O of the product of all the number of states in, and then they're multiplied I times. So it's basically n to the I number. So where I is the number of input variables. So you've got now this can vary, but let's say that you have the same number of states for all variables, just to simplify things. So you'd have n to the I, but many cases this is going to variables. It's going to vary. So you might have I input variables, so some will have one value or another number of states per variable. But we can maybe simplify it, just think of it n into the I. And then for time, you're going to have I times n to the I, roughly. So the takeaway here is that performance, it has a huge weakness in that it's not going to scale. As you come up with more states per variable or more input variables overall, the things are just going to blow up, and it's going to be very challenging to maintain. So one very popular approach with fuzzy logic is to try to avoid this combinatorial explosion. There's a strategy called Coombs method, and this relies on a little simple bit of logic to simplify the problem overall. So if we consider the situation P and Q implies R, that's basically what we have when we've got, say, two fuzzy states input on the antecedent. So if you have P and Q implies, say, some action, we can restructure that to P implies R or Q implies R. And if you do that, this opens up an opportunity to substantially simplify things. So we'll now end up with complexity of time where we're going to have our number of states times the input variables that we have. So much simpler, but we'll lose out because we can no longer combine our input states in a way that allows us to like carve up different strategies. So in fact, there's no way that we can say take a set of rules and then rip them apart into this new form where we just have the single antecedent value that implies the output action, because you'll end up with like these confusing situations, like where you might say for the same input variable, you've got two different opposing strategies. So it's best to actually start from the beginning to use the Combs method, like as the beginning of designing your fuzzy logic solution. So you're not going to use the ands and ors in defining all of your rules. Instead, you will just come up with these different single fuzzy states that imply to perform some action, or whatever the consequent is. And that again, we've vastly reduced the variables. And once you're familiar with this new approach, you can still get combinations of behaviors. It's just the combinations aren't happening on the antecedent side of the rule. Instead, you're going to get the mixing and blending of possibilities is actually going to occur in the defuzzification stage. So you've got these different different output states that are activated with varying degrees of membership. And because of those varying degrees of membership and whatever the strategy is that was selected for defuzzification, like the center of mass or the mean of maximum, or all those different approaches that we saw before, based on that selection, you get this interaction that still allows the Combs method to be pretty capable and do many of the same things that the fuzzy logic can do when you have, say, ands and ors, more complicated sort of Boolean-like operations. So that would definitely be something that you would want to consider if you have lots of input states or states on your inputs and lots of input variables to go with it. All right, so we'll wrap up fuzzy logic. So in terms of prose, easy to understand, very readable, this sort of declarative form, especially when we have like the set of fuzzy rules. It's an efficient way to represent linguistic and subjective attributes of real world or the video game world in computing. You get these smooth transitions between behaviors because the fact that multiple of these fuzzy rules are simultaneously activated with these varying degrees of membership, and then whatever the strategy is we use for defuzzification, that's naturally going to blend because we're going to be pulling the output crisp value is going to get pulled one way or another as things sort of gradually change. You're going to see that crisp value slide up and down the scale according to what rules activated. It might move quicker or slower as new rules activate or don't no longer are activated. It's generally going to be easier to create fuzzy logic driven behavior than it is going to be if you're using, say, methods that involve training. So again, those methods that are more grounded in computer science and probability, you probably are going to be able to come up with a more optimal solution than you can with fuzzy logic. But that's almost addressing the wrong concern when we're talking about video games. We're with the video game, we're looking for compelling, interesting behavior, not necessarily optimization. Downsides: defining set membership functions can be difficult. So there's lots of knobs and dials that we can be adjusting with fuzzy logic, and then of course that will have an impact on what we observe. And debugging knowledge can be difficult. You might have, say, fuzzy rules that don't often get activated, or when they are activated, their contribution is very small. Maybe you have certain rules that tend to dominate a lot, and conditions that would lead to other of the fuzzy rules being more activated or less maybe can just be very rare, and therefore the testing is difficult. And the defuzzification step can have surprising subtleties, and there's performance implications. So, of course, if you change from one to the next, you might have drastically different behavior. So it might be a little bit of just kind of random guesswork for some aspects of tuning fuzzy logic, though perhaps with experience you gain some intuition and understanding of how best to configure and design your fuzzy logic rules. Hello. In this lecture, we're going to continue our look at rule-based systems. So previously, I only went through a brief introduction of rule-based systems, but we will take a little deeper dive this time. So as you recall, when we were looking at rule-based systems last time, we discussed how it is from the era of symbolic AI, and was very popular in terms of academic research, 70s through 80s, and continued to be used in all sorts of applications well into, I would say, the early 2000s at least, and certainly still applications today. A lot of the work was in Lisp, so many of the examples you will find will be in Lisp because of the list-like nature of rule-based systems. So it's not as common in video games, though you can find examples of them. And let's see, so we primarily looked at the simplest possible rule-based systems that you can build in the introduction. And so that was to have production rules with a fixed priority arbiter. So basically, there's not actually any arbitration that's needed. And so that really simplifies what a rule-based system is, if you are substantially simplifying the arbitration. So when whatever sort of rule-based system you have, you'll have some number of rules, and they're analyzed in terms of some information, some knowledge that triggers the rule. And so you have a number of triggered rules potentially. So you might have more than one. And in those cases, there's this act of choosing which rule to fire. And that can be based on a variety of criteria. So that we're going to look a little bit at some different possibilities for that. Now, another thing that's really a challenge with a rule-based system is that the fact that you can end up analyzing a lot of rules, and you have a huge number, there's a challenge of managing the whole system and just the efficiency of how to be able to efficiently update, figure out what rules are triggered and then which to fire. And it's a problem, especially because the rule-based systems tend to become quite large with a large number of rules. So here is a simple example with some hypothetical game data. So we might have rules about what an agent does in like a combat scenario. So there might be rules about what to do if ammo is low or healthy or an enemy is near, and lots of other things. And all of those different rules are going to have some sort of condition for which a behavior will be executed. And now this can be indirect, as we'll see. But the end result is, at least in the context of a game, is whatever these conditionals are, it leads to agent behavior. And each one is a little like isolated behavior. Now, again, of all of these rules, you can have many that are triggered, meaning that the conditional logic is met. So in that case, the arbiter has to make a selection. And so all of this is driven through a database, or at least one design of a rule-based system is one that has this database. And that's common of like classic rule-based systems. So when each of these rules are evaluated, then some action is performed on the database, like removing some symbol or adding some symbol. And this is synchronized with the simulation. So that this is one sort of high-level design that you can implement for a game. So this database will have discretized representations of things in the simulation. Now, this might be very close to one-to-one in a lot of cases. So basically no discretization necessary. So for instance, you might have like an ammo count, so that the ammo count in the database would be directly representing the same information in the simulation. But you could have something that is more abstract in the database just for the purpose of supporting the decision making that the rule-based system is making. So and it can also include things that you might consider metrics. So like an enemy sighted, that's not data that is just inherent in the simulation. There's actually some sort of processing necessary typically to determine that an enemy is sighted. So that would probably involve like a raycast to make that decision. So whenever rules are evaluated, they would be analyzing the database based on whatever information is in the database. And that would have been synchronized with the game simulation. So then the rules are only acting on the database. And then as the rules are triggered and one or more over time is fired, then those will result in changes in the database, and then the simulation will have an opportunity to pick up whatever's changed in the database, and the agent will reflect some new strategy, some new behavior. So when you're working with a rule-based system, it's sort of like you're programming, but you're just writing these little isolated statements. So it's very declarative. So you're saying that if some condition is met, some constraint, then perform this particular action, which is usually, as we just discussed, a database manipulation or a database rewrite. So you'll have a database that is a mixture of information that is synchronized from the simulation, but also information that there's symbols that are being communicated to the simulation. So these might be like commands that are sent on to the simulation. So you might have, say, a steering behavior-based agent, and it's receiving these commands that are synchronized from the rule-based system database, telling it what target to steer towards, perhaps, or other behaviors. So I have an example here of database rewriting. Now, this is not a game example, but it's a pretty easy to understand one. So this is from Nules. And so if you're interested in rule-based systems, this is actually one of the platforms you might consider looking at, especially if you're familiar with JavaScript. So this is one that I've used before in some web development. So again, it's a JavaScript rule-based system. It's based on Jules. And this is just a little diagnosis example. And this is kind of typical of like classic rule-based systems work with would be to develop these intelligent systems to do things like medical diagnosis. So the idea is that you could have a huge library of these rules related to diagnosis, and all of them are evaluated, and they can be triggered according to patient conditions that are entered into this system. And then it'll spit out a diagnosis. And so in this particular example, we have some different rules about what symptoms this hypothetical patient has. And so, like, for instance, an example would be the patient. We have their name, and then we have their fever, which could be like normal or high or low. Spots on their skin, false, a rash, true, sore throat, false, inoculated, true. And so we might have, say, this is a very simple example, but we might have like a medical record, and information from the medical record would be present here. Then we could have various rules that are based on the conditions that you would find in this patient record data. So in the database, we'll have this, and so this diagnosis can be performed. Now, the diagnosis. This is where we have the example of the database rewrite. You can see that there is a. Let's see if I can get the mouse to show up here. So you can see that for the rule for flu, and it's got the conditions that must be met. So this conditional logic: sore throat, true, fever is either mild or high, and the then clause shows that a diagnosis is being instantiated, and this diagnosis is emitted. And so this is the act of performing the database rewrite rule. So it's inserting the diagnosis, and the information related to the diagnosis is going into the same knowledge base. Now, within the same set of rules we have for, say, the flu diagnosis, we also have rules related to determining treatments. And so this will automatically be fired according to this newly added data. This is the diagnosis for flu. So if flu or cold shows up as a diagnosis, then we're going to have this emitted treatment that now shows up in the database. Now, at some point, the rule-based system settles down. So you could actually, in this case, you would allow multiple rules to like fire one after another. So the arbiter might just go through, maybe picks one based on a priority or arbitrary condition to do so. But then you keep running the rule-based system, so it finishes analyzing every single rule gets analyzed, has an opportunity to be triggered and go ahead and let it fire. And so you might have multiple diagnosis for and then also multiple treatments. And so you might have a list of all of them. And so in that case, the doctor might have to pick. They'd say, well, all of these diagnoses could match. And hopefully it would be a very small number. But the main thing I want to show here was how this database rewrite would generally work, and how it communicates with both the rule-based system itself, changing. You can think of it as kind of like changing state. And so new rules get an opportunity to be triggered and be selected and fired. But you also have communications with some application layer. And so they're also reading from this database and maybe drawing things on the screen, for instance, in this case, or for a video game, the agent behavior would be reflected. So there's another way that we can define this conditional logic in the rules. And so probably in the intro, when we were looking at just very simple examples of rule-based systems, you might have thought, well, if there's a condition, then if the condition's met, then just directly tell the agent to perform an action. And so we can either do the database rewriting style that we just looked at, or we can do this simpler approach that's arguably more appropriate for video games of condition action. So we're bypassing the overhead of managing the symbols in the database. So like if we have a rule related to throwing a grenade, if enemy near, throw the grenade. So we're just directly telling the agent to perform the action. So yeah, there is a preference in game AI and in game implementations to do more of the condition action form rather than the database rewriting, because that involves a lot of dynamic data structures, these lists. It means that you're probably performing memory operations on the heap. So that means like using the new keyword to make newly allocated bits of memory that then have to be freed either manually in languages that require it, or garbage collections being hit. In either case, having a lot of memory operations that are typical of dynamic data structures, that's probably not something ideal for games. So the downside is that the database rewriting allows for this complex sort of data processing. We just saw an example with the diagnosis where the rule-based system can kind of track state internally, and you could probably still come up with ways to sort of send the data on into the game world in some fashion, or maybe have highly specialized rules where you have maybe some fixed data structures that can track some intermediate information about rules, but that's going to limit you. You're going to lose out on that flexibility. Now you can also have hybrid approaches, so you create specialized methods. It's basically what we're just talking about. So execute is part of an action, and then the results are reflected in your game state. So you can kind of use both approaches to be able to synchronize with whatever you're trying to do, either synchronizing with state type information so that future rules can act upon, or that the game itself, the agent on the game side, can perform whatever behavior is necessary. So in terms of representing information in our game, we're going to have declarative knowledge. And so these are statable facts about the world. And in the sort of classic Lisp-like presentation, you'll have these attribute value pairs. So you might have some attribute like the captain weapon, and that would be related to, well, what type of weapon does captain have, and then that would be rifle or machine gun or whatever. And so that value can change according to the state of the game world. And we can also have values that are nested knowledge. So this is like in Lisp, these are lists inside of lists. So captain weapon, and it could have a rifle, but we have a list that is an attribute of rifle, and then that could be ammo 36. So that's telling you basically that the rifle has 36 bullets. You can also have state-like information that is maybe related to, say, a steering behavior that your agent has, or an animation. So action, defend, or go to location. So the go to location, that is referencing like a path planning and path following combined into one. So this ability allows the rule-based system to be kind of like a state machine, because it is defining different different behaviors, like writing into the database of this different sorts of knowledge. So here we have an example with different different facts about a game scenario with like squad combat. Say you have some different soldiers, and they're working together in some sort of like a war strategy type game. So we might have attributes related to the health of each of the squad members, and then also what item squad members are holding. We might have an attribute for that, or weapons or ammo. And so all of these attributes is the declarative knowledge that can be used for triggering the rules, whatever the conditional logic is for each of these. So our database it holds all of this knowledge, and we have some external process that is its job is basically to populate and update the database according to the world state. So like maybe every frame, or some sort of determined rate, like a tick related to this AI processing, will go through and inspect game world state, do any sort of data conversions that are necessary, run any metrics that are associated, like that are not directly represented in the game world. These are also called probes, and so you might see a problem here is that there's no structure to how rules get executed in a rule-based system, at least that we've talked about so far. So unlike, say, a decision tree where we only need to execute our probes or metrics for the rules that are applicable, or similarly with a state machine, only the things necessary to determine transitions from the current state do we need to evaluate. We need to evaluate all probes, all metrics, any sort of expensive processing necessary to evaluate a rule. Well, if you have that rule at all in your set of rules, then you have to do all the analysis necessary to populate the database and keep it up to date. So clearly, this kind of sticks out as something that's detrimental to like real-time video game performance. And so the agent's going to need to have some sort of automation in place that gives it ability to perform the actions that are identified by the rule-based system. So the rule-based system is going to be updating the database with declarative knowledge, and that's going to serve as a signal to the agent to act upon, according whichever rules had fired. That's going to tell the agent what to do. And so that external process is going to be critical here, because it's going to discover in the database that there is this sort of stateful message that's being sent to the agent, and it's going to actually pass that data along appropriately, and then so the agent can actually perform it. So you're still going to have some additional smarts that the agent's going to have, and it's going to be more in the order of like playing an animation or running a steering behavior, maybe interfacing with path planning. And so the agent's going to perform these actions, and the results are going to be modifying the declarative knowledge, because if the agent performs actions, that's going to modify the game world, and those modifications to the game world are going to change. Similarly, the rule-based system could, while the agent's in the middle of performing any sort of behavior that it was originally instructed to do, the rule-based system could change, deleting that command from the declarative knowledge in the database and adding a new command, so some new behavior that the agent is going to be performing. And then we have procedural knowledge, the knowledge about how we do the things we do. And so this is basically the what is the action that is being performed. And so the if clause contains the data that needs to match according to whatever it's defined to be. So like Whisker's health, one of the soldiers. So we might have to match against, say, Whisker's health. So that's going to be joined by Boolean operators, perhaps with some other conditions. And so that's going to lead to what are different actions that we want performed by the different agents. So we could have a whole bunch of different rules that each refer to a specific object that is found in the game world that's represented in the knowledge. Now, if we have lots of different agents or characters in the game, we might end up in a situation where we have kind of similar logic running over and over again. So we might have a rule for Whisker, his health, and what to do if his health is low, or if the captain's health is low. and we might have the exact same logic related to both of those separate conditions. So it could get rather tedious to have to write if Whisker's health is less than 15 and if the captain's health is less than 15, and they're both identical rules other than the names. And if we have to do that for some arbitrary number of characters, that's just going to be a waste of all of these rules. It'd be much more concise if we could use some sort of wild card variable that could represent like anybody. And so, in fact, that's something that's very useful in rule-based systems, which we'll look at in a second here. So we have the components. We've got the declarative knowledge, the facts. We have the procedural knowledge, which are the actions, and often the declarative knowledge and procedural knowledge kind of coexist together in the database. And we also have selection knowledge, and this is knowledge about the way in which we're selecting rules. So part of that is just the conditional logic of the rules themselves. So like what are the Boolean criteria? But then there's also the arbiter, which is important to the selection as well. And so the arbiter will have some knowledge about what to do when there is an ambiguous situation of multiple rules being triggered. So which one is it that should be fired? So that's part of the selection knowledge. So the arbiter can get rather complicated. We've seen some simple approaches with the arbiter in our brief introduction previously. So we could have first applicable or fixed priority. And so this sort of bypasses the need for an arbiter at all. It's just implicit in the rules. You go through them in order, and the first one that triggers is immediately fired. So there is maybe some potential for average performance of not needing to analyze all rules. You will perhaps find one that will be triggered more often, though the way that they're often ordered is you have most specific conditions first and more general last. So it sort of makes sense that general conditions are perhaps the more likely to be evaluated. So maybe you still are evaluating all of the rules, but it'll kind of depend on how they're organized and just the nature of the problem. There you could have a least recently used strategy. You could just randomly select rules. We've seen a simple dynamic priority system example in our introduction, where we had some condition that would be evaluated. If the rule is triggered, then we would have some metric that would result in a priority. So we would track not only the fact that the rule is triggered, but it's triggered with a particular priority. But in this case, we have to analyze all the rules and see which triggered, and then we want to sort according to the priorities and pick the one with the highest priority. And so that can be pretty effective. And there can be all sorts of other ways that you might go about setting these up, dealing with situations with like trying to avoid selecting the same rule over and over. So maybe some hysteresis or stickiness to rules that maybe over time they eventually get replaced with some other rule. And that might be something that would be important in video games to do that sort of strategy, or anything with like a real-time simulation aspect to it. So back to the issue of needing these wildcard variables. So this is in the context of rule-based systems. This is called unification, and it's a notion of binding of variables into logical statements based on whatever these wildcards are. So a convention in some of the Lisp like rule-based systems is to um, show or represent with the question mark and a variable name. And so those are the wild cards in our rule-based systems. And so person, for instance, could be replaced with the name of one of our characters from our squad. So we might have any of the names that we saw before could be placed there. And now you match them. So if you have a complicated Boolean sentence as part of your rule, you might have further parts of the Boolean clause refer to the same variable. So we have an example here on the screen. So the question mark person health is one attribute that we're looking at. And then there's and radio held by question person. And so that person it matches in name. So it can't be two different people. It has to match. So you might plug in the name Whisker on the left side of the and also Whisker on the right side of the and. And so in that case, we would have to have the attributes that are maybe related in both parts of the clause, but it would need to fully make sense. Otherwise, that sort of unification strategy, the expanding the wildcard, it would fail. You would have discovered that there's not further information or attributes that would allow it to evaluate to true. So you would abandon that one, and then you'd maybe try the next name and so on, and to see which ones are triggered. So this allows rules that can match in many different situations. It allows more concise rule writing because you don't have to replicate rules unnecessarily. It does impact complexity. So you've shrunk the number of rules, but it's going to be related to the number of items in your database. And then M is the number of clauses in these patterns that need to be matched. So we have big O into the M. And so this is something that's really going to limit our use of the wildcards, because we're going to have to exhaustively analyze so many different possible bindings in order to find rules that can be triggered. So the algorithm, though, is very simple to implement. You'll just go through your database and determine these different candidate bindings, and then of those bindings, you'll evaluate with each of the rules, and then you'll be able to figure out if we're going to trigger the rule or not. Now, this is very simple, but it is problematic in terms of scalability. And so there's been a lot of interest in terms of improving upon this weakness, the lack of scalability. And so one popular approach that has been effective is the Reedy algorithm. So this is an approach for rule-based systems to make or to perform efficient analysis of rules, especially when we have this variable binding. And if we're able to efficiently analyze the different parts of the conditional logic, so that like the Boolean sentence part of the condition and the bindings that are related that we might have present in our rules. If we can do all that efficiently, then that might improve things for like video games, especially where we have real-time performance needs, and any other sort of system where we want the system to be able to quickly return different results and be very responsive. So what Reedy does is it is able to analyze all of the rules, looking for the patterns in the rules and related structure between multiple rules, and it restructures everything into a directed acyclic graph that has pattern nodes, join nodes, and rule nodes. And these can be used in a way so that they're sharing data between so the multiple pattern nodes that will feed into join nodes, what we'll look at in a second. And so this means that we're not replicating as much work. There's also the ability to preserve previous work. So if this is, say, built into like a game event loop that from moment to moment, little of the information will change. It'll probably be the same as it was the previous frame for the vast majority of the data. And so that is something that's also that works out well with the Reedy algorithm. So we've got with this directed acyclic graph, we've got these different patterns, and we can very quickly match to figure out, well, which rules are going to be triggered. And so, and then if changes are made based on a fired rule, so some changes of knowledge that either feeds back directly into the rule system or causes some behavior change in the game world, and then whatever that result of that behavior in the game world changes things, we're going to have these graceful sort of incremental updates to the data that's cached in the directed acyclic graph. And it is still able to work fundamentally the same as your typical rule-based system where all rules are analyzed and given an opportunity to trigger. Now, one concern raised in the Millington book is that this being true of any sort of algorithm that might be proprietary and part of a patent, is that you should always be cautious about using it in your own implementations, because it might be in a situation where you have to pay some license fee. So even if it's something that you write from scratch based on a description, even like say in Millington's book, it could have an impact on the products that you develop. And so Reedy is an algorithm that it is associated with proprietary and patented algorithm. All right, so we'll continue looking at the Millington example with the military troops. And so this is a Reedy example that involves some behaviors that you might have your troops perform that is strategically advantageous. So we might say have certain troops have radios, and the radio in this game is important that the radio stay operational for communication purposes. So you don't want someone with a very low health to be holding a radio, because if they become incapacitated or get killed or whatever, then you no longer have that communication going between all the troops. So there's this particular rule here that says if P1 health is less than 15 and P2's health is greater than 45, then we're going, and also that the radios are currently held by the P1 agent. So in other words, if P1 is hurt badly and all happens to be holding the radio, but there's also in his group is a player 2 that has good health or reasonably good health, then what we want to do is swap the radio over. So in terms of representing that swap, it's done symbolically in the database as a database rewrite. So first we have a write of removing the radio, and then again this isn't actually realized as an immediate behavior. It's just moving symbols out of a symbol is removed from the list of knowledge, and then we're adding a new symbol that reflects that the radio is held by P2. So again, we need some sort of external process to the rule-based system that synchronizes this information with the game world. So the agents maybe would play an animation of handing the radio off from one to the other, perhaps would be a way to do it. And then there's also another rule, change backup rule. And so this is related to cover fire. So maybe this would be like one of the troops is, say, hiding behind a barrier but firing bullets on the enemy position while another player is moving about. And so again, we have these wildcard variables that's reflecting the need for that unification strategy of being able to bind one of the characters to P1, but still meet all the conditions in the Boolean sentence. So if P1's health less than 15 and P2's health is greater than 45, and P2 is covering P1, then remove P2 is covering P1 and add P1 is covering P2. So basically this just means swap strategies. If you have someone badly hurt and they're maybe doing something in a dangerous position while P2's hiding behind a barrier and providing cover fire, then we're going to have them swap roles, because the one that's running around unprotected is so hurt that it make more sense to swap them around. So you can have lots of these rules, and all reflect the need for these wildcard variables and need this unification strategy. So Reedy, again, it's a directed acyclic graph. We're going to end up with something like this. So you'll notice that we've lost the ands. I think, let's go back again. So we had we had 4 different ands. So we had like P1 health less than 15 and P2 health greater than 45. So in these two example rules, you'll notice that for the swap radio rule and the change backup rule, they both have parts of the same conditional logic. And so we can break that down into individual pattern nodes. And so the pattern nodes are just the smallest pieces of those Boolean sentences. So what's on either side of the ands, and it could be ors and other types of logic as well. So those pattern nodes are then linked to join nodes, and the join nodes, that reflects the sort of Boolean logic that was removed. So those would themselves, each of the join nodes would be like an and lastly, those feed into the appropriate rule node. So whatever the condition that leads to the behavior or the database rewrites, what will be at the bottom in the rule nodes. So here you can see that by generating this graph structure, we've identified common uses of the same patterns in the rules, basically. So little parts of the rules represented in these pattern nodes. Now, these facilitate efficient analysis of the rules, because we can make these determinations just once and then they can be shared. But then there's also a lot more going on involved in running these rules, and that's because we have unification possibly occurring. So you'll see every single one of these rules has a wildcard variable, and those have to be bound to different possibilities. Now, in this case, each of the pattern nodes, they sort of are, they exist there in isolation. So say for radio held by P1, we could look at all of the troops in the game currently that are on, like say, the player's team, and we could figure out all the ones where this attribute is true. So that'll be any player one that has a radio held by them. So that might be a few different names. So we could associate that information with the pattern, and then we might similarly look at all the characters with a health less than 15, and that's going to be a different list. And then that information, so basically we're going to have lists of qualifying information at the pattern node. And then that's going to go down to the join nodes, and depending on what the Boolean operation is and what where it came from, we're going to find out if those bindings work or not. So we're going to remember what variable is bound to. So like for the furthest left pattern node shown here, it's going to be bound to the name P1. So that P1 name is important because it's going to have to be a match as the information propagates down the join nodes. What's going to happen is these lists that started originally at the pattern nodes, you might have a longer list, but as it bubbles down through each of the join nodes, you're going to be removing parts of the list as it joins with other lists bubbling down because variables don't match. And so you're going to probably get to a smaller and smaller set of candidates, and then finally determine of those which if any of the rules are triggered. So we might have an example of Captain Health 57 is covering Johnson, Johnson Health 38, Saleh Health 42, Whisker Health 15 is covering Saleh, radio held by Whisker. And so you can go through this as an example, and you can consider all of the different bindings that are possible from this the data in the database, which is shown here on the left. All those things that I just read off, that's our data that's in our database. And so we can look at each of the pattern nodes and figure out, well, what could we bind to, say, P1? And, well, there's only one holding the radio, so that's Whisker. And then we could look at, for the health less than 15, what bindings are possible. And that's again, Whisker. Health greater than 45, we can only bind Captain for P2. And then we have P2 is covering P1. And we got two different possibilities. We could either bind Johnson to P1 with Captain as P2, or we could bind Saleh for P1 and Whisker for P2. So we have all these different possibilities, and we're going to bubble those down and to the join nodes. And so we're going to analyze whether there's any conflicts that are occurring at this point, and if not, we just join them together as the all the possibilities that will go further, and then we'll at the lowest level of the join nodes, we're going to see that those are leading directly to our rules that might be triggered. And so you'll see that the only possibility is at the lowest level is for P1 to be Whisker and P2 to be Captain, and that means that the swap radio is triggered, and so at that point it can be selected and fired. So the database is fed into the top of the network of our reading network, and then the pattern nodes find the matches in the database and they pass them down to the join nodes. And when the wildcards are used, we'll have this variable binding. So again, you need both what fits into the variable, and you also need the name of the variable. Those two pieces of information are critical, because otherwise the join nodes won't know how to analyze and determine whether to exclude or not. So the pattern nodes are going to keep track of whatever the matching facts were. So this is going to be, in the, say, a video game, these are going to be preserved. And whatever matched the last time, that's going to be remembered. And it's just going to wait to see if any changes need to be made. So if the game world state has changed, if it's only just a couple things that change, then only the patterns that are affected will be updated. If they are changed, then only those get bubbled down. And so you can still preserve all of the other information for the other nodes. So this is really the key aspect to Reedy that has the big performance gain is that you're able to cache all of this. Of course, you're going to have the memory caching requirement to preserve this information. There is going to also be the bookkeeping cost, that if you have, say, a lot change, you're going to have an extra overhead of trying to figure out, well, what to update or not, when you might have been just better off updating everything. So it really does rely on this assumption that you're going to have very little change from update cycle to update cycle for most of your pattern nodes. So it will have less change. So yeah, that is very useful. Now the join nodes are also part of that caching. And it's basically the join node's job is to make sure that everything matches, and it'll have usually like the AND logic or. You could possibly have some other sorts of Boolean logic like an XOR. And yeah, so that's really key to the system in terms of collapsing together all of your different rules, the conditional part of the rules. Once you get to the bottom, it's very much like your typical rule-based system, because the rules are going to be triggered. You still need to have the arbiter that's going to determine which rules will go on to fire. But again, the whole system will, once those changes are made, if anything changes in the database, the next time we're just going to have this potential for the incremental updating. So we already talked about how all the nodes store whatever data they were last analyzed with. So all of that is cached, and they'll respond to any sort of bubbling down of new information. And if they change from what they previously had, they will bubble down. If not, there's no reason to have that affect anything below it. And so again, this allows things to work very efficiently. So that I guess closes out our look at Reedy. But even with Reedy, we still have problems with really large rule sets, to the point where we might be looking at further optimization. And one solution is to not always have all rules being evaluated at all times. And you can do that by having some sort of groups of rules. And so maybe one group would trigger, it may say, write to the database some change that says, load in this new set of rules the next time an update is performed. So this is kind of adding like a state machine like aspect to the rule-based system, so that one set of rules can figure out, all right, it's something's happened and it needs to go on to a new strategy. And so there's different approaches in different APIs for rule-based systems. So like in Drools, this is called agenda groups. You might see other approaches in different rule-based systems. So an example we can look at is right here. We have some different strategies, perhaps for like combat in a war type game. So we might have, we'll start with a master set. So this is basically a set of rules. Its only job is to enable other sets. But that doesn't mean that it's the only one that's allowed to enable other sets. So we can have like a hierarchy where the master set is the root, and then it identifies some state information, some conditional leads to the loading of this new activation group. Maybe have one for defense or offense or networks, and so we have the possibility to transition to these different sets, or transition into sub strategies within a set. So like offense might have melee combat or missiles, and those are selected again according to whatever the state is from the game world that's shown in the database. Now, one interesting thing about rule-based systems and some of the other of the classic symbolic AI era decision-making strategies is justification of action. And so this maybe not be as important in games, though I'm sure we could come up with some scenarios where it would be useful. But because you have these well-defined rules that are being fired, we know exactly what the conditions are that led to a rule being triggered, what the conditions that led to a rule being selected and fired. And we have maybe a whole chain of things that occur, like multiple database rewrites that occurred in sequence according to some initial condition and led to a resulting action that's being performed. If you have all of that information, you can write to a log and have a very detailed account of why something is. So that's really important in something like an expert system that's doing diagnosis for like medical condition. You want to be able to say exactly why something was done, because it's life or death. Now in a video game, maybe not as big a deal, but perhaps say a strategy game that where maybe the player is able to select from different strategies, maybe they're indirectly interacting with different sets of rules that are being selected, and resulting behavior occurs. And so the player might be interested, well, why did the agent do whatever they did? So maybe the role-based system could just tell the player, and you could take the audit, this justification of action audit, and present it to the player, and maybe come up with some appropriate and game-like way to show that to them. But then that would inform them and allow them to say adjust their future strategy, their future selection of actions. All right, so as for ready efficiency. So there's a big improvement here. So we have big O of n times m times p. So we have n is the number of rules, m is the number of clauses per rule, and then p is the number of facts in the database. So this is really a big improvement. And then average improvement can be pretty big as well, because we have that caching that is going on at each of the nodes, preserving. Now, if you have lots of unifying with wildcard variables, that can take over in terms of efficiency impact. If you have a large number of these wildcard matches. Now, there's a bit of a trade-off as well, because we have memory usage that is going to be increased because of the caching. So the trade-off is we're using the caching to buy our time performance. So advantages of a rule-based system is that it allows for something that has a bit of improvising to it. So it's not quite the same as like a goal-oriented planning, such as A-star planning. So we'll talk about that soon, looking at how if an agent is modeled from the perspective of goals, how we might be able to plan through a number of different possible behaviors defined with pre and post conditions, and then those would lead to different plans or sequence of behaviors that would hopefully lead to a goal. With a rule-based system, the fact that we're analyzing all of these rules collectively can allow for some improvising. We can have rules that get triggered and fired in ways that would never occur, say, with a finite state machine. There's only a small number of the transitions are considered. It's based on what the current state is in the finite state machine. So this can really allow for some more dynamic sort of behavior, but obviously we have this cost in terms of efficiency, having to analyze all of the rules. The performance hit is the trade-off there. And certainly rule-based systems is another means of creating reactive decision-making, reactive behavior selection. So downsides, you have less designer control because you can have these unanticipated reactions. It's just this declarative process of writing rules like, oh, in this condition, the agent should do this, and in this condition, it should do this, and so on. But it doesn't really, you can't really tie all the rules together with a cohesive sort of plan. It can be very difficult to debug because you never know of what rules exactly are going to be triggered, especially when you have the side effects of triggered rules resulting in your database rewrites, and also the resulting behavior in the game world and that feedback loop. So yeah, it can be very difficult, very challenging to debug and figure out. Making sequences of behaviors is also something that is difficult. Certainly there's possibilities there based on the information that's being stored in the database or stored in the game world as part of like a result of a behavior. Could track that sort of information, but it's kind of indirect and puts probably an unnecessary burden on the developer to try to do this, where it's much more natural in, say, something like a behavior tree. Certainly, rule-based systems have a reputation for being inefficient and also challenging to implement because of this the challenge of the inefficiency and trying to come up with ways to make it more efficient. And then also the authoring of the rules in that sort of declarative fashion. It's a level of indirectness, I would say, from defining these different rules in isolation, and then hoping that collectively, when they're analyzed all together, that you get the desired or intended sort of behavior. And you can get similar sorts of reactive decision making to decision trees and finite state machines, which, if you think about it, the decision trees or finite state machines, that it's a little bit more direct in terms of what you're trying to do. So it's more procedural, but you have more direct control over the end result as compared to the indirectness of the rule-based systems. So therefore, you might be thinking, why would I want to go to that much trouble? And I think really that the main thing that might lead you to want to do that would be if you particularly are looking for some improvisation, or if you, just the nature of the problem you're trying to solve, you have like little nuggets, little bits and pieces of things you know are the right thing to do, but you don't really have this cohesive strategy on how to tackle whatever the problem is overall. So this might often be true of something like a strategy scenario. Well, little bits and pieces of strategy, but telling troops exactly where to go and what to do, that's not always going to be something as easy to do. So there are lots of resources out there for rule-based systems. And I've got some information that was collated by another lecturer. And so there's a few different links, information on Drools and the related OptiPlanner that you might want to check out. Many of you are also familiar with the Russell and Norvig book, The Artificial Intelligence: A Modern Approach. And so in that book, there is a bit of discussion about rule-based systems. And so there is a project on GitHub that has some Java implementation that you might be interested in. Then let's see, here is, a little example of Jess. I forgot to put the link in here, but so you might want to Google Jess that's another system. And then the last system I'll mention is SOAR. And so this is another that is very popular, and it's even been used for game AI before. So this is a production system, and it's based on the theory of human cognition. And so it's meant to be like a platform to support all sorts of modeling, like simulating human cognition for purposes of agent behavior or decision making. So one example of the use of SOAR several years ago now was for Quake 2. There's a bot built with SOAR to play Quake 2. That is no longer available, but you can find discussion of online. So SOAR was developed at CMU and by these researchers, Newell, Laird, and Rosenblum. And so that is part of a very well-known work by Newell, The Unified Theory of Cognition. And this took several decades to develop, and it's been used in a lot of different systems. So if you're at all interested in rule-based systems, you definitely would probably want to check out SOAR as well. All right, so that wraps up our look at rule-based systems.
Good morning, everyone. Thanks for coming to this early morning talk. I know 9 a.m. is really early to talk about AI programming. I was a little bit worried about waking up myself. True story, last night at 3 a.m. my phone rang in my hotel room, and I woke up thinking it was my wake-up call, and I pick it up, and there's some drunk guy saying, "Where are you? Get down here." And I was all disoriented and confused. I just woke up. I was convinced that it was someone calling from the convention center, and that I'd overslept. So I jumped out of bed, got in the shower, and luckily I came to my senses, and I realized by the time I shower and get dressed, I'm going to miss most of the talk anyway, so I'll just cut my losses and go back to bed. So if whoever called me is in this room, thanks. You really freaked me out. So anyway, I'm a grad student. I'm using games to research AI. But I used to be a game developer. At Monolith Productions, I developed AI systems that we shipped in a number of titles, and this talk is about the unique approach we took to AI on Fear. If you guys were on a game show and someone asked you to name common AI techniques for games, the top two answers would undoubtedly be finite state machines and A*. We use both of these techniques in Fear, but in unconventional ways. Our finite state machine has only 3 states, and we use A* to search for sequences of actions as well as navigational paths. Our goal with Fear was to create an experience where you felt like the star of an over-the-top action movie. We wanted combat to be as intense as multiplayer against teams of real humans. So the AI do a lot of stuff. They work together to cover each other, to flank, to lay suppression fire. They dive through windows for safety. They crawl under stuff. They flush you out with grenades. They do a lot of stuff, so it's kind of counterintuitive that our state machine would have only 3 states. But in fact, the only states we had were go to, animate, and use smart object. Use smart object is just a fancy animate state. It's specific to our systems at Monolith, and rather than telling it to play an animation, you give it a database file that references a set of animations. But for the purposes of this talk, just consider it the same thing as animate. So what I'm really saying is we have 2 states. 2 states in a plan. So as much as we like to pat ourselves on the back and talk about all the cool things, all the smart things our AI and our games do, when it comes down to it, all they do is move around and play animations. That's it. And you might think, like, well, what about all the stuff like taking cover and attacking? And well, taking cover is running to a spot and playing a duck or a lean. Attacking is standing there going like this. And sure, the animation system does additional things, like on keyframes, it can play footstep sounds and create effects and tell a weapon to fire a bullet. But as far as the AI decision-making is concerned, all the AI does is decides to go somewhere or to play an animation. The hard part is figuring out when to transition between these states and what parameters to set. So parameters are things like, what position should I go to? How fast should I go there? What animation should I play? Should I play it once or should it loop? Typically, this transition logic is baked into the finite state machine in most games. And as we add more and more behaviors, this transition logic gets very complex. And sometimes this transition logic is in some kind of external table or edited in some kind of visual state machine editor, but somehow it's created by hand by a programmer or a designer. So what we did with Fear was use the planner to try to allow AI to decide for themselves when to transition between states and decide for themselves what parameters to set. So we wanted to take some of the burden off of the engineers and designers. If we look at the recent history of AI in games, not too long ago, we were happy if the AI just noticed the player and fought back. A little while later, gamers started wanting more realism. They wanted AI that could use the environment for cover. Today, we have these environments that are incredibly detailed and realistic with real-time lighting and physics. And if the AI behavior isn't as convincing as the environments. It's jarring. So we want AI that are very tactical, that understand their environment, that can use the environment and work together as best as possible to combat the player. And as we add more and more behaviors, the complexity gets unmanageable. It's not that any individual behavior in Fear couldn't have been implemented with typical state machine techniques. It's the interaction and interdependencies of all these behaviors that gets unmanageable. At last year's GDC, Damian Isla gave a great talk about managing complexity in the Halo 2 AI system. And I bring this up. This is one of his diagrams. You can see all kinds of behaviors that need to interact. I bring this up just to show that this isn't a problem specific to Fear or to Monolith's games. This is a problem the whole industry is facing as we want more and more detailed behavior. So you could think of this talk as being a variation on the same theme of managing complexity. The planning system was our attempt to manage the complexity. So what is the difference between a finite state machine and a planning system? In a finite state machine, you tell the characters exactly how to accomplish their goals. In a planning system, you tell AI what actions are available to them to satisfy their goals and let them decide on their own how to sequence these actions. So another way of saying this is that a finite state machine is procedural while a planning system is declarative. My motivation for going down this path was 3 years ago, beginning of pre-production on Fear. Designers are requesting all kinds of behaviors, and I'm thinking, there's only one of me, but there are lots of these AI characters. And if they're so damn smart, I should be able to offload some of my workload to them, and then we'll be all set. So the focus of this talk is demonstrating how a planning system improved the process of developing behaviors over the course of development of Fear, and showing you how we integrated this with our tools and how it supported higher level squad behaviors. So what exactly is planning? Planning is a formalized process where we're searching for a sequence of actions to satisfy some goal. And this process is called plan formulation. Our system at Monolith was inspired by academic STRIPS planning. So I'm going to give a really brief overview of what STRIPS planning means. The name STRIPS is just an acronym for where the system was created at Stanford. And in STRIPS, there are goals and actions. So a goal describes some state of the world we want to reach, and we reach that state of the world through a sequence of actions. And each action has preconditions that need to be true in the world in order to execute it, and effects of how it will change the world. A word about states. We use this word a lot in game AI. When we talk about finite state machines, states in finite state machines are procedural. They're updating every cycle. They're running some logic. They're playing animations. They're creating effects, firing weapons, like an attack state or a search state. When we talk about states in planning, we're talking about the state of the world. We're talking about an assignment to some set of variables that describes the world at some point in time. So in this image of a dog who's sitting at home wearing a tie, we can represent the state of the world in different ways. We can represent it with a logical sentence, like this dog is at home and he's wearing a tie, or we can represent it as a vector of variable values. So we've got this vector of variables at location and wearing, and we're assigning values home and tie. If we wanted to represent the state of the world in lemonade stand, we could use a vector of variables for the weather, the number of lemons, and the amount of money. These variables could be discrete, like weather is either sunny or rainy, or they can be continuous. You can have any number of lemons and any amount of money. So let's step through an example of how STRIPS planning might work. So if Alma, the evil little girl in Fear, was hungry, she wants to satisfy her hunger. So one way she could do this is by ordering Domino's. But if she wants to order Domino's, she needs to have the phone number. Alternatively, Alma could bake a pie. But if she wants to bake a pie, she needs a recipe. So we're representing the state of the world with these variables that represent a phone number, a recipe, and whether or not we're hungry. Our goal is to get to a state of the world where we're not hungry, and we don't care about the values of the other variables. If we're starting in a state of the world where we have a phone number and we're hungry, we can order Domino's and we'll get to a state of the world where we have a phone number and we're not hungry. If we have a recipe and we're hungry, we can bake a pie and we'll end up in a state of the world where we have a recipe and we're not hungry. If Alma is in the fortunate situation where she has both a phone number and a recipe, either plan will work equally well, and later on we'll discuss how we can get Alma to prefer one plan or another. A plan can have any number of steps, like perhaps Alma needs to drive her gremlin to the bank and take out some money, then drive home, then order Domino's. So ordering pizza is a Strips action. It has preconditions that we're in a state of the world where we have a phone number. And it has effects that we represent in Strips with a delete list and an add list. First, we delete the fact that we are hungry, and then we add the fact that we're not hungry. It might seem strange that we need to do this two-step process of deleting then adding instead of just changing a value, but there's nothing in formal logic to restrict any property of the world to having only one value. So if this action had the effect of setting hungry to no, we would end up in a state of the world where we're both hungry and not hungry. At times, this behavior in Strips is desirable. For example, if we have a buy action for buying an object, it has the effect of adding a property to the world that we own some object. And owning one object doesn't prevent us from owning another. So you can buy stuff and you can own coins and a key and a sword. So back to our example here, Alma has two possible plans that she can use to satisfy hunger. But what if we are, instead of trying to satisfy this goal for Alma, we're trying to satisfy it for Paxton Fettel. This is the cannibal in Fear. Paxton Fettel is not going to be satisfied with a pizza or a cherry pie. He's only going to be satisfied by eating human flesh. So what we see here is we actually have three plans that could satisfy hunger, but not all actions are available to all types of characters. So we make a subset available to each type of character. So this is essentially what we did on Fear, but rather than having goals of trying to satisfy hunger, we had goals like eliminate threat. You can eliminate a threat by firing a weapon, but that requires that the weapon is loaded. Or you can do a melee attack, but that requires that you're close enough to attack. So far I've shown you another way to implement behavior that we could have done fine with a finite state machine. So what exactly is the point? Let's look at some statistics first, some startling FPS statistics. The average lifespan of an enemy in a first-person shooter, not very long. The number of AI who die every day in first-person shooters, millions. For the price of a cup of coffee, you could save the life of a first-person shooter enemy. But jokes and Sally Struthers aside, my point is, if these AI are so expendable, why should we waste all this time and energy trying to plan actions to satisfy goals? To motivate this, I'm going to step through the process that we used with our tools to assign goals and actions to characters and show how this helped the process of developing complex behavior over the course of a 3-year project by piecing together simple parts. So the design philosophy at Monolith is that the designer is not responsible for scripting the behavior of each individual AI. The designer is just supposed to create great environments that allow AI to showcase their behaviors. So the idea is that if a designer drops a soldier into a warehouse, the soldier should just know what to do. But what we're finding here is I dropped this soldier into this warehouse, and he's not doing anything. He's totally ignoring me, even when threatened. He just stands there. So what you're seeing here is that when we go into our world editor and we drop an AI into the world, he starts out with no goals. He's got no goal set, so he doesn't do anything. So to remedy this, we go into our game database editor, and we create a goal set called GDC06. And we give this guy 2 goals, patrol and kill enemy. Now we go back into our world editor and we set this as the goal set for this character. And lots of characters can share this same goal set. So now when we go back into this exact same level with the same character, we find that he patrols around the warehouse. And when he gets to his patrol point, he turns around and eventually he notices us. And he starts firing. If we put an assassin in this exact same level with the same goal set, we see very different behavior. The assassin runs cloaked through the warehouse, then he sticks to the wall, and then when he notices us, he jumps down, and he comes lunging at us, and he beats the crap out of us. If we take this exact same level and the same goal set, and we put a rat in the level, we see behavior similar to the soldier. The rat patrols like the soldier. He follows a patrol path, runs to a point, and he turns around. And then he sees the player, and he gets very angry, and he comes in for the attack. He's coming in, still coming, and he doesn't attack at all. He runs away. So what you see here is that we have 3 characters in the same level with the same goal set, but they have very different action sets. The rat has the most limited action set. He has no means of attacking whatsoever. So even though attacking may be the highest priority goal, he'll never attack because he has no way of satisfying that goal. A soldier has the most expansive action set. He has all kinds of actions for ranged tactical combat, and the assassin has an action set for cloaking and melee combat. So what you've seen here is how a planning system lets you decouple your goals from your actions. In our previous generation of games, our previous AI system, we ran into the classic AI problem of the mime and the mutant. I'm sure you've all seen it. In No One Lives Forever 2, we had mimes. In Tron 2.0, we had mutant virus guys. And we were sharing an AI system where our goals had embedded finite state machines. And so all of the characters shared these goals, and there was no way that a character could take just part of a goal. You had to take the whole thing. And as we tried to add variations in behavior for different characters, we had to add more and more branches to these state machines, and they became very hairy and unmanageable. For example, in No One Lives Forever 2, we had these clumsy policemen who, as they chased you around, they'd get out of breath, and every few seconds they'd have to stop and catch their breath. And they were using the same chase goal as every other character in either game, and they were the only characters that needed this behavior, but because they needed it, we had to add a branch into the finite state machine of the chase goal that every character had to consider, and it just added more complexity when we wanted to go and make changes later. It added a lot of risk towards the end of the project. In contrast, for Fear, we were able to add an entirely new type of character during beta with no risk to anything. We added this flying drone with very little code. We were able to take actions and goals from other characters. We took the actions and goals for tactical ranged combat from soldiers and some actions for flying 3D movement from our ghost, and we created a new type of character. There's another reason to consider decoupling goals and actions, and that has to do with sharing of information. In our old system, each goal was a black box and didn't share any information with the other goals. The problem this causes is, well, I thought this Xbox 360 commercial reminded me of a problem that we encountered because of this. So what you're going to see is a bunch of guys running around a city pretending to shoot each other and reacting to that. And then we come to one guy who's too busy to react. He's got to finish what he's doing, and then he reacts. So we had almost this exact same problem on Known Lives Forever 2 with our old AI system. We had these characters that could interact with all these objects in the world, like they could decide to, for example, sit down at a desk and start doing some desk work. And you would think if you shot or stunned a guy at a desk, he would slump over the desk. But what we found instead was that you'd shoot him, he'd finish his work, he'd get up, he'd push in his chair, and then he'd pass out. This was because only the work goal knew that he was in the sitting posture interacting with a desk. And it had no way of sharing this information with the death or stun goals. In order to get around this, because we didn't want to ship this way, we just had to hack around it. There was no clean solution in our old system. In contrast, in a planning system where goals and actions are separated, this forces you to share information somewhere, like in a centralized working memory. So the work goal might set the guy into a sitting posture interacting with a desk, but when you transition to a new goal, all the other goals have access to this information and can adapt their plans accordingly. So having all these separate modular atomic behaviors allows you to layer more and more complex behavior over time out of very simple parts. And I'm going to show you the evolution of our combat system in Fear. You can think about the Fear Soldier combat AI as being kind of like a 7-layer dip. We start out with the base layer, the beans. The beans are the very basic goals and actions. A character initially has the goals of guarding or killing an enemy, and he can satisfy these goals with actions of idle or attack. The thing to notice here is that this is literally how we did it. We added actions and goals to goal sets and action sets, and you never have to explicitly create any associations saying, this action is for this goal, and this action can transition to this action. And while it looks like on this slide there's some kind of one-to-one correspondence, you'll see in future slides that's not the case. So in these videos, I've turned off the lighting effects so it's easier to see the character's behavior. So this is the beans layer. The character's guarding, and when he notices us, he starts firing. So next we add the guacamole. I've highlighted our additions in blue here. So we add a new goal, dodge. We'd like the AI to look like he cares about his life, and when a gun's aimed at him, he should get out of the way. And we give him a couple actions he could use to satisfy that goal. Dodge shuffle and dodge roll. And again, so notice we don't have to say dodge shuffle and dodge roll are used to satisfy dodge. The character will figure that out when he searches for actions because embedded in the actions are a representation of their preconditions and effects. So they'll have an effect that will satisfy what the dodge goal wants to satisfy. So now we see the same scenario. The guy's guarding, he sees us, he starts firing, and when we aim a weapon at him, he either steps to the side or he rolls. Next is the sour cream. We'd like our AI to be smart enough that if you get close to him, he can figure out that he can use melee attacks instead of ranged weapons. He can save his ammo. So we add the attack melee action. We don't have to add any new goals because we already have a kill enemy goal. This is just an alternative way of satisfying that goal. So now, same situation. The guy's dodging, you get close. He does some melee attacks. When you back up, he goes back to his ranged combat behavior. Now we add the salsa. This is where things are getting exciting. We add the cover goal. Instead of just dodging, we want AI to use the environment. So the cover goal gets an AI who's not in cover to want to get to cover. And he gets there with a go-to node action, and then once he's there, we have a context-sensitive action for attacking from cover. So he can play the right animation to attack from a covered position. So same situation, he runs over and he takes cover behind this box, and then he fires at us from there. So still as part of the salsa layer, we don't want to lose that behavior we added earlier for dodging. So we need to give the AI a way he can dodge into cover. So we add another action called dodge covered. And now what we'll see is that he'll go into cover, and he'll start firing at us. But if he notices a weapon's aimed at him, he'll dodge into cover and then come back out a few seconds later. Sometimes dodging is not enough, though. Sometimes you're still taking fire. So we give him an alternative means of attacking from cover, where if he's taking fire, he can decide a better strategy would be to blind fire, to just fire over the top of the box. So, and this is the onions. So he dodges, he goes into cover, he's firing at us, aim a gun at him, he dodges, comes up, fire a few shots. Eventually, he decides he's taken enough damage that he's just going to blind fire over the top of the box. We're getting towards the top of the dip here. We got the cheese. We want to get a lot more movement in the characters. We want them constantly moving around using the environment. So we add another goal called ambush. This is basically a goal for running and hiding when you don't have a good cover position. So we don't have to add any additional actions because ambush is just choosing a different kind of node to go to, and we already have this go-to node action. So in this video, you'll see a little more movement. Part of it is the effect of the ambush goal, and part of it is from level design. We add an additional cover node behind the box, so the AI can move around behind the box, but at some point he'll decide he's just not getting good enough cover, and he'll run and hide. And when the coast is clear, he'll come back. Oops. Okay. So he goes behind the box. He's taking a couple different cover positions back there. It's not working out. He decides, I'm going to get out of here. He runs to an ambush position for a second until he thinks his cover might be clear again, then he goes back. So we can get a lot of movement in the environment this way. The final layer is the olives, and we'll get to that a little later. That's where AI start communicating and coordinating with other squad members. So my point here is what you've seen is this planning system lets you throw in, just toss in additional goals and actions. And it's not like you don't have to write code for these. Of course you do. Each one of these goals and actions is a C++ class, a small, very focused class of behavior. But what you don't have to do is explicitly specify the state transitions. You don't have to specify which actions are associated with which goals, when an action can transition to a different action, or when goals can transition. You don't have to do any of this mess, and this is where it gets really unmanageable. In our previous system, in No One Lives Forever 2, late in the project, we decided we wanted to add this behavior where AI would turn on lights anytime they entered a dark room. Adding this behavior was a real headache. We had to revisit each of our goals and go into the state machines and shoehorn in this new behavior and hope we didn't break anything. So in the planning system, this would have been much easier. We could have said, all right, the go-to action has a new precondition that the lights are on in the space I'm going to, and we could have given the AI some new action for turning on lights, and he would have figured out when he needed to use this, and it would have worked universally for all goals that use the go-to action. So having AI that can sequence these actions on their own, this gives them the ability to reason, and as they plan and replan, this gives them dynamic problem-solving ability. So if we have this situation here where an AI is patrolling by, and he comes in this room, opens the door, he sees us, and he starts firing. If we run this scenario again, same scenario, but we change our behavior, we'll see the AI replan several times and adapt his behavior to fit the situation. So what you're going to see is the player is going to run over and physically block the door with his body. And then we're going to watch the AI's behavior in a security camera, and we'll see that the AI can't open the door. He'll try to kick open the door. When that fails, he'll replan again and look for another way into the room. So same situation, he's patrolling by, we run over, and we hold the door shut with our body. He comes up, he tries to kick the door after opening, it doesn't fail, it doesn't work, and he walks around, he finds a window, he dives through, he comes in close enough to do a melee attack. So now let's talk about implementation and how our implementation differs from strips. In a number of ways, we simplified strips for our purposes. So earlier we talked about how if Alma has several plans she could use to satisfy the same goal, they're all equally valid. But we want to, as game designers, have control over which action she takes. So we allow designers to specify a cost per action, and Alma will always try to take the least cost sequence of actions to satisfy some goal. So she'll prefer to order pizza, but if she doesn't have a phone number, she can fall back to baking a pie. So this is where our old friend A* comes in. Now that we have a cost metric, we can search for the sequence of actions that has the least cost path to the goal. Normally in games, we think of A* as being a means of path planning for navigation, and we used it this way too in Fear. This is a guy path planning on a navigational mesh. So if we compare our use of A* for navigation and for planning, in both cases, we have nodes connected by edges that we're trying to get to some goal. So when we're navigating, the nodes are navmesh polygons, and they're connected by edges, which are the edges of adjacency between navmesh polygons, and we're trying to get to some goal polygon. When we're planning, the nodes are states of the world, and actions are the edges that connect one state of the world to another state of the world, and we're trying to get to some goal state of the world. There are situations where we use both action planning and path finding at the same time. For example, in this video, there are characters that are using A* to pathfind to tactical positions, but they encounter the obstacle of this trailer, and they overcome that obstacle by doing action planning to figure out to crawl under it. So they plan their path, they crawl under this thing, and then they get to their tactical positions, and they're attacking us, and then we throw a gratuitous grenade. We saw in strips how actions have a delete list and an add list. We decided for our purposes not to actually implement a delete and add list. Instead, we represented preconditions and effects with the exact same data structure, this fixed size array representing the state of the world. The reason we did this is for performance. It's trivial then to find an action that has an effect that's going to satisfy another action's preconditions. So the attack action has a precondition that the weapon's loaded, and the reload action has an effect that it reloads weapons. So it's very easy to see that these actions can chain. So we had our world state was represented by this fixed size array of 4-byte values, and these are some examples of the kind of values we stored. And these values could have, these variables, could have constant values or variable reference values. So we kept track of like whether or not the target was dead, whether or not the weapon was loaded, what type of vehicle we were on. And we could tell the AI to go to a specific node or have actions that got you to a node specified by some parent goal or action. So for example, the cover goal picks a specific tactical node that it wants the AI to go to, and the AI can use the go-to action that has this variable reference effect that's basically like a wildcard that says, I'll get you to whatever node you want to get to. This fixed size array does limit us, though, in some respects. We can only have one value for each property of the world. So we can only consider one weapon and one target. And the AI may be carrying multiple weapons and may be aware of multiple threats. So the way we deal with this is through attention selection. We have subsystems that we delegate the responsibility of setting what's in focus. So the weapon system decides which weapon is in focus, the target selection system decides which target is in focus, and then when we're planning, we only have to consider one of each weapon and target. Another change we made is we added procedural preconditions in addition to our preconditions specified in this array. In a game world, it's just not practical to represent every aspect of a game world in a fixed size array of symbols or variables. There are things that are expensive to compute and or have an infinite number of possibilities. So we have a C++ class for an action, and an action has this fixed size array for preconditions and effects. And then it has this function, check preconditions, where we can write any arbitrary C++ code to run any checks in addition to filter out whether this action is valid. So an example of where you might need this is this AI, he's noticed this explosion, and he wants to escape from the danger, and he has two actions he could take. He could crouch down and flinch, or he could flee. But if he wants to flee, he needs to have a safe escape route. And it would be impractical to constantly keep track of an escape route available from any possible danger. So this is where we use a procedural precondition on the fly to check for the flee action. We do some pathfinding on the fly to find out, is there an escape route available? If there is, he'll flee. If not, he'll fall back to crouching and flinching. Similarly, we have procedural effects. If we just apply the strips effects, the fixed size array of variables, this would imply that effects take effect instantaneously. But in reality, it takes some amount of time to apply an effect. You have to play an animation, or you have to navigate to some position. So each action has a function that during execution, it runs this activate action function. And this is where our planning system connects to our finite state machine. So activate action is where the planning system sets the AI into a particular state of the state machine and sets a parameter. So, for example, the flee action determines where the AI should run to, and then it sets the AI into the go-to state with the parameter of some destination to go to. Another example would be all of the different variations of attacking. They would set the AI into the animate state, and they would pick a specific animation that worked for that type of attack. So now that we have AI that are smart enough to handle the basics on their own, that frees us up to focus on higher-level squad behaviors. In Fear, we have a global coordinator that periodically clusters the AI into squads. Each squad can run one squad behavior at any given time. We have simple squad behaviors and complex squad behaviors. Simple squad behaviors do things like telling AI to lay down suppression fire, go to specific tactical positions, or follow other AI. The complex behaviors handle the more in-depth analysis required to do things like flanking, coordinated strikes, retreats, and reinforcements. We had 4 simple squad behaviors. Get to cover was a behavior where one AI would lay suppression fire, and other AI who aren't currently in valid cover move to valid cover positions. Advanced cover is a behavior where one AI lays suppression fire while other AI move up to tactical positions closer to the threat. Orderly advance is a squad behavior where AI follow each other in a single file line into a combat space, and the AI in the back of the line faces backwards and covers the rear. Search is a squad behavior where AI split up into pairs where they cover each other and systematically explore different rooms in the map trying to find the player. A simple squad behavior follows these 4 steps. First, find participants. It tries to find AI that can fill these different roles that are required, like laying suppression fire or going to cover. When it finds these AI, it sends orders to them. The AI then, on their own, reevaluate their goals and determine how they want to satisfy those orders. Or they can decide that there's something else that's higher priority and they're not going to satisfy those orders. So the squad behavior then sits back and monitors the progress each update, each cycle or frame, and eventually decides that it's either succeeded or failed. For example, the get to cover behavior. Initially, there are a couple AI firing from cover, firing at the player, and the player fires back and invalidates one of their cover positions. At this point, the get-to-cover goal can find the participants it needs because it has someone who can lay suppression fire, and it has someone else who needs to get to valid cover, and there is other valid cover available in the level. So it sends orders to these AI to lay suppression fire and go to the new cover position, and then it sits back and monitors the progress to see if this guy got there. So he reevaluates his goals. He notices that he's got an order to get to some cover position, and he figures out that he can do a plan involving GoToNode to get there, and he starts running there, and eventually the behavior detects that the AI is at the position he was told to go to, and it says, all right, I've succeeded, and then the behavior exits. Alternatively, maybe the AI is on his way following his orders when he notices that the player has thrown a grenade. In this case, the cover position he was going to is now invalid, and the AI reevaluates his goals and says it's much higher priority for me to flee and save my life than to follow these orders. So he goes somewhere else. And the get-to-cover behavior, it's updating, and eventually it notices that the AI stopped moving at a position other than where he was told to go to, and it decides it's failed. And at that point, it exits, and it might immediately start up again with new orders. So now let's look at our complex behaviors that handle things like flanking, coordinated strikes, retreats, and reinforcements. How many of these did we have in Fear? We didn't have any. Gamers playing Fear observed these complex behaviors. They observed AI flanking, coordinating, retreating, and bringing in reinforcements. But we never implemented any of that. Basically, it falls out and emerges for free out of the interaction between the squad behavior sending orders and the individual AI responding to those orders and evaluating their own goals. And there are factors in the level design, what opportunities are presented to the AI. So like in the situation we were looking at earlier, where with the get-to-cover behavior, when the AI decides he's going to get to a new cover position, if the level happens to have some obstacle, he's going to come around from the side. And from the player's perspective, it looks like he flanked him, but really he was just going to the next cover position that he's aware of. Similarly, if we have two AI doing the advanced cover behavior, they might come from opposite sides and end up on either side of the player. And the player's like, wow, they did a coordinated pincher attack. How'd they figure that out? But really, they're just moving up to the next available cover position that they're aware of, and this is where their paths took them. Our implementation of squad behavior was not anything particularly sophisticated. It wasn't really notable. What's important is just the separation between the squad layer looking at the full situation and sending out orders, and the individuals deciding how to respond to those orders and having the option to even ignore those orders if they want to. A logical next step from what we did on Fear would be to formalize this squad behavior layer. And if you're thinking of doing that for your game, you might want to look at something called an HTN planner, a hierarchical task network planner. Describing HTN planning is outside of the scope of this talk, but my paper that goes with this talk gives some references that you could follow up. But the reason I bring it up is that the planning we're doing for individuals is completely sequential. It plans to take one action after another. But if you're planning for a squad of agents, you need to consider the fact that some of these actions need to occur in parallel. So you have to have some kind of a hierarchy. Having this bird's eye view of the situation in the squad allows you to figure out how to get AI to verbalize and communicate with each other. And sometimes this verbalization is enough to convince the player of behaviors that aren't even implemented. For example, our AI, they're aware of how many members are left in their squad. And when you get down to the last AI in a squad, they'll say some variation of, I need reinforcements. We never actually implemented any behavior for bringing in reinforcements. But eventually, the player is going to run into other AI in the level. And since he heard this guy say, I need reinforcements, the player assumes that the AI called reinforcements in, but really they would have been there anyway. Wherever possible, we tried to make these verbalizations a dialogue between multiple characters instead of just one character saying an announcement of some kind. Having this dialogue really reinforces to the player the fact that this squad behavior is intentional and reinforces the illusion of intelligence. So instead of having one AI play a pain sound, we have a dialogue between two AI, where one AI says, what's your status? And the other one says, I'm hit, or I'm all right. Instead of having one AI who's lost track of the player say, where did he go? You can have multiple AI. One says, did you see anything? And another AI can either say, no, sir, or might call out his position, saying he's behind the boxes. We also use dialogue to explain a lack of action. If you're firing at an AI and he's not moving, you might assume he's unintelligent. But if you hear multiple AI having this conversation where one says, get out of there, and the guy you're shooting at says, I've got nowhere to go, then you have this explanation, and you understand he's not moving because he's not aware of any better tactical position, and now he doesn't seem as unintelligent. I noticed someone on an internet forum making the comment that not only do AI give each other orders, but they actually do what they're told. The reality is, of course, that it's smoke and mirrors. We have this bird's eye view of the situation, and after we decide what the squad behavior is going to be, then we find a dialogue sequence that maps well to that situation. So where can we go beyond fear in terms of planning? It was great to see that the Fear AI seemed to be well received by gamers and the press. But it was also interesting to read a lot of people on the internet making the comment that the AI in Fear, the combat was just like the Marines in Half-Life 1. So Half-Life shipped in 1998, Fear shipped in 2005. So it kind of seems like in 7 years we haven't really made that much progress. And what's worse is people seem happy about this. They're like, yeah, it's just like Half-Life 1. So there's got to be more we can do. And my opinion is we need an order of magnitude more interaction, cooperation, and communication between the AI, and hopefully also between the AI and the player. But to get there, we need to look at new techniques. In the Cognitive Machines group of the MIT Media Lab, we use robots and computer games as platforms for studying language understanding. Our goal is to have robots and computer game characters that can use language the way humans do to communicate. This might seem far-fetched, but the Media Lab tries to aim for, it tries to look 20 years in the future. And if we look 20 years in the past at video games, 20 years ago we were playing Super Mario Brothers on the NES. And so games have come a long way from here. And today we have games with incredible graphics that all games can have great graphics. But I think in the next 20 years, AI is really going to be what separates one game from another. And if we look at GDC this year, there are a lot of interesting middleware tools, but they're all focusing on the presentation, these procedural animations. They're not going to make AI any more intelligent, any more able to interact with each other or communicate. What was I going to say? Okay, well, so anyway, so in Fear, our system for getting AI to communicate, it wasn't anything particularly sophisticated. We basically looked at the C++ code for the squad behaviors and just figured out where we could insert some dialogue lines. And this is a very labor-intensive process involving many iterations where you look at the code and you put in something, then you play the game, and it doesn't play out quite how you expected. And we had many, many iterations of tweaking. When you look at the code, it's not always obvious how things are going to play out. When we first put in the ability for AI to ask each other, what's your status, they were asking each other what's their status all the time. They were very concerned about each other. And there are times where this is inappropriate. Like in this screenshot, this guy's head has popped off. It's pretty obvious what his status is. There's no reason to ask him. And he's probably not going to respond anyway. So ideally, we'd like a system that's as well structured and well informed as our action planning system to control our dialogue. So one thing we're looking at is a unified planning system that combines actions and speech. Because when you think about it, the things we say are structured much like the things we do. There's some reason we say them, a precondition. Like you say, look out grenade, because you see a grenade coming towards one of your squad members, and you expect it to have the effect that your squad member is going to distance himself from the grenade. The hard part comes when there are actions that you can take by speaking or taking a physical action, and they both have the same preconditions and effects. So how do you decide when you should speak and when you should do something yourself? It turns out there are a number of factors you need to consider in the cost calculation when you're weighing one versus another. For example, the physical situation, like who's closer to the door, and the social situation. You don't usually shout commands at a higher-ranking officer. Another aspect of planning we're looking at is plan recognition. We want the AI to cooperate both with the player and with the AI. The problem is the player is unpredictable. So our thought is if you can observe the actions the player is taking, then you might be able to recognize which plan they're carrying out, and you can infer their goals, and then you can figure out what action they might take next and how you might best fit in with their plan. So for example, if you have a role-playing game and the player is trying to unlock a door and he has to create a key at a forge, and you've seen that he's picked up gold and gone to the forge, the AI can figure out the best thing he can do to help the player is go and light a fire. And it turns out that a hierarchical plan like this can be reformulated as a context-free grammar. The benefit of doing this is that then you can leverage existing techniques for parsing languages to parse actions and predict future actions. So I'm going to show a quick video, like a 1-minute video, of a prototype we built to demonstrate plan recognition. We built this prototype back in October, and what you'll see in this video is a player who's trying to get out of a locked door, and there are 3 possible solutions, and they all require help of an AI character, and the AI figures out the appropriate response to that player's call for help based on what he's seen the player do so far. So we built this using the Torque engine, and so the player is the barbarian guy, and he wants to break out of this door back here. And so the first solution he can use is that he can run to the Fountain of Youth to shrink down so that he can fit through this crack in the wall and go and grab this key. But when he gets the key, he becomes full size again, and he can't get through the crack in the wall. So he goes to get out through this door, but he encounters this door he can't get out of.
Can you help me with this?
So he asks for help, and the AI notices what he's done so far and realizes he can step on this lever to open the door for him. And then the player can escape. So now if we run the same puzzle again, but this time the player goes and grabs some gold and asks for help.
Can you help me with this?
The AI knows that to help him, he needs to light the fire, and then the player can go and create a key. And for a final solution, this is just a reverse of the last one. If the player goes over and lights the fire and asks for help.
Can you help me with this?
The AI understands that to help him, he should grab the gold and go to the forge and create the key. And then the player can grab the key and exit the level. So thank you very much. I'm supposed to mention for Monolith that they're hiring. They're hiring for all positions for future console and PC games in the Fear universe. And go visit their booth here or visit the webpage and work at Monolith. It's a great place to work. So hopefully we have some time for questions. 2 questions? Okay. Whoever gets to the microphone. Oh, go ahead.
My question would be, how did the AI react as far as like the physics objects and knocking those over and then using them for cover? Are those all like specifically scripted points that they know, okay, I can knock this box over this way and use it for cover? Is that how that works?
Yeah, in Fear, we have specific objects that can be interacted with for cover. But yeah, I think definitely for future games, it's important to start finding ways to author objects that, however they end up, you can use them for cover.
Were you able to come up with a good heuristic for searching the action graph?
We just used a heuristic of, we looked at the number of, in our fixed size array, we looked at the number of variables that didn't match the goal state, and we assumed that, our heuristic was assume that every variable can be satisfied with one action that has a cost of 1. And then when you search, you may find out that actually it takes several actions or more costly actions.
Hi. Could you talk a little bit more about how you determine priorities and transitions between the goals, so you didn't get like very binary actions or...
So the goals, in our game database, we assigned a priority per goal. Like designers would prioritize them. And then when the AI detected significant changes in the environment, like the goal has, the AI has sensors that are observing the environment and collecting these perceptions in working memory. And then when significant new perceptions come in, the AI flags himself to say, I need to reevaluate my goals. And then he goes through his list of goals and finds the highest priority goal that can be satisfied. Each goal has a calculate or is relevant function. And once we find the most relevant goal, then we search for a plan, which we may not find. If we don't find it, we move on to the next.
So this isn't evaluated every frame? This is
not every frame.
Okay.
But much less frequently than every frame. Only when necessary.
Hello. In this lecture, we're going to begin looking at goal-oriented behavior. So we are now going to transition from decision-making as we've considered it so far, now introduce the concept of goals for our agent and how goals can be used to motivate the agent to find or plan for a particular solution towards achieving a goal. All right, so first of all, I want to mention that goal-oriented decision-making in academia is focused on optimizing the likelihood of an agent achieving a particular goal or a reward. But in game AI, like we've mentioned before, but it's worth bringing this up again, is that in our game, any of the AI solutions that we look at, including goal-oriented decision-making, is that we are focused on generating or selecting, planning a behavior that supports the gameplay experience. So again, that leads towards simplification of the problem, cutting corners, cheating, in terms of finding our solution. Now that said, goal-oriented planning or decision-making in general, this is probably an area where there's the most similarity between what you find in academia and game AI as compared to many of the other artificial intelligence techniques that we've looked at so far. All right, so in regards to reactive decision making, we've looked at decision trees and finite state machines and behavior trees, fuzzy logic, rule-based systems. And so all of these approaches are reacting to conditions, like conditions in our game world that are accessible to our agent. And so these are all based on some predefined plan that was designed by the programmer, the game developer. And so successfully completing a step in the plan opens up the opportunity to complete the next step, provided that it's successful. But the agent only knows, in terms of its decision making, it's just recognizing that these individual steps can be completed. So implicitly, this can lead to a goal being achieved, but the agent's never aware that it's working towards that. It's never selecting actions because it is motivated by a goal. All of the whatever the notion of a goal is, that is in the head of the programmer, the algorithm designer. So that means that there can be some limitations in what the agent can do. So if we can involve the goals more directly with the agent, that might open up some possibilities. All right. So let's consider some problems with reactive decision making. Things that we're not able to do with the techniques that we've looked at so far. So one is we have this shallowness in terms of selecting actions. So all of the techniques we've seen, they have the agent take the next best move according to whatever is available. So in, for instance, a finite state machine, whatever the current state you're in, you'll have some number of transitions. And so of those transitions, you'll expect that the most appropriate transition is selected, but that's only if the developer has anticipated it and configured the criteria for the transition such that it can guarantee that it is truly the best one. Now, if some scenario is not properly considered by the designer, then maybe the correct transition is not taken. Maybe the wrong one's taken or no transition at all. You have similar problems with rule-based systems that can result from the nature of the rules that are available and also possibly the configuration of the arbiter. So whatever arbitration takes place to select a rule of multiple activated rules. So this is one of the aspects related to problems of decision making. This is one of the things that would lead us to think, well, maybe if we can include goals in the algorithm, that we could improve things. Another issue is adaptability. So again, this shallowness that we have represented in the techniques that we've seen so far, that means there's this lack of adaptability. Our agent can only respond according to the plan that is laid out for them. And this is not a plan for any like for different particular goals that might arise. It's like one collective plan that can address any sort of goal that might be prioritized that the designer has anticipated. So that again restricts the ability of the agent, and the end result is that any sort of unanticipated situation, the agent's not going to be able to respond well. And this is also an area where if we can involve goals in the decision-making process, then we can get some gains in adaptability. And also there's a heavy design burden. So all of the decision-making techniques that we've looked at, this requires that the designer build into the structure all contingencies as a way to encapsulate goals that might arise at any point in the life of an agent, at least in the context of a video game. So what are the different things the agent might need to do in order to maybe survive in, say, a combat situation or other gaming type scenarios, and so we might be able to, through the introduction of goals, avoid some of this heavy design burden by introducing adaptability and make some gains in terms of easier to develop agents that are already able to better respond to situations. So we have this desire to develop agents motivated by goals for their decision making, and because of that, this is generally going to suggest that our agents are performing some sort of planning. And so we've talked about planning before in the form of path planning, and we'll actually see that there are similar types of concepts at a high level as we go from path planning to more general decision-making planning. But in video games, there are also other simple goal-oriented scenarios that we can consider that are maybe simple enough that the planning is really a trivial thing. In fact, you might not even recognize it as being planning per se. So we're going to build up from the very simple examples, following along in the way that Millington presents in his game AI book. So we're going to look at a very simple sort of goal-oriented planning for agents in a scenario that is basically like the game The Sims. And so if you have ever played The Sims, you might be familiar with what we'll talk about. And I'll try to give a brief description of The Sims if you have not played it. So in The Sims, you as a player are kind of like a god, meaning that you're sort of like overseeing the well-being of your sim or sims, and you have indirect control, which is common of what I would call the god game genre. So you're not directly controlling the character. You're not telling them exactly what to do. Instead, you are manipulating the environment around the agents, and they have free will to some degree, at least according to their AI implementation. So the main way that you interact with the AI is that, well, you're looking out for their well-being, and they have different needs and wants, and you're trying to address that by providing artifacts. So these could be like different objects that help the sim. This can include things like building them a house, putting furniture and various items inside the house, and these can be related to the various needs of the sim. So these little human characters. So for instance, they might be hungry, or need to go to the bathroom or sleep, that sort of thing. And so you're responding to the sims by observing their emotional state. I think they have like little thinking bubbles above their head that show what is really on their mind, and so you're always having to manipulate the environment around the Sims, and so a critical piece to the game implementation is the AI, and so this is a goal-oriented sort of AI system. And so Millington describes something that I believe he worked on a game that, not The Sims specifically, but a similar game, and very likely the games of this genre work in some fashion similar to what Millington describes. So we have the agents like the Sims modeled with various needs. And these can vary with time and conditions. So, for instance, over time, agents can get hungry or sleepy. And as we'll see, even some of the behaviors that they can perform can influence things. Like if they exercise, then maybe they get hungry sooner. So the basic approach is that the agent, the implementation, the goal-oriented behavior is that it's selecting, that each sim is selecting an action that addresses current needs. And so these needs are the character's goals, is basically reducing the need. So we can think of the motives and goals are sort of unified, and so this is one of the aspects of where maybe in academia AI research these might be distinct, but often in games you can just treat them as the same. So in The Sims, these needs can be things like hunger, the need for food, bathroom breaks, social interaction, shelter, hygienes, like being able to take a shower, and there's other things as well. I think like having fun, addressing boredom. So there's all these different needs that you quickly learn about as you play the game and observe your sim and see how happy they are. And your goal as a game player, again, is to look out for their well-being and keep the Sims happy. So one aspect of the needs is that it's not just a on or off sort of thing. Typically in the gameplay, you're going to have what Millington refers to as insistence. And that's basically how strongly does the agent need something. So like in the case of hunger, a 1 would be like maybe they're just a tiny bit hungry, and then you work up in the scale. Well, I guess 1 would be full, and then like 2 would be hungry, and then you work your way up to 5 where they're just really hungry to the point that it's like detrimental to their health. So we can represent the insistence with a value. It might be like a discrete value scale. It could be real number values that increase, and really you can change to different types of representations of insistence, and still the overall concept will still be the same. And the reason why insistence is useful is that we can make comparisons between the needs. And you could include a weighting. Maybe some certain needs would be weighted higher. But if for the sake of the example moving forward, we'll just assume that they're all the different needs insistence values are normalized such that they are directly comparable. And so again, we're going to want that, because when the agent is making a goal-oriented selection of a behavior, we are going to involve this insistence. And so in terms of the behaviors, these are going to be actions that the agents can take. So each sim might consider all of their different needs and the insistence values related to each, and then consider all the available actions. Now, in the game for the Sims, most all actions are provided by the affordances of artifacts. So again, in this God game scenario, you're buying various gadgets and gizmos and so on, and then the each of these the agent can interact with in some way. So a bed the agent can lay down and sleep on. If the bed is not there, then they cannot sleep. And so this creates, this is the whole mechanic for the gameplay, is providing the artifacts to allow for these different actions. And other examples, you might buy a refrigerator or an oven and groceries, and then that opens up possibilities for the sim to address, say, the need related to eating, resolving hunger. You might, if your sim is having complaint or is complaining about being bored, then you could buy a video game system or a pool table, and that will address boredom with this fun experience. So once you can provide the sim with these different artifacts and they've got these actions, then the sim can perform one of these actions, but each of these actions will have a side effect. Now, in the simplest case, you might just focus on the positive result, that being the reduction of insistence of a need. And so if you reduce the insistence, then that is a good thing. So the sim will have one less problem at the current moment. But you can also have side effects that are negative. So you might have a dynamic that, say, addressing one need, the insistence of one need, might increase the insistence of another need. And it's also possible that you could have some actions that don't directly satisfy the insistence of a need, but it could be a critical step in a multi-step sequence that then would lead to resolving the insistence of a need. And so back to the example with the refrigerator and the oven and buying some groceries, you might have raw meat that's in the fridge. Well, raw meat you don't want to eat. You want to cook it first. So we could have like a whole sequence of actions of going to the refrigerator, getting the raw meat, then putting the raw meat in the skillet, put it on the stove, wait for it to cook, then put it on a plate, take it to the dining room table. And so this whole sequence is not until the very end when the insistence of hunger is resolved. Now that's a bit more complicated example for this goal-oriented behavior that we're hoping to implement for our agent. So we're going to focus on simpler examples first, but we are going to build up to handling that sort of a scenario. So a simple approach here is that we could have an algorithm where we just select the action with the most utility. And so we're going to define utility as just a reduction in need insistence. And we're going to select the one that's got the biggest reduction. And if we happen to have a tie, well, in that case, we can just have a random selection tiebreaker. But in this in this scenario, we need all actions that would be considered are going to directly address the insistence of any given need, and so that being our goal. So we're not taking into account negative side effects like the impact it might have on other needs, so if you consider this as a very straightforward algorithm, you can probably just imagine it in your head exactly what you would do, just iterating through your different actions and then seeing the impact on the needs, and then just keep track of which one had the biggest reduction. Again, we're considering that all of our needs insistence are normalized so that they're directly comparable. So we can just pick the biggest of all of them. So this is very similar to a rule-based system. We could actually think of all of these actions as being triggered if they're available at all. It's like they're all triggered at once, and we are determining a priority. And so this will be a dynamic priority because we've got the sim, their state, and the state being the specific insistence value. So for instance, if you have a hunger of the lowest value, eating a big steak that would normally, say, wipe out a level 4 hunger, that's not going to have a very big reduction in insistence. It'll have no effect. So it's dynamic because of the variation in insistence for the particular sim. So this algorithm, very straightforward. It's just the sum, a big O sum of goals plus actions. So we can consider an advanced scenario. And we're going to progressively consider more complicated examples. So here I've got a bit from Millington, the chapter 5, section 7.3. So he's got a goal where all of the needs and the current insistence levels are listed. So eat is at level 4, which is very high, 4 out of 5. Bathroom is level 3. And then we have right now only 2 actions available. So there is the sim could drink a soda. So I guess they have a can of soda nearby. That would reduce the insistence of eat or hunger by 2. And but there's in this case, with this more advanced scenario, we have a negative impact, an increase in insistence of bathroom of +3. And then there's also visit bathroom. And so that only has a positive effect of a reduction of bathroom of 4. So in this case, our current need for eating, that is at level 4. And so you might think, well, if you address the highest insistence need, then we would select drink soda to reduce it by 2. We can see that bathroom would then be increased to 6 or 5 if we're capping at 5. And so we can assume that reaching the highest level of insistence in the sims means something bad happens, like a puddle on the ground for the sim, and they'll be especially upset. So we actually, from this example, see that we need a new algorithm that determines the impact of selecting and applying an action that fully considers both the positives and the negatives. So for this new metric, we want discontentment. So this discontentment is a metric that is applied to all of the needs insistence values. And the SIMS goal is now to reduce overall discontentment rather than just selecting the action that has the biggest reduction in any given needs insistence value. Excuse me, because of this change to the metric, we can now properly consider both negative and positive effects of our actions that the sim might select. So instead of maybe selecting an action that then in the very next step leads to a bad outcome, like the bathroom disaster, now we can have some better informed decisions on which action to select on the part of our sims. Now, in terms of the discontentment metric, instead of a simple sum of each need, the insistency of each need, we want a nonlinear mapping of each insistence towards whatever the value is for discontentment. And so, for instance, if we have the scale of 1 to 5, we might want to have like a 4 be more than a linear difference greater than a 3 level insistence. And a simple approach is just to take the square of the value. So if you have a level 4 insistence for a given need, that would be 4 times 4. And then you would add that to the square of the next insistence value in the whole, whatever your total number of needs are. And so now, again, the algorithm is still very simple, but we do have to go all the way through all of the goals. For each action considered, all of the goals have to be considered in terms of the impact and then because the negative effects, we can cover. We have a positive effect on one need and a negative on another, or some arbitrary combination of positive and negative effects. And then also we've got the in terms of calculating our metric for discontentment, we have to evaluate all of our needs. And so this means that rather than the sum of goals and actions, we now have to multiply them. So a little bit more complicated in terms of time complexity. The memory requirements are still the same, big O1 memory for both approaches that we've seen so far. But this is really a big improvement in the quality of actions selected by the sims. Now, there's problems with the discontentment strategy. So one is that it doesn't take into account doesn't fully take into account side effects that result from actions being performed. So all we've seen is just the immediate effect on the insistence values of the needs. But we could also open up new actions in the future. So this is getting back to that example, like the cooking example. So if you take the meat out of the fridge and the next step, you have new actions available to you. You could put the raw meat on the stove. So this current algorithm doesn't capture that sort of change in effects and what that impact might have on reducing discontentment. It also doesn't consider timing. So if actions have a time element to them, like how long it takes to perform, it doesn't consider that. So we're going to first consider the second item, which is the simpler problem to address. So if we want to consider the impact of time, then we'll need to keep track of how long actions take to perform. And also we might consider insistence of our needs that increases over time. So we might have some sort of rate so if we have an action that takes a certain amount of time, our algorithm could consider, well, over that duration, the other needs, the insistence values of would then increase according to the rate times whatever the amount of time has been taken. So this discontentment calculation will be adjusted to consider the whatever these known action durations are and the insistence increase rate. So just multiply it out as part of the algorithm. So here is an example, again, from Millington. We have needs. Eat is currently at level 4, and it also changes at +4 per hour. And then there is bathroom currently at level 3, and it has also a predefined rate, but it's at +2 per hour. So within the hour, both would be maxed out at full level 5. And then we have some different actions that can be performed. So there's eating a snack, which will reduce the insistence of eat or hunger by 2, but it takes 15 minutes to complete now. So that's some new information related to the action. And then eat main meal, and that involves preparing the meal, so it takes a lot longer, but it has a higher reduction of the insistence value. So eat is -4, but it would take an entire hour. And then there's visit bathroom, -4 takes 15 minutes. And so we can consider each if they're applied, so that the algorithm would make this determination. So it would figure out what the new insistence values of all of the Sims needs are. So eating a snack, eat would now be 2 instead of 4, and the bathroom will have increased according to the rate, which is 2 per hour and times 15, so that's a quarter hour. And so we would now have the 3.5, and we can determine an overall discontentment, and that would be 16.25. And so we have similar calculations that are made, determining the reductions of each of the needs if that action was applied. Now, this is a simple example where only positive effects, meaning a reduction in insistence, is considered. You could also have the negative effects as well, but knowing this duration that it takes for each, we can go ahead and plan out what the end result would be for performing that action. So again, it's just multiplying the rate of increase of insistence for any given need times the amount of time that the action takes. And so this allows us to more correctly consider the impact of taking an action, and definitely lead to some more complicated sort of behavior. Now, one issue with this, in The Sims, your action durations will generally be known just by how long an animation takes to play. But in some games, you might have, in order for an action to be performed, it might be preceded by like a path planning. So the character has to walk over somewhere. There's a little bit of that in The Sims, but you tend to just be in the house with very short distances to travel. But it's important to consider that you're not always going to be, in terms of the algorithm, not always going to be able to just have a pre-computed value for how long an action is going to take. All right, so not all needs are going to have predefined insistence increase rates. So this is another thing that can vary. Some will vary over time, and in The Sims, this might change according to, say, maybe based on a day schedule. So perhaps the character gets hungrier in the morning, so maybe the rate will increase more quickly, perhaps at certain points of the day to try to motivate certain types of gameplay. And if you do have these sort of changes in rates, the game engine can just provide those to the agent. Like the agent just says, game engine, what is the current rate? And it can just plug it in terms of calculating the overall increase in insistence as actions are considered. However, some rates cannot be predefined in this fashion, according to some schedule. So you maybe need to think of other game scenarios beyond The Sims where you would have goal-oriented behavior. And that might be a situation like, let's say, a real-time simulation of combat. So you've got agents that are fighting with one another, and so you have maybe various resources, but one of the resources will be health, and this health value can drop according to, say, interaction with the human player or interaction with other agents, and you could analyze the rate that the health drops over time according to, say, an action being performed, like attacking. So if you have an agent that is considering an attack behavior or an action, then if it knew the rate at which it loses health while performing the attack, it might decide, well, say going into battle with 100% health, it's expected it'll drop to 70 for a round of attack. And that might be acceptable. But if the health is already at, say, 50, and you expected it to drop to 10 or less, then perhaps the agent instead picks to do something else, maybe like further recovery before considering that. Now, the challenge is, well, how do you figure out that rate? And that involves, you need some way to sample the values that are occurring as the game progresses, and be able to get an average over some window of time. So like in this, the example just given, you maybe measure how health drops over time while performing the attack behavior, and then you could preserve that information in the form of this moving average, and then be able to use it in future goal-oriented selection of actions. Now, in video games, this this particular approach that Millington suggests is very useful. In fact, you'll find it useful in aspects of game development beyond just this scenario. I use this quite a bit anytime that I need rates in a game. Because I'll first mention the correct way to do this. If you want a truly correct moving average or sliding average, you will generally implement this with a circular buffer, where the circular buffer has enough elements that it maybe represents samples at uniform time intervals over the length of time for which you want the moving average. And so you are, as you add new items, you're replacing the oldest data. So once the buffer fills up, you start replacing the oldest values, and you keep a running tally. And of course, you know the number of elements. So to perform the average, you can divide, if it's like a boxcar filter, where all items count equally, or you could have other filter shapes. Maybe if you want to, say, have a weighted average with a bias towards the newest elements. But all of that requires memory storage and complexity of maintaining the circular buffer. Instead, a much simpler thing is to just have a single variable to store. But obviously, you're giving up accuracy in doing so. But this works fairly well in practice, and it's to have an exponential moving average. And so you have some logic to how do you initially populate the thing. And so if it hasn't been written to before, you generally, the very first value gets to be the overall value. You can alternatively just have some neutral value like 0. So you just assume you're starting with 0, and then the values that you add to it have some little incremental contribution. And so the basic idea is you make the assumption that you're rather than dropping the oldest value out, you're just going to reduce it proportionally. So you'll have like an alpha value of say 0.05%. And so that this new value that you're adding to this like fake running average, I often call the exponential moving average like a poor man's moving average, meaning it's just kind of a little cheap, easy to implement approach. But so you might say 0.05 times the new value plus what's representing all of the old values. You would do 1 minus that 0.05 or 0.95, and then that would be times the whatever is your exponential moving average from the previous frame. So you get this new current frame value, and so it will tend to trend towards whatever the newest values are if they tend to be the same. So you'll have this exponential drop off of the values. But this is perhaps maybe more detail than necessary, but I think it's such a useful technique that it was worth discussing a little bit. So again, anytime that you need to track a trend in a value in a video game, this is great. But back to the topic at hand, if you need to monitor a rate for the purpose of selecting actions in goal-oriented behavior, this is a nice, quick, and easy way that you can do this. All right, so next up, we're going to start to begin to think about proper planning. We really haven't had much of any planning so far, other than just evaluating this metric and then picking whatever has the maximum reduction in discontentment. So with the Sims example, consider again that actions taken might result in new possible actions in the next opportunity to make a selection. So if you're trying to, in the current moment that the agent's making a decision, if you want the agent to make an optimal action selection, then it needs to consider the effect of following actions. And so this is where we're really seeing this need for planning. So for our Sims example, we can consider maybe a short sequence of actions that could be selected, but of that short sequence, what is the best sequence at reducing discontentment? But we can't just evaluate the sequences, like just all random combinations of sequences in the current step, because the actions we have available right now, that doesn't necessarily reflect actions in the future. So this is really complicating things, because if we make, say, the first action selection of, like, if we have 50 available right now, we pick one of the 50, and then we have to somehow figure out, well, what new actions would be available, and try to represent that in a way that then when we pick the second one, that we have the proper selection, and then the third one. And so at each level there's a change, and like, how do you keep track of what actions appear or disappear according to the effects of each action? And so this necessitates representing world state, and this world state is really, it's just a reflection of what the possible actions are in the game, and also the state of the agent. So like the change in the needs, the insistence of each of the needs. So world state is in a discretized form of the actual, whatever the actual simulation state is. So we're going to have this simplified representation, and it's just enough information to facilitate our planning that we're performing. And rather than represent everything in the world, one little optimization we could do is we could say, well, the current world state already provides us with a lot of information. So instead of just re-representing everything that might matter to us, instead we could keep track of like a difference vector. And so this would be, as we consider applying each action, all we need to do is say, how is it different than the current world state? And so this will be a list that grows in terms of information. As we apply more and more actions to this possible sequence, we're going to have more and more changes, the effects on the world. Some other aspects to these world states that we might find useful in the future, I'll go ahead and mention now, that to be able to copy world states. Make them easily clonable. So this may require some software engineering effort up front to ensure this. And similarly, it'd be nice if these are hashable. That means that we can store these in something like a hash table with quick retrieval. So in the Sims example, the world state, really is focused on modeling actions of the available sims and also the insistence values for each of the sims needs. So this first planning scenario that we're going to consider is going to involve a depth first search, but we're going to have a maximum depth. So we're only going to go to a certain depth, meaning that it's just a certain number of actions that we're considering. So this is over this depth, and it's generally a very small value, like 4, like for a Sims scenario. So 4 actions deep. What's the best one? The best action to select, or the best plan of 4 actions in a row to select that is going to have the best overall outcome for the sim. So in the Millington book, he describes an iterative implementation rather than recursion. So that this is nice in terms of real-time performance and memory utilization to go with iterative. And so if we did the basic situation, what we're doing is we're considering a first action to take, and then in a depth first nature, considering the next action to add to the chain, and so on until we reach our maximum depth, and then backing up and trying each iteration. So going all the way down to, say, a depth of 4, then backing up, and then working our way back to, so from 3 to 4 again, considering all possibilities. And so if you do this depth first search, sort of going all the way down and backtracking and down and progressively till all possible combinations to the maximum depth are considered, then you will find the best sequence of 4 actions. And if we build upon the algorithm that we looked at previously, we can consider things like the effects of an action in terms of the amount of time it takes, and both the positive and negative effects on the insistence values and overall discontentment metric. So we can we can pick the best sequence overall, at least to this depth. But this can be quite expensive. So it's worth considering anything we can do to avoid evaluating all the combinations of actions that are possible. And so Millington has a proposed heuristic that involves optimizing the depth first search expansion by abandoning a particular branch of this depth first search if a consecutive action results in an increase in discontentment. So what that means is, say you're at like depth of 2 in our search. So we are currently considering 2 actions in a row so far, and we're looking to add a 3rd action to get to our total of 4. If performing that 3rd action actually results in a discontentment score that's worse than at level 2, then we just can abandon that. And it's kind of like we're pruning off parts of the tree that's formed by the depth first search. Now, the downside to this is it means that a good long-term outcome that just happens to involve a short-term increase in discontentment, it's not going to be found, because we're just going to abandon even considering that branch. So this algorithm is big O n times m to the k. So again, n is the number of goals, m is actions, and K is the number of steps in the sequence. So how deep are we going to consider? So, like, say 4 actions, it would be to the power of a 4 action sequence would be to the power of 4, for instance. So this this is time complexity. So this is the same with or without the optimization that Millington describes, because this is worst case performance. And again, worst case would mean we might, for any of the branches, we might not ever find a case of where we see an increase in discontentment. But in practice, Millington says that heuristic worked well for a Sims scenario. I saw about 100-fold increase in speed. And he's getting that because we're not searching to like some arbitrary huge depth. Instead, these tend to be fairly shallow depth searches with the depth first search of say 4 and a choice of around 50 actions per stage, or that's what the agent has to choose between. So this does seem to be a good optimization, especially given the tendency to have a fairly short depth. It also has, Millington found it has this added benefit of avoiding short-term discontentment increase that would be inappropriate from like a human behavior perspective. And so this is actually something that's hard to deal with in turn. Like if you had the non-optimized or the non-heuristic version of the GOAP DFS, then you might have scenarios where, say, the sim would just accept that they're going to soil their pants, but say, oh, that's okay, they can just throw their clothes in the wash and change clothes and then ultimately be happy later. But real people don't act that way, and so avoiding those type of strange sort of negative consequences in the middle of a sequence actually can be a good thing, especially when you have these really simplified examples of like human behavior that this can pay off. All right, so we've now begun to get to the point where we have some true planning taking place, because we we're now needing to model our world, creating the discretized representation, and we're applying operators to the state, and we are searching through possibilities to find our goal, that being the sequence of actions that has the best reduction in discontentment. So we will next consider some even more complicated examples of goal-oriented planning. So we'll stop here and start up again soon. Hello. In this lecture, we're going to continue looking at goal-oriented behavior. So we're now going to consider a more complicated scenario where we're going to need A-star planning, similar to our use of A-star for path planning. So if we think back to when we were doing path planning, we needed to represent our continuous game world with some discretized form. So we broke up our continuous space into these different distinct regions that we could associate with a graph structure with nodes that have adjacencies in the form of edges that connect the nodes. And each of these nodes represents some state information about where the agent is located. And we could use a search algorithm such as A*STAR to plan moving the agent around in an abstract sort of way through operators that define the action of moving from one of these discretized space locations to the next. So we're going to have a very similar thing for action or behavior planning, where we do still need to discretize the space or the game world rather, as whatever is involved in the planning. So this might be, say, an inventory for our agent, like objects or artifacts that the agent possesses. It could be other state information in the game that is important to the gameplay. So maybe if light switches are on or off, or if certain resources are in certain places. But we still need this sort of discretized representation that is often defined in terms of some kind of relationship between the different elements of the game. And so this discretized representation, we have a world state, and we can manipulate it through applying operators that change or augment a given state to a new state. So, for instance, the agent might pick up an object and now possesses it, so it's in their inventory. Or that they flip a light switch and then the switch changes. So these operators have preconditions and effects or post conditions. So these are kind of similar to the operators in path planning, where you might have the up, down, and left, right movement with a grid lattice type of movement. But these operators, there can be many more of them because you have complicated behavior in games. These will often be maybe associated with like animations that the character plays. So it appears as if the character is performing some sort of behavior. So there's a lot of similarities, and really it is the same problem. It's just the way in which the space or the world is discretized and the specific operators will change. Perhaps there's many more as compared to path planning, but again, it's still this at a high level. It's still the same sort of planning, and there are some challenges that pop up because of the differences in representation, and we will address those as we move forward. So one thing I wanted to mention before we get too far into this is that Jeff Orkin, who worked for Monolith Studios, worked on an A*STAR behavior planning system for the game Fear. And in this class, you should check out his presentation that he gave at a game developer conference. And he went into detail on his motivation and implementation details related to designing the agents for the enemies in the game Fear. So be sure and check that out in the Canvas Learning module. Watch his talk. It definitely recommend checking out. It's very interesting, very informative. We will still touch on some of his ideas and what he presented in this talk, but I recommend you watch the whole thing. So one thing I want to mention now is that his motivation was not primarily to develop advanced AI capabilities for his agents. In fact, that was probably not a significant motivation at all. Instead, Jeff was looking to make it easier to author the behavior for his agents. And he saw a benefit in decoupling goals and actions and allowing for more declarative authoring and allowing for a lot more reuse in the code and implementation. And so we've seen that as being a beneficial feature of other reactive decision-making approaches in some of the previous lectures. So for instance, behavior trees have some very similar aspects as compared to finite state machines, but they are supporting reuse, just the nature, the behavior tree structure, being able to break off parts, subtrees from the overall tree and reusing parts across agents. So there's similar sorts of benefits from this goal-oriented behavior planning system. Now, when we're considering these sorts of systems, it is worthwhile to consider whether we're using a general purpose solution or domain-specific solution. So that in academia, you will generally find papers and books that discuss general purpose approaches, and that makes sense because it's broadly applicable. But from the context of video games or other high-performance situations, maybe control of real-time systems, you might want the benefits of domain-specific implementation just largely because of performance. But the general-purpose solutions are often very abstract. They work with symbolic representations. So from the era of like Lisp, where knowledge is represented symbolically, and because of that, you have a performance penalty because you're working with a lot of dynamic data structures, and like as compared to, say, having fixed length arrays, compressed sort of representation for rather than like general purpose sort of symbols having very specific data types, that certainly restricts how you might apply such a system to other problems. Like you're kind of going to be locked in with a domain-specific implementation. But that's the sort of thing that you probably need to do for a video game to get their sort of real-time performance. And so, for instance, like with Jeff Orkin's work in Fear, that's the one thing he goes into a lot of detail about, is how he had to give up some of this general purpose ability in order to streamline the system for real-time performance. So Jeff Orkin's solution was actually based on STRIPS, which is out of Stanford from Fikes and Nielsen. This was a planning system that was designed for a demonstration robot. And this robot could solve problems that involved manipulating stacks of blocks. And so you could give it a particular goal of maybe configuring blocks or getting the robot to a certain location, perhaps by building a staircase out of blocks and then climbing. And so it represented or discretized the state or the world of the robot, which was like confined to a room, so like a square area, I believe, and it had a finite number of blocks in the room, and they could be configured in different ways. So you might have, say, one block on top of another. And so that could be represented symbolically in their planning system with a relationship of like on, with that meaning block on one block on another, and it's parameterized. The symbol's parameterized, so you could say which block was on top of another. And so the planning system would work by having, there would be some number of states, and that would be like the initial state, and then the goal would be to have certain configuration of states be achieved. And so actions, there's just a small number that the robot was capable of, and these might involve stacking or unstacking blocks, or driving around to different locations in the room that it was confined in. So each of these actions has preconditions and effects, or postconditions. So the preconditions would be some requirement for the action to be allowed to be performed, and then there would be effects that, provided those preconditions are met, that the robot could reliably perform the action, and then you would get these certain effects as a result. So for instance, you might have an initial state where you've got, say, some blocks in a random configuration, maybe two stacked, one by itself, but your goal is to get them stacked in order, where A is on top, B is in the middle, and C is on the bottom. So this requires several different manipulations of the blocks, of picking them up and moving them, and the robot has to be able to figure out the relationship between these different operations, so that, for instance, it doesn't get further from the solution or block itself from whatever the next appropriate action should be. And this is a demonstration of why the planning is needed. So an operator might be unstack, and we can see that it's got preconditions. It requires that there be two blocks that are stacked, and that the top block, the one that we're attempting to unstack through the operator being performed, it can't have anything on top of it. So we could say maybe the robot is not strong enough, or not able to balance lifting two blocks at once, or whatever the limitation is. And then the effect is going to be manipulations of the world state. And this is performed by these add delete operations. So we're adding a new symbol that defines a relationship, and we're deleting some old state information that no longer applies because it's been manipulated and changed. So we can think of the search space as being these connected world states. So we're representing the entirety of the world in each of these little state representations. And we talked before in part 1 of this goal-oriented behavior series about how there's optimizations you could do here. You could just represent these world states as differences from the current state, so we don't have to store as much information. But we can still think of this as being this graph-like structure where we have these different connected states. There are a few little there's substantial issues that we need to consider about the nature of these states and how the states can change, which we'll talk about in a bit. So keep that in mind. So the strips actions can, of course, we can have all sorts of different actions. Here is an example problem involving travel. So we have different airports that, say, the agent might be at, and we're trying to get from one location to another. So we might have flying as one of the possibilities. You might have a system like this to help someone planning on on how to travel as well. This wouldn't necessarily have to be an agent. It could be like a recommendation system for like how to get somewhere, like which tickets to buy, and building an itinerary for travel. All right, so applying actions will change the world state in the context of the planning. So the world state just not being the actual world state, but a representation of the world as it changes incrementally according to these different operators or actions that are applied. And there's different sequences of actions that can reach the same world state. So this is kind of an interesting issue. And we have the same sort of thing in path planning. There's more than one route to a location. And so you can have more than one route to a world state as well. But there is no limit to how many actions in a sequence can be applied, typically. Like maybe in some narrowly defined problem domains, we might have limits. But generally, your agent, if it has some number of actions available to it, it's going to be able to just keep completing things. Say like stacking a block and unstacking and stacking and unstacking. There's not an easy way to limit that sort of behavior without adding some constraints to how our search is going to be performed. And so you can have actions that reverse these previous changes that have been made to world state. So this is different than path planning because you typically, at least for a video game, will have a finite map, and you can just keep searching until you exhaust all of the different nodes. But we can't do that with behavior planning because there's just always, you can just keep going back and forth. So because of that, it's important that we have some effective strategy to deal with it. And there's different things that are necessary. So since we have these world states that can be repeated according to the operators that are applied, it's worthwhile to recognize this and stop planning when there's a repeated state encountered. So this means that our state representations, we want to be able to easily compare them as we generate new ones. And one way, so we want to be able to clone them and then efficiently clone them and apply like incremental changes, because we generally, as we apply operators, just small changes are going to occur typically. And then we want to be able to hash them efficiently and effectively. And so that if we can do that, then we can support transposition tables. And so these are hash tables, but ones that have only one item per hash key. And so if we have that, what we can do is, as we're considering the application of different operators, as we're performing our search, we're going to be generating these new world states, and we can preserve them in the transposition table. And then every time we apply a new operator, like some new step in our search, we can check the transposition table first to see if there's already something at the hash that of the state we're trying to save. If there is, then rather than storing it redundantly, we will either replace the entry in the transposition table, and it's going to, so each of these world states is also going to be associated with the plan so far that led up to it. And so we're either going to replace the entry in the table with the updated partial plan, or we might decide that what's there is not worth replacing, and therefore we're not going to be storing what we currently have, and we'll just abandon searching any further down that path. And so that this creates some improved efficiency in terms of the search algorithm. Now, we could possibly have states that are different that hash to the same value, but we can still leverage the transposition table for this. And so the fact that we're only going to replace entries if with a certain condition, and so this can be done with a heuristic that if the action sequence, like this partial sequence of actions, so we haven't figured out the goal yet. This is just like intermediate as part of the algorithm. If we have a shorter action sequence, then that will replace the entry in the transposition table. So the same hash value, but now we have a new sequence. And otherwise, we stop searching that branch. But there's as in Millington's AI for games, video games book, he points out that this heuristic allows identifying the shorter action sequences in such a way that it ends up pruning off many of these possibilities that we would consider possibilities of sequences of operators being applied in such a way that that you avoid many possible redundant states. So this is a worthwhile optimization to the search, especially again considering that we can have unlimited sequences of operators applied. There's nothing that restricts, at least from the possibilities of what the agent could do. So we have to restrict the search itself. Now, in addition to that optimization, we still don't want to search to some arbitrary depth. So we will limit the depth, and an ideal way to do this is to use the iterative deepening implementation of A*. Now, this is not, we did not cover this in detail, but it is an appropriate variation of A* for this purpose. Now, you also need a heuristic. And so in this context, the heuristic estimates the distance from one world state to the goal world state. And so we'll revisit the topic of heuristic, but keep in mind that that's what the heuristic is going to do. Now, what we will end up with in terms of a plan is going to be a sequence of different actions, and we will have preconditions that are equivalent to the transitions in, say, like a finite state machine. And the effects are the same, like the results that you would have from performing the action or behavior associated with a state with a finite state machine. So if you perform A* planning with similar sorts of actions, you're going to end up with the same sort of resulting observed behavior of your agent. So it's really pretty much the same thing, except we're able to remove many of the different contingency sort of transitions that you might otherwise have to build into a finite state machine. So you get some decoupling of all of these different contingencies, and so you have a cleaner representation. But overall, you still have the same sort of individual behaviors. It's just the relationship between these behaviors is going to change a bit. So in many cases, you still get the same sort of outcome. So we're getting more flexibility because we don't have to bake in all of these different contingency sort of transitions. Instead, we can have goals that that can change, and those goals might change according. Like an agent might have many goals in mind, but the priorities might change based on the contingency. And so when goals change, that means that the plan changes. And so rather than representing that like in a finite state machine, we're going to be able to just allow this path planning, or sorry, the behavior planning algorithm to do all of that management for us. And so this is really where the big benefit came for Jeff Orkin in his system. So finite state machines, they're going to be telling the agent how to behave in every situation, every sort of contingency. But in the planning systems, the agents have goals and they have sets of actions. And the agent gets to decide how to apply the actions to achieve the different goals. And so that, because that planning is automated, it doesn't have to be pre-baked in, it's really easy to add additional goals, play around with a prioritization of goals, and it's also very easy to add additional actions. So that was a big payoff for Fear, for the game Fear. So Jeff Orkin was able to leverage that. So there's a lot of agent interaction with the environment, like strategically using objects for cover, hiding behind things while fighting with the player. And so the agents, they have to have a goal in order to be able to accomplish anything. But the agents themselves are not especially complicated in terms of what they do. They're all basically attacking the player. So it's a combat-oriented game. And so the system is basically the same planning system with many common goals across all the different agents. So you might have, well, in the game, there's different types of soldiers that might have different types of attacks and abilities. But a lot of them, they'll share the same goals for the most part, but they'll have different actions available to them. These actions are largely associated with animations that they play, maybe some special cases for certain types of weapons and that sort of thing. And they all have some path planning as well to perform to get around the environment and to track down the player. But overall, the system's very flexible. And Jeff Orkin did not need to build complicated contingencies into state machines like he had with previous games that made the state machines very susceptible to bugs, especially when trying to add new capabilities with very little time for design and debugging. But it is much easier to do so in Fear. So the planning in Fear results in some different benefits. So, for instance, the decoupled goals and actions. Each character has their own action set, and therefore, when the search is performed, there's different unique preconditions and effects. Still motivated by the same goals of attacking the player, self-preservation, that sort of thing. But this allows for late additions to character types. It automatically addresses, excuse me, the connections between different sequences of behaviors, and as long as you get the preconditions and effects correct, you get generally the sort of expected behavior from the agent that you want. You also can more easily share information between goals, whereas in a state machine, this requires a lot of hard coding that's very fragile. You can layer behaviors easily through just having different sorts of actions or behaviors, and also goals with different priorities. And you can also realize dynamic problem solving. So the system can replan when there are failures. So if the plan is generated and the plan cannot be completed, so there's an example shown in the Jeff Orkin's presentation where there is a soldier trying to track down the player so it first tries going through a door, but the door is locked. So then the agent will go through the window. So it breaks down the window and hops in. So in the case of fear, there's a very flexible system. Again, it's doing things that all could have theoretically been designed as part of a finite state machine, but it's a much easier system to maintain, to extend and modify, and even the initial authoring is all much easier to handle. So benefits of using A*STAR is that the agents can find creative or emergent sorts of solutions that weren't specifically designed, but that as individual, actions performed is all possible. It all could have been implemented with some other sort of reactive planning. It also can be less predictable because it can always, as goals and situation changes, it can shuffle around or mix and match different actions to achieve different results. Downsides, though, you can have optimization of actions to a fault. So you can end up with, for instance, these sort of absurd mall cop type solutions. So if you think back to the example of the guard trying to break down the door to get to the player to attack them. If the guard already knows where the player is, it might decide that, the shortest path spatially might be, rather than walk all the way around to the door, just go through the window right from the start. And that would be kind of silly in many situations. You want to try the easiest, lowest energy effort. And that's really just a problem of defining action cost. So in terms of searching, you want to have certain actions that have relative different cost. But so this is sort of like a tuning sort of issue. You could also have other kind of crazy possibilities, like maybe if the agent is aware that an object can, say, flip a switch, you could end up with the agent throwing a grenade to flip a light switch, and so that would be the sort of thing you would probably want to avoid. And so the nature of having this planning system is that all of these actions are available to consider, and so there might need to be some sort of restriction to make that less likely or not possible to have it returned as a result. It can also be more difficult to debug. When you have a finite state machine, you at least know all the states and transitions. So when you see some behavior occur, that was a result, a dynamic result from the planning system. It can also be much more computation involved. The finite state machine has a fixed data structure, whereas with the planning system, this has to be rebuilt anytime there's a change in goals, or maybe a broken plan because a certain action could not successfully be performed. So you're having a lot of opportunities for computation. And if there are lots of actions that are possible, then you can have a really huge search space as well. Sophia is not the only game to have used a planning system like this. There's also some other examples you can find if you Google and look into the implementation details. Empire Total War, Fallout 3, Killzone, which I believe use hierarchical task networks, which we'll briefly mention in a bit. But yes, so this is a fairly popular approach that has, especially after Jeff Orkin's presentation, generated a lot of interest. So here's another example of a scenario where we have some hypothetical character has got this initial state, has a gun for sale, ammo for sale, possum alive, but he does not, so the little tildes negate. So it doesn't have a gun loaded, doesn't have food, doesn't have a gun, is not a criminal, doesn't have ammo, and so on. So that's the initial state for the character, but the goal of the character is to get rich and have food. So there's all these different actions that can be performed, like rob bank, shoot possum, load gun. And you can see each has preconditions and different effects. So if we visualize all of these different possibilities that could lead to the goal, you end up with a fairly elaborate set of actions that can be performed in different ways, different combinations. And it does look a good bit like a finite state machine in terms of this structure generated, but it can continue on forever if we don't have some limitation. Now, the way in which these sequences are created, there's two fundamental ways of approaching this, and one is to do so in a forward direction. So you're performing a state space search where you start with the initial state, whatever the current conditions are, and then applicable actions that with the preconditions are currently satisfied, whatever the current, like so at the very beginning, it's just whatever the current world state is. But then as we apply operators or actions, then the world state's going to change and it'll open up new possibilities. Either new actions will be available or actions will be no longer available, depending on the precondition requirement. So we can expand all of the possible actions from the current state. Then we can test each for the goal, or as we select the one with the best score, we can check for the goal, and then basically perform the A* search, but again, most likely a depth limited search, and so that seems a familiar and sort of expected way of approaching the problem. But we could also perform a state space search that goes backwards. So we would start with the goal and assume that the goal is met. And so what action could have led to that? And then of those actions that could have led to the goal state, what are the preconditions for that action, and then that defines what would be the action that would go before it. So we'd look for actions that have goals that address the preconditions of the other action. And so you're basically working backwards. And so this sort of reasoning, this is a little example that was on Wikipedia with Fritz the frog, but it's showing how you might go about reasoning in either with forward reasoning or backward reasoning. So we might have certain rules that define characteristics of, say, different sorts of creatures, and we have some knowledge. And so based on the knowledge, you go forward through the rules, chaining them together until you reach the information that you're looking for. So we have rules like, if X croaks and X eats flies, then X is a frog. So we have knowledge that Fritz croaks and Fritz eats flies, and so we can just look through and see if any of the rules match. Of course, the first rule matches very, very quickly, and we're done. So we're able to figure out our goal, which was to determine. Actually, let's see. We're trying to determine what color is Fritz. So we actually have to evaluate rule 3 as well. So we plug 1 and 2. It only matches with rule 1. So now we have new knowledge that Fritz is a frog. Then we can plug that into 3, and then we get green. But the backward reasoning, we start with, well, what would be valid for color? So we look at all the rules, and we see that, well, only 2 of the rules address color. So one is that is green, and the other is yellow. So we can recognize that those are the only 2 colors. So then we can say, well, if it's green, then it's got to be a frog. So then we could find, well, what is a rule that matches with the result of being a frog? And then so that identifies that whatever it is croaks and eats flies. And so you can see how this backward sort of chaining can work. So this is a really kind of simple constrained example. But let's consider this other scenario. Let's say we have a needle in a haystack. So we've got this array of sticks, and all of the sticks are either hay, or we'll also say a stick can be a needle. So either bits of hay or a needle. And our goal is to stick a needle in a voodoo doll. So maybe we have a video game character, and it wants to stick a needle in the voodoo doll. So there's lots of sticks around, and we need the needle. So with forward chaining, it's going to require checking each stick with get stick operator or action, and then seeing if we can chain that with poke voodoo doll with needle. So that with the prerequisite being that the agent has the needle. But with backward chaining, we can start with sticking the voodoo doll, because the result is that action has been performed. The goal is to stick a needle in a voodoo doll, and so if that has been performed, then that's the result of that particular action. So we work backwards from that, and so we know that needs to be a needle. And so the symbol for needle is identified, and then get stick needle can be called completing the search. So you have these sorts of scenarios that can pop up. Another popular example that you'll find if you like look at planning systems is, say, buying a book and by its ISBN, so the unique code for the book. So if you're going to if you need to buy a book before, like as part of a sequence of actions, maybe buy a book and then read it and write a book report, with write the book report on the book being, say, the goal. In terms of the planning system, you would have to have the agent, as part of the planning algorithm, would have to consider buying every possible ISBN in the database, which could be massive. So there's, to us, it might seem obvious, like, well, you just pick the correct book. You'd have to have a heuristic that's aware of that, which might be possible in a very narrowly constrained problem. But if you have a more general purpose sort of planning system, that would be challenging to have a heuristic that would work in a like a general case. So it's likely that in terms of the search, you would need to, with forward planning, you would need to search all of those different possible ISBNs until you finally find the correct one. So this sort of demonstrates the problem. Now, of course, you could have, like, for the needle in the haystack, you might actually want your game to have this challenge of finding the needle, but this isn't reflective of like a puzzle for the agent. Just the searching out of the number of possible actions that are available, and it could be a result of the combination of parameters for the action, could result in this explosion of possibilities, and that would make forward planning not desirable. So like backward planning could work a lot better in this case. So with forward chaining, you have a lot of irrelevant actions, or the potential for irrelevant actions to cause a high branching factor. And in planning systems, like you can have agents that are capable of lots and lots of things to do. But with backward branching, your branching factor can be much smaller, because by working backwards, you're often in a scenario where you've excluded a lot of possibilities because you already know particular bits of information that are desired. And so, say, similar kind of parameterized possibilities like the needle in the haystack, you exclude all of the irrelevant actions by going the other way. But this can be susceptible to long backtracks where effects negate earlier decisions. So you can have trouble not being able to connect with whatever the initial state is easily. And it can also be more challenging in terms of heuristic design with backward chaining. But I believe, at least in academia, descriptions of planning systems, they tend to focus on backward chaining for like these sort of planning systems. So our heuristic, again, with A star, we have the sum of the action cost and then plus the heuristic. So how do you estimate the distance to the goal? And it's going to depend on whether you're doing forward or backward chaining, whether it's actually the goal that you're trying to reach or the initial state, so distance to the initial state for backward. So our heuristic is going to be informing the search algorithm about which node to expand. And if you recall from path planning discussions, there's a good bit of attention given to the admissibility of the heuristic. So if we have an admissible heuristic, that means that we will be able to get the shortest path for path planning. But we also saw the inadmissible heuristics and the benefits that can have, because it can give us a more informed estimate. So we might be able to sacrifice some possibility of getting an optimal solution, sacrifice a bit of that, so that we spend a lot less time, a lot less effort in the search, expanding nodes. So we previously saw that, if you want an optimal solution, use admissible. If you don't have a heuristic at all, it's going to be the same as Dijkstra's, because the H is 0, so all we have is the cost as we expand. But if you have a heuristic that more accurately reflects cost, then the search becomes more informed. So in this sort of general planning, an inadmissible heuristic can actually be beneficial in similar ways that we saw with path planning. So we might be willing to sacrifice this sort of optimality for the purpose of the real-time performance of our game, for instance. So in terms of a heuristic for A-star path planning, it can get pretty challenging to design a heuristic. So it depends on if you're going with forward chaining or backward chaining, but it'll generally be based on the cost of what are the differences in the world state representation that you currently have that you're considering, and what is the desired world state. So whether you're going forward or backwards, we're comparing world states and differences in the world states. You can potentially do some sort of pre-computation or analysis to come up with maybe some fixed or perhaps a parameterized function that would give you a heuristic cost for different say actions that could be performed. And the way in which these are compared, you probably want some common unit of comparison. So if some say a particular symbol in the world state might be associated with one action, and so would be straightforward. Like if it's always only that one action, you could just have whatever the cost of the action that manipulates that that symbol in the world state. That would be your heuristic value, and it would be a very accurate one. But you can have things that involve multiple steps, and they could be variable steps. But in terms of comparing these, you probably again want some kind of common unit of comparison, and it could just be that an action is counts as one. So you might say normalize it, just all actions count as one. But some elements of the world state might say involve several of these actions. So maybe you'd have an estimate of 3 for a particular symbol that could change. Or you might have, maybe rather than each action is just one unit, maybe it's based on time. In a video game, you might have actions that are, say, based on animations that play. And so maybe you normalize these sort of heuristic scoring based on the amount of time. But there could be other game resources as well that maybe makes more sense. So this is something where it's going to be very sort of domain specific in how you go about doing things, and how much work you want to put into heuristic design. Now, from academia, there's some suggestions on how to deal with a heuristic if you want it to be admissible. And so this is, in order to be admissible, if you have, say, you're trying to estimate, again, differences in world state, and you say you have a handful of things that are different, which would suggest you've got like actions associated with each of those differences. Like you got to get, say, collect a number of things. The character has to have collected like 4 or 5 things in their inventory. Then you're probably going to have like 4 or 5 actions at least to realize those changes. So the safest thing to do is that you could just pick, well, which, addressing those preconditions, which is the one that is going to cost the most. And so just use that as the estimate, that one thing. Now, realistically, you would think, well, the agent still has to do all those other things. So surely it would cost more than the maximum, but you can't guarantee it because you might have more side effects from whatever actions are performed. You can't guarantee that they're independent of one another. So the safest thing is to just only take the maximum. But if you take the sum, again, if they're not independent, that might overestimate. So if we take the sum of estimates of whatever changes need to be made between these two different world states, the current and the goal world state, that sum might be overestimating if the actions being performed are not independent of one another. So, but you could probably argue that the sum in most cases is a more realistic sort of heuristic. And so, in fact, that's what was used in FEAR. If you listen to the entire presentation, there's a question at the very end of the presentation someone in the audience asked. And so in FEAR, each action, well, there's an assumption that for each difference in the world state, that there is one action associated with changing that, and it costs 1 point. So all actions are just weighted equally with this value of 1. So if there's like 4 things different between the current state and the goal state, then the heuristic is that it costs 4 units. And Jeff Orkin said it worked fine in his situation. So he probably had a lot of independence between the actions that were performed, maybe entirely guaranteed independent, perhaps, which I think in a simple game that might be a reasonable sort of thing. So the benefits of planning, decouple goals and actions, and because of that, you can do things like what Jeff Orkin was able to do in FEAR, creating these new character types with minimal effort. It's really, the effort fell more on the side of the artists and animators rather than him as the AI behavior designer. And overcomes issues that make state machines that become unmanageable because of dealing with all of those contingency type transitions. It also allows for dynamic problem solving, an ability to replan when failures occur. So basically capturing the sort of ability that you would have in a finite state machine that truly correctly captured all contingencies, but without having to put in that development effort and debugging. All right, so where do you go from A-star behavior planning? So there's clearly limitations. If you have lots and lots of actions, things are not going to scale very well. You just have a heavy burden for any sort of search to find possibilities. One way to address that is with hierarchy. So you can have a hierarchical task network, and this is, at least at a high level, works much as you would probably expect. We're going to encapsulate more primitive sorts of actions within higher level descriptions. So, for instance, going on a trip might, say at a high level, you're just going from location A to location B, but that could consist of lots of smaller steps, like getting a cab, taxi to take you to the airport. In the airport, you take one airplane flight to one city and then to another, or if you have a direct flight, and there's all these different possibilities. There's other things as well, like maybe build a house in a game, or perform some sort of strategic maneuver in a military game. And so there's an assumption that all the lower level preconditions are met when this higher level plan is made. So once a high level plan is made, it needs to be broken down into the smaller levels and then check to make sure all the correct preconditions were met at the lower level. And if they're not, then that's going to bubble back up to the higher level and require changes to the plan to fix it. But if, assuming that the high level plan is feasible, then you can decompose it down into all of those base low-level actions, and those are what the agent is actually able to interpret and perform. So this has benefits because it limits the number of operators that would be performed at any given point in the A-star search. So you can considerably decrease the number of actions that need to be analyzed, and but then you still have this opportunity to double check and make sure that it's truly possible. You're, say, given a task, and then you pick a method which conditions match the current world state, or pick randomly. Then you work your way down to the lower level in the hierarchy, and then consider the application of those lower level operators, and keep continuing the process. And then the agent can execute the full plan once it's realized. Now, another interesting thing is that you can create a partial plan, maybe by only decomposing, say, early parts of the high-level plan, and assuming that the high-level plan will continue to work. But if not, worst case is you just replan. And so there's these performance benefits, again, because you're able to do a lot of the searching aspects of the planning at this higher level, and therefore less actions and state information to be considered. So we could think about how this might work better than, let's say, an A-star behavior planning approach with a hierarchical task network. So search time, very likely we're going to see these improvements because we're representing lots of primitive states with these higher level, primitive actions with these higher level actions. Authoring time, maybe would be a bit more work with a hierarchical task network, but there also tends to often be natural structure to organizing, and the fact that you are organizing could be beneficial just in terms of managing and thinking about the problem. Now, optimality is a situation where the hierarchical task network can lose out. The abstractions that are taking place might mean that some sequences of lower level actions or behaviors will never even be attempted by the search algorithm, because you've got these boundaries between the higher level. When you decompose down from the high level to the low level, there's kind of these boundaries imposed, and so there might be optimizations that, if the entire A-star search was performed, it could work out a lot better. Also, similarly with the optimality, novelty or predictability can be a problem, and if you had everything A-star, you might have more novelty because more possibilities are explored. And lastly, partial solutions. You can more easily do that with hierarchical task networks, because you can just work only with the high-level parts that you're interested in the short term, and then later decompose as needed. All right, so that concludes our look at goal-oriented behavior and A-star planning.